The door stays open.
Someone will close it at some point, I believe. Let's get started then. Good morning, everyone. If we could have the first slide up, that would be great. Thank you. Welcome to the Land Ice session of the CSM workshop. I'm Gunther Legui, the co-chair of the Land Ice Working Group with Miriam Vizcaino here, and Kate, our software liaison, is also here. We'll be moderating this session this morning. Before we start, I would like to remind everybody with our code of conduct, which the bottom line is be friendly with one another, ask nice, good question, and try to engage in good conversations. As an experience here, I just want to remind everybody, there is no stupid question. We all come from different backgrounds, and it is okay to have a question that, if you're not an expert, if you don't know Land Ice so much, it is okay. That's what we're here for. So we have a great agenda today. Do I do the next slide? Yes, so, yeah, okay. And Miriam Vizcaino is going to moderate the first half, and then Kate is going to take over. We're going to be passing the microphone around if you have any questions. Each talk is meant to be about 10 minutes plus 3 minutes for question. I am the only outsider on this, where I might not take any questions, and you can ask me question after the break, depending on how long I run. So without further ado, I'm going to start this session by giving you a brief update regarding the community ice sheet model CESM and our path towards CSM3. So I had put this slide up for how getting a community Earth system model ready for release is like tricky, because it includes many different areas and intricacies that you have to take into account. And I quickly realized that when you switch CSM with CESM, well, it remains true. So so we're still spinning the wheels, and eventually we're going to get to CESM3 with intermediate steps here. And our path towards CSM3 and CESM3 started a couple of years ago. Pretty much as soon as CSM2 got released-ish, we were on our way to CESM3 and also CSM3. So we are here. Okay, we're summer 2024, and the CSM3 science freeze, as Dave Lawrence hinted at yesterday, is going to be within a month now, at the end of July. And then the full release of CSM is going to be in the winter, and we plan on to have a similar timeline for CESM for the next release. With respect to the Land Ice Working Group plan for CSM3, here's our timeline until the science freeze and then the delivery of CSM3. So as maybe some of you went to this software engineering working group workshop yesterday, and we are working on diagnostics with Cupid for the Land Ice diagnostics. We are right now also in the work of diagnosing the surface mass balance from CSM and how it can be used to generate a good Greenland spin-up within CESM. We're going to do something similar for Antarctica, and with a goal of putting these two modeling items in sync. It's not working super well here. There it is. You can see here in yellow, this is an effort that is ongoing in replacing the no-evolve mode of CESM with a data GLC, and Kate is going to tell us a little bit more about this right after I'm done talking here. And this is along with the development for the Antarctic ice sheet coupling within CSM3. It's a development that is undertaken with collaborators in Norway with Maja Verdenstein, Heiko Golzer, and Michele Petrini, but also here at SFNCAR with Bill Sachs, Bill Cade, and myself. So when it comes to Greenland, that our main goal right now with the development of CSM3 and the workforce being run right now to see how the model is doing, we care a lot about the surface mass balance that CESM would receive from the PI, from the pre-industrial stage. And what you're looking at here in this figure is the surface mass balance for the PI control of CSM2, like it was before, what is currently the PI control development for CSM3, and that you can compare with the regional climate model here. It's MAR that we chose for this. The PI control for CSM3 is averaged for over the last 40 years of what's available to have a similar climatology lengths as MAR provides. And you can see, if you look in terms of general patterns, that there's a good agreement currently between CSM3 and MAR. And you have wider ablation zone. Overall, you also have a wider accumulation zone in the southwest here with too much snowfall. And in this case, of course, CESM is said to no evolve, but CLM can still form bare ice over the tundra. At the bottom here, I've put the net average of the accumulative sum of this integrated surface mass balance, and you can see for MAR, there is about 350 gigatons per year. So it means that without a dynamic ice sheet, the ice sheet would be gaining mass, and it was the case in CSM2, and for now in CSM3 as well. It's not a showstopper, of course. However, here you can see, even though the number is a little bit lower, it's because of greater compensation of greater accumulation and greater ablation. So there's improved snow physics and soil temperature in CLM that might help with some of these biases that's still not in place here. But all things considered, because the model hasn't been tuned here to improve surface mass balance, this is still very promising. We're also actively working on Antarctica, a spin-up for Antarctica for the pre-industrial here. So this present like new challenges that we haven't dealt with before. And this is done in collaboration with Mira Berdal and Eric Steig from the University of Washington and Betty Otto Blisner and SFNCAR from projects that we're funded under. This is a sample of the challenges. In Antarctica, the Grounding line has been retreated over the historical period. And so it means that if we want to go back to the pre-industrial stage, we need to make the grounding line re-advance a little bit where it used to be, if you want to be a little bit more realistic. For example, you can see there's this, oopsie. There's this white box here that is the inset of this plot here, which is Pananun Glacier. And you can see that this is a better topography of Pananun Glacier where the ice lies in. And in black here, you see the grounding line of the current observed area. And this red star here is from proxy data. The group was able to diagnose that the grounding line used to be on this little ridge here. So about 40 kilometers more forward than it is today. So there are many things like this all around Antarctica that we might try to deal with for important parts, and like to not have too much retreat of the grounding line as we simulate the historical period. So this is still in testing. Mira has a poster actually outside his door about this project. There's also the ice-ocean interaction problem here. Right now we have, in CESM standalone, we have a crude representation of ocean thermal forcing in ice shelf cavities. And the way we do it, we just linearly extrapolate of the ocean condition at the calving front, because we don't have interactive ocean or other thermal forcing information. We could use the product that has been used for SMIP6, but then we need to adjust it for CSM2, and we don't have data for CSM2, for example, under the cavities. So one way to go about it, of course, is to use some information from MUM6 for the Ronnie Kirchner and Ross ice shelves at the very least, these two big ice shelves, because at 2/3 of a degree, the workforce resolution for MUM6 can actually generate some information, some ocean circulation under these big cavities, but not over the smaller ones. Another way to go about it is to add a sub-iShelf cavity circulation module within CESM, but this is still in the work and it's not clear that it's going to be ready for CSM3 release. Another caveat here with ice-ocean interaction in Antarctica comes from the MOM6 grid. And what you're looking at here is, of course, it's Antarctica on the CESM grid at 4 kilometers. And you have these dotted lines that represent the extent of the MOM6 grid of the South Pole. So it only extends to 81 degrees south. And so you can see here clearly that for the Ross ice shelf, it cuts it in half and it cuts the grounding lines in half as well. So if we were to simulate and try to do the ice-ocean interaction here, we would maybe do a good job at the grounding line here, but then there would be a complete unknown in this area. So one solution for this would be to extend the MOM6 grid to down further south to 85 degrees south, which would lead to this circle here and alleviate this problem. And another solution potentially would be to move the pole a little bit, but that might be a little bit more complicated. So this is an ongoing discussion that we're having with Gustavo Marquez. But this won't be delivered with the release of CSM3, but maybe in a later release. And the reason why this is even 85 degrees south would be better. Here on the right-hand side, you can see that if we remove the Ross and Ronny ice shelf, which is a potential experiment that's going to be done with TipMip, you can see that even there, the 85 degrees south grid would not extend to some of the grounding lines, but it would already be better. One of the caveats, of course, in extending this grid is that it might impact the ocean time step in computing time. So a lot of work needs to be done here. 1 minute. Ooh, okay, good. By now you might have heard that CESM has been adapted to be used for glacier modeling. There's a poster outside this room about this effort, and this was undertaken by mainly by Bill and Sama Minara, a postdoc at NSF NCAR, and we successfully use CESM to simulate alpine glacier. And here this is an example of the Mont Blanc area in the Alps. We were able to model the entire Alps. But we have ongoing effort with collaborators who are interested in using CESM for further studies. And the Southern Patagonia icefield is one example, and Matthias Troch is going to talk about it later on today. This will have other challenges that the Alps didn't have, is that a lot of glaciers in the Patagonia are man terminating and they end up in fjords. So we'll have to work on something to work out there. And lastly, we're going to go back and trying to simulate high mountain Asia. And because of the size of the domain, this was a little bit challenging. Last but not least, the CESM release that is going to come with a delivery of CSM3 will include, we call it CESM 2.2, and it will include all of these new ice sheet physics, initialization, test cases, and code validation, and they're all pretty much ready to go. So that is very exciting. I still need to deliver on the test cases. For later release, CSM3, we're going to have other targets. I just want to highlight here that new calving schemes and option might be included into the CESM 2.2 release, and Bill is going to tell us a little bit more about this in his talk this morning. So I haven't touched on other things, just like paleo sheets or GIA, but if you have any question on this effort, please let me know. And for whatever information you might like, please reach out to us. Me and Kate or Bill, we're always here to answer questions. Thank you very much.
Thank you, Gunther. Our next speaker is Kate Theyer-Carter, and she's going to give us updates to the coupling of the ice sheet and ocean.
All right, thanks, Miriam. Hi, everybody. My name is Kate Theyer-Carter. I'm an associate scientist at CGD, and I'm the software CESM liaison for the Land Ice Working Group. So like Gunther said, feel free to talk to me if you have any questions about CESM and CESM3. In particular, we've made a lot of changes this year, and we're getting ready to support some really exciting science in the future, which required some big differences in the way that we've been handling coupling between CESM and the other components. So this is kind of an informative talk. It's got a lot of boxes and arrows and plumbing. And if y'all zone out, that's fine. You can come back to it later when you've got questions. That's totally reasonable. Just a quick overview. Oh, hey, I didn't think he was going to work. So I'm going to give you an overview of where we were in CESM2 and go through the issues that we had with that over the last few years, just to sort of motivate the changes that we've made so far. And then I'm going to talk a good bit about each one of those and finish with a list of the science applications that we're aiming for that. So I know you guys have been here for 3 days and you know how CESM works, but I want to start with sort of a zoomed out view and then sort of zoom in closer and closer as we get to what I'm talking about here. CESM has a hub and spoke architecture where each of the components talks to a driver mediator in between. It advertises those fields, and then any component can pick up those fields or request those fields. Some components expect certain fields from other components and need to know right at the model startup what is going to be available so that they can compute what they need based on what is out there. For this talk, I'm going to look at CESM. Let's see if this works. Nope, that's going to move the slide. Which one is this is the top button? Top button? Okay. Oh, there you go. Yeah, so CESM up here, and then the ocean and the land. And I'm going to kind of get rid of the mediator in the middle. You guys can just assume that all of the arrows that connect these things are going through the mediator, and the mediator is handling that grid remapping between the different components. Okay, so this is a figure from CESM2 and the Laura's paper that it's just so nice. It's really pretty, and it makes everything look so simple. But it was a good overview of what the couple fluxes look like in CESM2. And you can see that we've got some interaction between the ice sheet and the atmosphere up here that was done offline. It's not handled while the model is running. So I'm not actually going to address that today. That's sort of a separate step to all of this. What I'm going to talk about more is the CESM and land coupling, and then the CESM and the ocean coupling. Oh, yeah, so they're there. Okay, so in CESM2, that lovely picture actually ends up looking more like this. So this is my boxes and arrows, and things are getting a little more complicated. But we have two types of CESM. I want to remind everybody this. We have the CESM evolve with the fully dynamic ice sheet that is evolving in time. And then we have what is called CESM no evolve, where the ice sheet actually isn't called. So you still get all of the CESM code. You still have to build the CESM code. You have to have that code in your sandbox. But then at runtime, when the model goes, even if you have some processors associated with it, nothing happens. It just does, it skips right over it. So because of that, CLM, which manages the surface temperatures and mass balance for the ice sheet, actually has to handle the ice sheet differently when it knows that it's not evolving underneath it. So it handles the runoff fluxes and what's called snow capping fluxes completely differently when we're in a no evolve mode. So that's why there's this guy's just coming out the side. It's weird. We've got some surface in SMB for CESM evolve, and then we've got different surface in SMB coming when CESM is no evolve. And then also in that case, we have what are called snow capping fluxes, because you can't grow the ice sheet anymore when it's non-dynamic. So CLM sends those straight to the river runoff, and which goes to the ocean. It doesn't matter if you're in evolve or no evolve mode, CLM will always send the rain and surface melt to the river runoff model, which goes into the ocean in CESM2. But CESM, when you're evolving, it handles the melt, the basal melt, and the glacier calving and sends that straight to the ocean, disregarding this sort of regular pathway in CESM2. All right, there you go. So let's look a little bit more about this and what sort of issues that we've kind of hit up with it. This differences between CESM evolve and CESM no evolve from the CLM point of view has caused some problems. Because CLM has to manage the conservation of water in the ice sheet when CESM is non-evolving, it's done things like produce negative ice fluxes. It has all this extra code for those cases. And it's a little bit difficult to understand from a scientific point of view what the differences are between the two. And then, yeah, so here's the negative water flux issue. So the snow capping happens whenever we get more than 10 meters of snow above the ice shelf. CISM will send that to the ocean because it can't grow more ice. But then later on, when it's melting, there's no ice available to melt, so it pulls the water back in from the ocean. And we have a couple of different ways of fixing this. Last year for this meeting, I talked about one method that we were going to implement in CLM because this is only dealing with CISM no evolve. But we've come up with a better way to handle that with a new feature, the data GLC, which I'm going to talk about in a second. In CSM2, like I mentioned previously, the basal melt and calving actually go straight from CISM to the ocean. And this requires some meshing in ice sheet, the grid mapping files from one to the other, because the ocean cannot take a point influence of water very easily. It needs to be smooth. So this gets really complicated quickly when you have multiple ice sheets, Greenland and Antarctica. You have multiple grids available for each one of those ice sheets, and they start bringing in new ocean models, and each of those ocean models have new grids. This mapping system here starts getting really difficult to handle, and we've hit up against this issue with Antarctica and specifically. And then you'll notice that there's no heat flux coming back from the ocean, which is really important for Antarctica, especially for sub-ice shelf melting, like Gunter was talking about previously. So CESM2 just didn't support this flux at all, and we'd like to add that for CESM3. So the other issue here is that the options that we had available for CESM2 were either CISM evolve or CISM no evolve. And as I mentioned previously, this means that you have to get all of the CISM code if you're going to use one or the other, and you have to compile it and have it available for the model to run, even if the ice sheets aren't doing something. And this caused some of the components that have component-specific com sets, like the atmosphere that runs an F case, it doesn't really care much about ice sheets, to move to a stub glacier from CISM no evolve so that they don't have to have that extra code management. But there are certainly com sets that could use that in between non-active stream reading ice sheet without all of the CISM overhead. And that was the motivation for the DGLC that I'll talk about in a minute. So what are we doing for CESM3? We've got a new flux that we've added in from the new ocean. So you see we replaced POP with MOM, and now we have the ability to transfer heat and salinity below ice shelves. Oh, that's only 2 minutes, okay. From MOM to CISM evolve on multiple layers below the ice shelf. So we've got this flux added in. And then we've rerouted those fluxes, the melt and calving fluxes from the ice sheet through the river runoff model. So they follow a similar path to how CLM handles them. And that actually reduces the need to have those mesh complicated ocean ice sheet mapping files and makes the whole system much simpler from the runoff and melt standpoint. And then we've replaced CISM no evolve with this data glacier model that Mariana Vertenstein has put together. And her name was on the first slide. She did a ton of work with all of this and did a great job. This component actually reads in multiple streams in the same way that CISM evolve does. So from the standpoint of all the other components in CESM3, it's completely interchangeable with CISM evolve. We don't have to have special surface fluxes or handling of the code from CLM standpoint anymore. It's very transparent, and you don't need the whole CISM's code base in order to run it. So hopefully this would be much more appealing to those all active and ocean com sets that need something to interact with to test their fluxes without needing the whole of CISM going in. And we're very excited about this. I'm very excited about it. Mariana seems very excited about it too. She's done awesome. So this is where we were with CSM2. Just to go back to my initial slide, we've got a whole lot of different options for CISM. We've got different negative fluxes. And now here we are in CSM3 with a much more clean, laid out, and highly functional coupling framework. So we've added things and simplified at the same time. And I wanted to thank so much the people at NORISM again. Mariana has done a lot of heavy lifting for this so that it can be used in both models, and Heiko and everybody else out there has really been working hard on all of this, and we can use it together, which is great. And then a quick list of the signs that we want to support with this. So CSM3, the default all active comp sets are going to include evolving Greenland ice sheet, which is going to benefit from those runoff through the river runoff models. And then we're going to hopefully support an out of the box, not necessarily scientifically supported, but available Greenland and Antarctica with some version of CSM3. It may not be 3.0, maybe 3 later. We've got the possibility of doing experimental coupled comp sets with mountain glaciers, and that's what I was talking to Samara about. And we needed this river runoff model because those do not move to the ocean. Bill Lipscomb is just laughing right now. Sorry. And I'm hoping that when we have these sub-ice shelf heating fluxes from the ocean, that we'll have better simulations of the evolving Antarctic ice shelf to produce better sea level simulations. Got ISMIP coming up, TIPMIP, all the MIPS. So this is all a very exciting time, and I think that we've got a good architecture to support all the science going forward. Here's some useful documentation for CSM2, and hopefully we'll have it written for CSM3 before too long. So thank you, guys.
Thank you, Kate. We don't have time for questions, so we are going to move to the next speaker. That is Sandeep Narayanan-Sethi, online, I think, remotely from India.
Yes, I'm
Yes,
online.
we have you
Yes.
there. Okay. Sandeep is going to talk about the influence of Greenland melt on the ocean circulation.
I'm unable to share my screen. I think the other participant is sharing. Sure. Hello, everyone. So myself, am I audible?
Yes.
Yeah.
Yes.
Thanks. So I'm Sandeep Narayan-Sethi. I'm from Indian Institute of Tropical Meteorology in India. So I'll be talking about the topic of influence of Greenland glacial ice melt on global climate. So I'd like to give you a broad overview of our model, which we have from our institute, which is IITM. So we are the first ones from India who have participated in CMIP 6. So we have the atmospheric component of IITM ESM as the GFS, which is the global focus system, with 200 kilometer resolution with 64 vertical levels. So it is T62. It's a spectral model. And the land surface model which we have is NOAA LSM, and the ocean model is the MOM4 P1, which is tripolar. Moving ahead to IITM ESM V3, which we'll be using for the CMIP 7, we have improved the atmospheric and oceanic resolutions, and we currently have a TCO 126 atmospheric grid, which is approximately 67 kilometers in the tropics. And also ocean with this increased ocean resolution of around 0.25 degree near equator. And also we have an interactive river discharge in the current version of the model. We have land use land cover type incorporated. Earlier we had 13 types and now we have 24 types. And the other major inclusion which I'll be talking about and what the results which we have obtained so far is the land ice inclusion that is for the Greenland only. And also we have some improved aerosol microphysics from our model. So here is the schematic of how we have incorporated the TCO grid in our model. The incorporation of this triangular cuboid octahedral grid will actually help us to get a higher effective resolution near the tropics and also the better computational efficiency. So we have resorted to this from T62 to TCO 126, which was almost 3 times the resolution improvement. On a broad scale, this is what we'll be doing. So we have a TCO 126 grid. In between, we have incorporated TCO 62 grid, which is almost 140 kilometers. And we currently move to TCO 126, which is 67 kilometers. And this is our CMIP 7 plan. We would like to participate in the IPCC AR7 fast track simulations, which include DEC, Scenario Map, DMAP, PMAP, and LMAP, GeoMap, and CFMAP. These are the preliminary results from our model, which shows the TAS on the upper left panel, we see a relatively, this is a 2010 control simulation. We see a stabilized temperature, and also because our climate model, which we have shifted from lower resolution to a higher resolution, we tried to see the top of the atmosphere radiative imbalance in the model. And we see almost well, around 1 watt per meter square at the top of the atmosphere radiative imbalance. And also when we check for the top of the atmosphere minus surface, our model seems to be stable in the bottom right panel, which is around 0.2 watt per meter square. So with global mean fields, which from IITM ESM v3, which showed an improvement, we moved to see what are the better results which we were able to get. We see a substantial improvement in the Atlantic meridional overturning circulation, which causes a reduction in the North Atlantic bias in the lower panel, if you can see, and also a reduction in the Southern Ocean SST bias because of the North Atlantic deep water formation, which rises as a branch over the Southern Ocean, and that is getting improved in the current version of the model when compared to the previous version. So we see there is a cooling, relative cooling or reduction of the bias, warm bias in the Southern Ocean. So giving us this state of the model was given us the hope and chance to integrate the CISM for Greenland, configure for Greenland into IITM ESM. Since we had only sea ice component and Arctic sea ice is melting at a higher rate in the recent decades, and also it's projected to increase, and the unprecedented melt is going to change in the future. And also because the Greenland glacial ice melt is also happening and it's going to change and increase in the future, we tried to incorporate, it's a very preliminary way of doing it, thanks to Dr. Gunter and Dr. William Lipscomb, who have encouraged us to use their model and helped us to incorporate the CISM. So what I did was the IITM ESM, I have used from IITM ESM CMIP6 simulations. I have ran a 4 kilometer Greenland setup of CISM using PDD scheme, in which I have given the precipitation, temperature, and topography from our model, forced the CISM, and the outputs from the CISM, that the accumulation, ablation, ice temperature, air temperature, basal melt rate, and ice thickness. I have used the freshwater flux, that is the accumulation minus ablation, and I fed it to the MOM, that is the oceanic component of the IITM ESM. So the freshwater discharge from the Greenland is added to the river runoff, which is actually computed from our atmospheric model. And this is actually fed into the nearest ocean via the river destination fields. So the river transport, we actually follow the protocol by GFDL, and we use the river destination fields, and we route the water, that the precipitation minus evaporation, into the nearest destination point. So this is how we have incorporated the Greenland land ice melt. It's a one-way coupling, and I'm going to show you some preliminary results, what we have obtained by using this particular schematic or this particular pathway. So here I show on the extreme left the ablation time series, that's a blue color curve, from the Greenland computed from CISM, and which is provided as an input to IITM ESM. And here in the center panel top, the blue color curve is the historical surface air temperature globally averaged. We see there is an enhanced in temperature, which is obvious. And we see in the last 25 years, the red curve is where I have included the Greenland melt also. So we see that there is a, if not substantial, there is a cooling due to this Greenland ice melt, which I have incorporated. So focusing rather than on the global mean SST, I have seen the SST anomaly deviation from 1985 averaged over the Atlantic. So here on the right panel, the highlighted is the Atlantic region, which we have considered. The blue curve is from the CMIP6, and the red curve is from the green, and where we have incorporated the Greenland discharge. So we see there is a cooling due to the enhanced Greenland ice melt, which I have imposed, and also freshening due to the enhanced melt, that is the reduction in the salinity. The same thing we have seen seasonally, salinity, and we see that there is, with the seasons, we see that there is a freshening, which is because of the Greenland. So then we saw the SST, like I've seen there seasonally, and we see there is an SST cooling over the entire northern Atlantic with warming over the subpolar gyre location, the sinking branch of AMOC. But another conspicuous sign which we see is the warming across the tropical North Atlantic in March, April, May. And a switch of signal from El Nino, this is a El Nino kind of signature. We see that is also popping up when we have introduced the Greenland glacial ice melt. Also, the other conspicuous scene we have seen is the this is the SLP, seasonal SLP difference when we have included the Greenland minus the control, which is the CMIP6 version without the Greenland.
Sorry, the 2 minute, check.
Yes. So here we see a strengthened Icelandic low and a weakened Azores high, which is a sign of a negative North Atlantic oscillation. That is a negative NAO. The GPH and the winds also show that is a negative NAO during MAM. So this negative NAO is one of the important factors for contributing to the North Tropical Atlantic warming, NTA warming. And we see clearly there is an NTA warming over the North Tropical Atlantic, and see the SST increase. And also this wind evaporation SST feedback. Here I'm showing the latent heat flux. The wind evaporation SST feedback is actually helping in order to generate a negative NAO and the tropical North Atlantic warming. Also, we see that there is, because of these changes in the North Tropical Atlantic, the SST anomalies over the Pacific are also getting affected based on the papers recently in Schwale et al. And they have shown that the North Tropical Atlantic can actually change the characteristics in the Pacific. And we see that there is a shift from El Nino to a La Nina kind of state. And also because of the changes of this upper level salinity and the temperature, we see a reduction in the AMOC. We see there is a, when we see we almost saw a one Swedrup reduction in the Atlantic meridian overturning circulation, and the black line is from the control and the red line is from this is the poleward ocean heat transport, and we see there is a reduction in the ocean heat transport. Also, the meridional stream function, if we see this, the red is the warm waters which are getting transported towards the north, and we see there is a subsurface reduction in the strength of AMOC, and also weakening of the North Atlantic deep water formation, which can influence the Southern Ocean SST biases. Putting in a nutshell, this is what we are seeing. The precipitation responses also are important, and they are actually playing a major role just by inclusion of the Greenland land ice melt. So there is a lot of work which has to be done to incorporate Greenland land ice melt, but with the preliminary one-way coupling, we are able to see these results. Though I understand that we are at a preliminary stage, but we'd like to put a two-way coupling into the our IITM ESM and try to understand the role of Greenland with more detail. With, of course, the focus of more monsoon and changes in the ITCZ because of that. And there it goes. Thank you so much. Thank you so much for giving me this opportunity.
Thank you very much. Thank you very much. This is a great work. Maybe one quick question.
Oh, thanks.
If not, we move to the,
I'll ask one. How do you initialize your Greenland ice sheet from when you start running it at PI?
Oh, yeah. So what I have done is I have used the CISM version 2, which I've got from Dr. Gandhar, and I have used the pre-industrial surface air temperature and precipitation and topography from our model. And we have ran for almost 40,000 years in order to get a stable mean state of surface air temperature over the Greenland. And once it's stabilized, and that is the point where we have started our historical where I've said that there's Greenland inclusion into the model.
Super, thank you. Our next speaker is CG1, and he's gonna talk to us about the drivers and feedbacks for Greenland melt.
Thank you. Okay, yeah. Okay.
So I'm using CESM to create the ice model.
Thank you. My name is Ziki, and I'm a PhD student from CU Boulder, and today I'm going to present the current results from this ongoing project. So, as the main contributor to the mass loss of Greenland ice sheet during the past decades, the surface melt has increased significantly over the past decades. And on the left figure, we show this is like projection from RECMO 2, and it shows that by the end of the century, there could be another 5-fold increase of the surface melt. And in the right plot, it shows the daily melt content from NISIDC, and we can see the large variability of like the subseasonal variability of this. And what caused these variations and changes is a causal question. So the surface melt is controlled by the complex interactions between the ice surface and also with the atmosphere. And there are many feedbacks, like for example, the albedo melt feedback, geometry SMB feedbacks, and we can calculate the melt energy based on some like adding up these surface energy balance terms, which are the night long wave, short wave radiation, latent heat, sensible heat, and ground heat flux. And here we are trying to enter these two questions. So first, what is the relative importance of these energy balance terms and precises for driving the surface melt of Greenland, and also in the global warming, will there be a regime shift? And we are using causal inference because causal inference goes beyond correlative approach by trying to establish the direction of the link and also identify the confounding factor, and also is able to extract the network from a complex system. So the method basically a causal inference method contains two steps. The first step is to you input a time series and it outputs a causal graph qualitatively. And the second step is based on the causal graph, it estimated quantitatively the causal effect. So the method we use here for the first step is called PCMCI plus, which is an extended version of the PCMCI method that can both identify contemporaneous and lagged causal links. And this method has been applied to climate science, like detecting the causal relationship between climate variability modes. And here is an example of the causal graph. And we can see in this causal graph, the sign, direction, and the time lag of the causal links are assigned. And if there's no number on the causal link, it means a contemporaneous link. And you can also see for some of the causal link, there isn't an arrow, but with two white circles at both ends. That means an oriented causal link. And if there's a cross sign, that means it has a competing causal effect from opposite directions. And there are several assumptions need to be made for applying this method. And for data we use is from a couple CESM2 simulation, which include a historical simulation using a 1 degree version, and also idealized warming scenario. We use two versions. One is the 1 degree, and also we use this variable resolution grid that has a 1/4 degree refinement over the Arctic region. And to compare with this, we also use regional climate models, RECMO and MAR, and also one firm model that is have the same atmosphere forcing with RECMO, but has a different surface physics. And this is shows the top panel shows the CO2 forcing of the idealized warming scenario. So we have run this pre-industrial control until the ice sheet achieve near equilibrium state and start this 1% per year CO2 increase, and then until it reaches 4 times pre-industrial value and run another 210 years. And for both the this pre-industrial and 4 times CO2, we use the last 50 years for our analysis. And for variable selection, we select melt fluxes and the 4 major energy balance terms. Ground heat fluxes is not included because of its smaller magnitude. And we use monthly time resolution, and all the variables are averaged over the ablation zone of the ice sheet. So this the data preprocessing includes two steps. One is detrending and also normalization. So these are the time series before and after the preprocessing. Okay, so first we evaluate the causal graph from CESM2 and the regional climate models and also GAMP. So we can make, so first we know that because we select the variables based on the energy balance equation, so we will focus on the causal links connected to melt instead of causal links between energy balance terms. And also, so the map here shows the ablation zone mass for each of these simulation. And another thing to note here is this GAM has a relatively shorter time periods compared to the other three simulations. So we can make several observations here. So first, most of these links are contemporaneous. So that means these processes are fast at our monthly timescale. And another thing is all these models agree on the positive connections between shortwave melt and sensible heat and melt, but the difference is their directions. So for CSM2, we detect this lagged melt albedo feedback between melt and shortwave, with 1 month lagged causal effect from melt to shortwave radiation. But for these two regional climate models, we found this competing causal effects, which could mean contemporaneous feedback loop, but not necessarily. It could be just the method cannot detect the direction in these two simulations. And yeah, this is and then we also so this plot shows I also applied the cross correlation based on the same time series, CESM2 historical time series. And we can see compared to the PCMCI causal graph, the lagged correlation graph shows much more significant links, which decrease its interpretability compared to this causal inference result. And then we compare the pre-industrial simulation period with this 4 times CO2 period. So that's the left and right column shows, and the two lines shows this 1 degree version and this a 1/4 degree version. So we can see in all of these causal graphs, this lagged melt albedo feedback is quite robust. And another thing is in this 4 times CO2 period, we also identify a positive causal link from latent heat to melt, which could mean in a much warmer climate like this 4 times CO2, the latent heat fluxes may play a larger role. And then I estimated the causal effect based on the 1/4 degree version causal graph. So, okay, yeah. So this two panels shows the direct causal graph at lag 0 and also 1 month lags. So if we focus on the top causal graph, from the blue dot to red dots, which shows from the pi control to 4 times CO2, we see a decreasing causal effect for this radiative fluxes, but an increasing role of the sensible heat. But still in the 4 times CO2, the dominant driver is still net shortwave radiation. So I will give a summary of the current result. So we show that causal inference can let us focus on fewer important drivers compared to a correlative analysis, and can detect lagged feedback loop like the melt albedo feedback for Greenland ice sheet surface melt. And but there are problems like I forgot to say the problem are in our causal graph, the direction of the causal links are not very robust. So we are trying like different causal inference methods to see if it has a better result. And to answer our research question, so first we identified that both in a pre-industrial period and also in a much warmer climate, the night shortwave radiation is the dominant driver for surface melt. And but in a warmer climate, there's a regime shift of this direct causal effect of these different energy balance terms, with an increasing role of turbulent heat fluxes compared to radiative heat fluxes. I think it is agreed with previous studies, like in a warmer climate, there could be, for example, more warm air penetration at around the ice sheet margin, and so increase the turbulent heat fluxes. Okay, thank you very much.
Time for final questions.
Everything was crystal clear.
We move to the next speaker, who is Dan Martin, on the impacts of the damage rheology coupling on ice sheet evolution.
This is the so this is very much a work in progress. Sort of look at this cool thing we're doing. Talk. And this is work with joint work with Sam Kachuk and Jeremy Vasses at University of Michigan, and then also some people came visit us last summer, Duncan Carpenter and Anjali Sandeep from University of North Dakota. And the overall takeaway is that real ice is messy. Like we do modeling, we tend to sort of assume a lot of smoothness in ice that isn't really there. It's brittle, it's like fractures, crevasses, et cetera, et cetera. And you can see that pretty much, all this stuff in Pine Island Glacier ice shelf. And the question then is how does that impact actual ice dynamics? So the way we generally handle this in ice sheet modeling is that we have these ideal ice sheet models, and then when we try to match observed velocity fields, we do two things. First we infer a basal friction field, but then in order to actually be able to match the observed velocity fields, we also have to adopt some sort of viscosity multiplier, particularly in the ice shells. And this is what we've done for the Amundsen Sea. And you can see that there are two things. The red areas are where we have to substantially reduce the viscosity to be able to match observations. The blue is places where we have to harden the ice, and that's probably because our temperature field is too warm. And so don't pay attention to the blue stuff. That's basically just a bad temperature field. But this is actual dynamics. And if you look, you can see that that's basically where the crevasses and damaged ice are, right? So that's great if you're just trying to do an inversion and model right now, right? But we want to be able to, but that doesn't evolve. We have a snapshot. We can't usually evolve these things. So what we'd like to do is actually model damage in a large scale model. And so the approach we're taking, we're following Bass's model in 2015. We start with the dynamics of a single crevasse. And you assume the crevasses are transported with the ice flow. And then if ice is in tension, the crevasses tend to increase. If ice is in compression, the crevasses tend to heal. And then from there, we go to the idea of a damage as a measure of the average crevasse penetration over some, unit cell or whatever. D equals, and then we have we make this quantity D. D equals 0 means no crevassing, no damaging. D equals 1 means that the crevasses fully penetrate the ice, and there's really no structural integrity there. And the goal then is to couple this D, this quantity we're evolving, with viscosity and then evolve it. So like I said, basically this evolution term for D is basically advection with a source term, the advection equation, and then a source term. And I'm going to just sort of be cartoony about this and say that it's a source term that's based on local stresses. It includes surface mass balance. And we sort of maintain a floor of the Nye zero stress minimum crevasse depth. The ice sheet model we're using is, perhaps unsurprisingly, bicycles. The key takeaways of bicycles are it's a finite volume, vertically integrated model. We use a version of the Schuf-Heimarsch L1, L2 approximation for the momentum balance. And it's an adaptive mesh refinement model. We can adaptively refine our computational mesh where we need to resolve things like grounding lines and shear margins and things like that. So it's a good thing for doing things where we don't really know where things are going to happen. And it's been used a lot for regional and continental scales. So we've done this, we've implemented this model, we have this source term, and we can do some experiments. The first is just to evolve this damage quantity. Don't couple it, just evolve this damage quantity in the ice. And then we start with the I values in initial condition and evolve to steady state and then see what that looks like. And this is an idea of if we're in the right ballpark. The other thing we can do is you use this to predict calving fronts. So the two tests we're going to do, we're going to use this to see if we can predict calving fronts, and also see what this looks like against what we've observed when we do from the viscosity multipliers we did when we did our versions. And this is in a paper, K-Chuck et al. 2022. The first test we did was our Drygalski ice tongue. Ice tongues are nice because they're a 1D test. And so basically what we did there was we ran out, figured out where the damage was one, calved it off, ran it, kept on running, and just basically did that recursively until we got to a steady state. And what we got was something that looked very much like what you see in observations. This is the plot of the damage. And you can see right where it gets to 1 is basically where the observed calving front is right now. And when you do that, the ice thickness you wind up with in bicycles winds up looking very much like the observations. So that means we're sort of on the right track, I think. We've done sort of we can do this sort of very simple test case. When we do this in the MSNC, we just, like I said, we just evolved this damage field. We've turned off the viscosity multiplier coupling. So this is basically just undamaged ice. We're evolving to try to figure out where the damage would be. And we wind up with something that looks very much like our inversions. We have high damage regions in the shear margins like you'd expect. And so then the next thing is then say, well, how do we couple this? And so what we need is a coupling function that's a function of the damage such that basically that becomes our viscosity multiplier in real life. And we experiment with various forms. The most obvious thing is just a linear function, right? The multiplier, the viscosity multiplier is just 1 minus d, because it's, you want it to be 0 with no damage, or sorry, 1 with no damage and 0 when it's fully damaged. But maybe there's some other things we looked at as hyperbolic tangent. There's a question of, is there a floor? Is there a place? Is there a minimum viscosity multiplier that doesn't go to 0? Things like that. And so what Sam did was he took our computed viscosity multiplier and correlated that with the damage he computed and created this plot. So two things jump out. The first is that this is a plot of damage versus the viscosity multiplier we observe from our inversion. This offset here is, like I said, because we're probably too warm. So this is that that sort of blue background you saw. But the two takeaways here are, first of all, the low damage. This never works when you want to do, does it? Low damage on the low end, there doesn't really have a big effect on the bulk viscosity. And then the other thing is, it looks like it doesn't go all the way to 0. It sort of caps off at maybe 0.4, 0.5. So that's more like the hyperbolic tangent we're looking at. So the next thing we did was, then we took this and ran this with a Mismet Plus example. Mismet Plus, you might recall, is a intercomparison project where basically it's a marine ice sheet, basically an ice stream in a trough. And the idea is it has it's designed to test buttressing and the idea is to maintain a ground line on retrograde slope due to the impacts of buttressing. So the idea is you spin this up to steady state, then apply basal melt forcing, which causes the ice sheet to retreat. And then you turn off the melt forcing and it re-advances. The warning I have here is that one of the big takeaways is that when you start coupling damage in, it makes your solver really unhappy. Our workflow is basically, Sam runs it, breaks my solver, emails me and says, I broke the solver, I fix it, next step, continue. Because if you went with these really weird configurations of ice and viscosity and really high resolution things that you haven't seen before. So just a warning, I guess. So the impact, this is grounded area, there we go. And this is volume of rotation over time. There's a bunch of experiments here. The key is that each color is a different example. So the 0 is the control experiment with no forcing. And then the dotted line is the damage included version of the solid line is no damage. The coupling, the dotted line, the dashed line is with damage coupling. And so you see in all cases, damage, including damage, reduces the grounded area, and also reduces the volume of rotation. So it increases the amount of sea level rise in this case, and increases the amount that your grounded line retreats. And if you look at this, is the plot of the damage over time. The top one is the undamaged one, the uncoupled one, and the bottom one is coupled. This is after initial condition after 100 years, or when the melting stops, and then after 1500 years. And if you look at that one in the lower right, that's with damage coupling in the steady state. That looks kind of familiar. And so so here's a movie of what's going on. And when I saw that, it was really exciting. So this is the plot of the damage. This is the retreat phase. So we're melting, You can see the ground line retreat. One thing is we very quickly wound up with an ice tongue instead of an ice shelf because of the effects of the damage. And now we're re-advancing. And you can see it's advancing very nicely. Advancing at a glacial pace. It's always much faster when you're, but the amazing thing that happens is when you get to this point, you still maintain an ice tongue, right? You never quite regain the whole ice shelf. And then you start to get these sawtooth patterns. And that looks really like what you see at the Erebus ice tongue, which is, I saw that, I was like, well, this is really exciting because I've never seen anyone do that before. And what's happening is you have these stress concentration that happens at that corner point, and that causes the viscosity to weaken, which then you have this sort of in and out, periodic thing that happens. So that was pretty neat. So the caveats here, this is, like I said, this is still very much a work in progress. What does this really represent? I mean, we have this sort of, we're moving from a crevasse single thing to some sort of integrated quantity. We're still trying to piece out what exactly that means in a model, right? Everything we do, we sort of start with this idea of an idealized thing, and then we sort of try to say, well, then we're going to make a model of it, and then you integrate it over a cell, and you kind of have to keep track of what you're thinking about there. And so we're still trying to sort out the coupling details and all these things, but I think it's an exciting start. Summing up, lots of progress. Incorporating ice damage into our models. I think it's a useful thing. I think it's really important. Still sorting out a bunch of details. The key thing to point out is that damage reduces buttressing. So this is actually, it has a real impact on things like, marine ice sheet coupling and how things, basic evolution and sea level rise. And a lot of what we've done is assumed a lot of buttressing, and maybe that's overestimating impacts. So
Thank you.
That's it.
Have you explored the possibility of using neural network studies that relate observations of the damage with velocities? Have you explored that path?
We thought about that because it's an obvious way to sort of get a damage model that's not as expensive and complicated as this. We wrote a proposal to do that wasn't funded. So we thought about it, but apparently not hard enough to be persuasive.
So is there any mechanism to deal with the healing?
Excuse me?
Healing.
Yes, I mean, there's healing that happens here too. I mean, you see that crevasses will heal. Yes, the damage can retreat, and yeah, my talk is gone. So, if you watch the movie, you can see the crevasses are healing too, as well as growing. The source term is both positive and negative. Right.
Yeah, move the next speaker. Previous to last, who is Joanna Milstein. She's going to talk about the extreme value perspective on Calvin events.
Okay. Is there this thing? Amazing. It's okay. I'm Joanna Milstein. I have really enjoyed zooming into some of this and hearing your talks this morning because I am really an observational glaciologist and think of myself as spending the vast majority of my time doing INSAR analysis and making these velocities that serve as inputs to your models. But this is a project that my collaborator, Mickey Mackay, and I spun up quite recently, thinking about a way that we could work together. And it's been quite fun and quite exciting. So I'm going to talk to you today about an extreme value theory perspective on large iceberg calving events. And I think that this might be piquing some of your interest. I gave a short talk about it last month or so at the Colorado Glaciology Workshop, and that's how I ended up in this room today. But hopefully you like it, and at the end you can always just tell me go back to remote sensing and making velocities. So, before I move on, well, how do I go backwards? Oh, okay. So this iceberg up here is iceberg A68. It's about the size of Delaware, a little bit bigger, and That's a pretty sizable chunk of ice. We know that these large iceberg calving events are a very dominant process of mass loss from Antarctica, the other one being melting, but it's about 50% of mass loss from the continent. And so this process of calving recently, I really like the work that Jeremy Bastis has done, as Dan brought up, thinking about calving as a stochastic process where we can think of the probability that an iceberg will detach in a given interval of time as being described by a PDF. And so the range of calving, Dan just showed this video where we worked up to 600 years, but from an observational perspective, we're really thinking about things that are happening on the orders of hours, like tiny cars falling off of cliffs, like car size ice, to something size of Delaware detaching from an ice shelf. And so recently we wrote a review paper thinking about how to visualize the scale and how we can relate these things, because the calving of these large tabular icebergs and really small icebergs as well, these are infrequent occurrences, particularly the large ones. They're very difficult to observe because we don't have a sense of the timing and the rate of these processes. And as you all well know, it's really complicated to model because of things like viscosity, right? So we can get things like these explosive disintegrations in places like Larsen B, where we lose ice rapidly in a matter of hours, to more sustained calving of iceberg in places like Thwaites, where we see kind of regular sustained growth and then detachment. And that happens kind of on the scale of meters and the temporal scale of weeks or months. But then we have these really large tabular calving events that are huge and happen very infrequently, the order of years. Something that we also kind of consider and are learning in our observational record now is that ice shelves really have a calving cycle, some sort of natural cycle where the ice shelf, much like Dan's video, will grow out over the open ocean until it can no longer sustain its weight and then loses some ice, a little bit like a cantilever. And so what we realized is that we do have decades of observations from the outcome of large calving events, otherwise known as icebergs. So this is kind of a fun data set where iceberg tracking is of great interest for oceanographers and marine biologists, shipping routes and collision avoidance and clickbait articles, right? Like this is from a BBC article tracking iceberg A68. And I feel like every time one of these large icebergs calves off, some great aunt emails me and I say, yeah, that's awesome. But this database is really amazing because it's almost 50 years of data showing iceberg positions and estimated sizes, and it's this really remarkable consolidated database. But we're not really interested in tracking the icebergs themselves. We want to identify the icebergs right when they have appeared and calved off from the ice shelf. So we're looking at the data of iceberg first date of appearance, and we can use this to predict the recurrence intervals of sudden mass loss calving events in Antarctica, guiding us towards two important questions in glaciology. I think these are kind of two questions that drive a lot of my research, where what is the timeline of a typical calving life cycle in the Antarctic ice shelves? So when these ice shelves grow, what is it, 40 years, it's 60 years? How often are they going to lose a lot of ice that no longer is serving any buttressing potential? And then maybe more pertinently, is the rate of calving increasing in Antarctica? I think that's a bit of an open question at the moment. And then really for you all, I think that Bill will talk about this next, like figuring out how to parameterize calving is a real beast. So what we did is we brought in a real statistician to help us glaciologists out to think about using extreme value analysis or extreme value theory to assess the likelihood of future high magnitude calving events. So within this database of iceberg positions and estimated sizes, there's 632 named icebergs over 48 or so years. We decided to look at the largest iceberg in every year, so long as it's greater than 400 square kilometers, which is quite sizable, but kind of sets us a threshold of what is extreme, which is really a subjective term. And so this narrows our database to 42 icebergs to look at, which for observational data isn't so bad. It's not an adaptive finite element mesh, we're looking at different scales. But what we do is we use this generalized extreme value distribution to fit our iceberg sizes This is a little bit like a Weibull distribution, if there's any real statisticians in the room. And we can look at the QQ plot, looking at the theoretical quantiles when compared with the normal distribution, and see that this doesn't fit quite as well as it would with the PP plot, looking at the theoretical cumulative probabilities and the empirical data when fit to this extreme value distribution. And so this is for the entire database. And we can use this model to look at recurrence intervals and project outwards beyond our 40 or 46 years to think about the likelihood of future high magnitude calving events and how often we would be able to see icebergs of certain sizes. So we can expect to see an A68, a Delaware-sized iceberg, every 10 years or so, this purple line. Every 5 years or so, we can expect to see something like an iceberg A76, and that's about that calved off of the Filchner ice shelf in 2021. And then, notably, the largest iceberg in our record is, I believe it's B15. I really should remember the details of this, because the other thing that we did through this project is manually validate every single largest iceberg. I'm currently updating the Wikipedia page of largest icebergs because it's incorrect. So it's a lot of brain space on this. But so the largest iceberg in our database is about 11,000 square kilometers. And so you'll notice that as we project outward beyond to a 50-year return interval or so, we get iceberg probability or an iceberg larger than we've ever seen before, but really on the order of the collapse of the Amory ice shelf front, or something kind of not really beyond the realm of probability, but beyond, or possibility, but beyond the realm of our observational history. So notably, this framework of using extreme value theory comes from or is often really used in earthquake modeling, or thinking about earthquake recurrence intervals, and flooding when we think about like 100-year or 500-year flood. And so when we model floods, flooding in Boulder is very different from flooding in places like Berkeley. So we look at quadrant A. There's a really standard nomenclature used in this database. So we just look at one area of Antarctica, which is really the Antarctic Peninsula, to see if this model fits similarly. And the parameters differ across continental and regional quadrant analysis. So all of our data is this blue line, and we can see, or all of our data is this blue line, and quadrant A is this red dashed line using a maximum likelihood estimation. And we can see that it's this tail that really changes after the 100-year recurrence interval. So the generalized extreme value model is a good fit. It's just a heavier tail, and we still have that right skew in our data that would make it appropriate to use this type of probability distribution. And so I'll wrap it up by just showing you the map of just our 42 largest icebergs and kind of where they're distributed around the continent. But other things to note is that we incorporate time as a covariate, just as a very simple linear covariate, and show that iceberg size does not increase, or iceberg sizes are not really increasing with time. We're not seeing more and more large icebergs throughout our data set. Something else that I really love to talk to some of you about, because I have never thought about the southern annular mode in my research, and someone brought this up, and we looked at monthly the southern annular mode return, and it noticeably is correlated with larger iceberg calving events. When that is positive, we see much larger icebergs. And then the parameters for this continental data set are different than regional scale parameters for quadrant A, B, C, and D. But I really think that this is a useful specific form of stochastic modeling to broaden our approach for incorporating calving into ice sheet models. I'm really an observational glaciologist, so this might be a very annoying conclusion to some of you, that this might be a fun way to incorporate calving. But yeah, it's been I think this is a really promising approach for a really complicated problem that I think deserves a lot more attention. So thank you so much for having me, and I'd be happy to take any questions. Yes.
I have people who send me those same articles, and what I was wondering is there something that could happen, some event that could happen that would surprise you and make you think this really is different from the past?
So I think what the data that we're looking at is really this type of iceberg, where it's a large block and it's really one cohesive piece. I think that things like the explosive disintegration that we saw for Larsen is the type of calving that would be so confusing, in large part because it's so wet. It's really dealing with, it feels like it's dealing with almost like a soft fluid flow process as opposed to this detachment. So that would really confuse me and make me maybe respond to my people who send me those articles. Yeah. I'll move over. Next. Great.
So our last speaker for this part of the month is Bill Lipscomb, more Calvin schemes for Calvin MIP. Did you go through the slides back? Yeah.
Was that? Is there supposed to be a light?
Yeah.
Sorry. Oh, okay. Okay, got it. Okay. So Joanna has introduced this topic, but I'm going to be approaching it from a very different point of view. I'm thinking about not individual big calving events, but calving as an average process, averaged over time scales of decades or even centuries. And is this something that we can prognose in our models? And the answer is, even though calving is a huge part of the mass balance, it's not something that modelers do very well yet. There's no calving law, sort of simple equation or approach that even allows us to reproduce steady state calving fronts in Antarctica without a lot of individual tunings to specific regions. So that's something ice sheet modelers are really interested in. And it's something that we often sweep under the rug. So for instance, this is a CESM simulation of a spin up of the Antarctic ice sheet where the ice shelves, the Ross and the Filcherani and the smaller ones are very nicely modeled. But the way we do that is with the mask. We simply say that any floating ice that goes beyond the present day extent of the calving front is forced to calve. So in that way, we get a really nice present day spin up. But then when we run into the future, probably our calving retreat is underestimated because the calving fronts tend to stay where they are since there's no physics going on to make them retreat. And that means the models are potentially too conservative in terms of how much the ice sheet could change. So there's a new model intercomparison project called Calving MIP, part of the EU Protect project with multiple phases. It's a really, really cool project, and I'm glad that it's out there because these MIPs always force you to understand and improve your model. So phase one of calving MIP is not focused on calving laws, but on the more preliminary question of calving algorithms. The idea here is that your algorithm is your numerical method. Your calving law will give you a number like what is the rate of retreat due to calving, the average rate of retreat in a given place and time. But the algorithm is the underlying numerics that enables you to model calving in a model of finite resolution. So the basic problem here is that, like, here you have a numerical model with grid cells of, say, 5 kilometers across, and here the calving front is exactly the cell boundary. Next time step, some ice will flow from here into the next cell. So far so good. But the next time step after that, ice will flow from that cell into the next cell, and pretty soon you've diffused your calving front instead of having it march, slowly along, maintaining the front. So that's what a model has to deal with, is how to maintain the front without it diffusing. And we've tried a number of things in CESM over the years. And for calving MIP, I made a few changes, and this is basically what the model looks like, the algorithm looks like now. We go through the model and we identify calving front cells, which is any grid cell that borders an open ocean cell. And we classify calving front cells as either partial or full. And a partial cell is a cell that's relatively thin, and you can define what relatively means. Relatively thin compared to its upstream interior neighbor. So this would be a cell. Let's suppose this is 300 meters in height, and let's suppose nominally the thickness in this cell is 100 meters. So we interpret that as instead of 100 meters of ice filling the whole cell, it's 300 meters of ice filling 1/3 of the cell. So that's conceptually how we think about it. And then when we're doing our transport, we have some logic that prevents ice from leaving the cell. So the result is that now we have more ice in the cell, and maybe now it's half full of ice at 300 meters. And we keep going until we fill the entire cell with 300-meter ice, and then we allow that to advance to the next cell. And then when we're doing our calving law, which gives us a lateral calving rate L, if you have L applied to 300 meters, that implies a certain rate of volume loss, and we convert that to an equivalent rate of thickness loss, and that's how the thickness, which is a state variable, how the thickness evolves. And so now calving MIP, in this first phase, there's two basic experimental domains. The first one is very simple. It's just a radially symmetric domain where you have grounded ice in orange surrounded by an ice shelf. And what you do in this experiment is you start off with your steady state ice shelf and you make it retreat, and then you make it advance again. So nothing too exciting. All the models, these 9 models plus CESM, can do this. One thing I'll notice is that CESM is not quite radially symmetric, that it's a little slower to retreat in the diagonal directions than along the X and Y axes. And so that's something I want to understand and hopefully fix. But it's not a huge problem. And so we contract, we re-advance, and all the models, as you can see, pretty much have the same behavior. So that's good. And then we go to a more complicated domain called the Thule domain. I'm not sure why it's called that, but Thule it's the former name of an Air Force base in Greenland. So I guess it has something to do with Greenland. But anyway, you have this more complicated topography where the white outline shows the outline of the grounded ice. And then you have a circular ice shelf, circular calving front around it. And you force retreat, and then you allow re-advance. So when you force retreat, this is what CESM does. This is what the other models do. If you look closely, you can see that not all the models are doing the same thing. So there are some interesting differences here. But what CESM is doing is generally similar to what the other models are doing. So that's reassuring. And then when we re-advance, likewise, what we're doing is pretty similar to what some of the other models are doing. And the re-advance, interestingly, is not the time reversal of the retreat. It actually advances in sort of a different way. But anyway, so we've contributed our results to calving MIP, and so far so good for this phase. So having improved the numerics of the model, the next question is, does this help us with modeling real calving, at least in a steady state average sense, in Antarctica? And I worked on this a couple of years ago, and due to some numerical issues, sort of put it aside, but with the improved numerics, thought it would be a good time to come back to it. And I found this paper that came out last year by Wilner et al., where they did this really nice study looking at applying 4 different calving laws to the Antarctic ice sheet and assessing the different laws. The 4 laws, one is you just say you calve when you're thinner than some threshold. That doesn't work too well because calving fronts have all different thickness thresholds. So thickness is not the only thing explaining why a calving front is where it is. Then there's some complicated things involving crevasse depth, which I'll skip over. And then the 2 laws that perform best in this study were an eigencalving law and what I'll call a stress threshold law, where the eigencalving law is you take the eigenvalues of the horizontal strain rate tensor, and you have an along flow eigenvalue and a cross flow eigenvalue that represent tensile stresses in the direction of flow and across the flow. And if both of those are positive, you can multiply them together and get some number, and you multiply that number by a constant. And the idea that's been around for about 10 years, originally implemented in the PIC model, is that should tell you your calving rate. And then this other idea, which is sort of similar but different, is you have a sigma represents some function of this horizontal stress tensor, and you have a threshold. And if sigma is equal to the threshold, it turns out that the lateral calving rate is exactly balancing your velocity out to sea, and you have a steady state. Otherwise, you have advance or retreat. So it's this stress threshold is determining where the calving front is. And in this paper, they applied these different laws, and eigencalving works really well for the Ross ice shelf. But then for Ronnie and Filchner, these are the calving fronts you get from different laws, and you can see they're kind of all over the place. So one law in this study, one law does better in one shelf, another law does better in another shelf. And so I implemented the eigencalving law and a variant of the stress threshold law in CESM just to see what would happen. Eigencalving here on the left, floating ice in yellow, and you can see it's quite messy. You get these tendrils of ice, West Antarctic Peninsula, here in the Get Shelf, all over East Antarctica. The basic problem is, I think, is that you only have calving when both of the eigenvalues of the strain rate tensor are positive. And so if one of them is negative, typically the across flow, you don't get any calving, and so the ice can just advance. So then I tried the stress threshold approach, and it's tunable. So I tried one tuning value that didn't work so well, and then I tried a different tuning value, and it actually works quite well. So you can see, for example, not only do you get the big ice shelves pretty well, Amory and Larson as well, but the small ice shelves have fairly reasonable calving fronts. The caveat here is that I am, in this case, basically tuning the temperatures so that the thickness of the Ross ice shelf is correct all the way out to the calving front. But then beyond the calving front, nothing is tuned. So the only way to get rid of the ice beyond the calving front is by calving or melting it. And it does calve in about the right place, which is cool. One caveat is in this simulation, after 1,000 years, Thwaites is in the process of collapsing. I think that's an artifact of the spin-up procedure we've chosen. But that's something to be investigated, because obviously we want to spin up to a steady state where Thwaites is there and rather than not there. So just to summarize, we've developed a new numerical approach or calving algorithm that allowed us to participate in calving MIP, and the model does quite well, we think. And given this new algorithm, we're now in a good position to test a number of calving laws. And this is still very early days, but we found a calving law that seems to work quite well out of the box. And with some further tuning, we hope we can apply it to Antarctica. And then when we're doing longer term simulations up to paleo timescales, the hope is that we have a relatively simple calving law that gives relatively realistic calving fronts so that shelves will respond in a physically realistic way to variations in climate. And the code is there, and hopefully these things will be sufficiently well validated that we'll feel comfortable releasing them in CESM 3 and CESM 3. Thank you.
I'm curious if this might be I don't know if you'll remember this, but what values of the stress threshold you used, or what value? And then,
well, for the stress threshold, I used 50,000 pascals for this experiment.
Did you play around with higher or lower?
I was just doing this over the weekend. So,
okay. So,
but what I think is, well, so that's something I want to play with. Do you have a value you think is the right value?
maybe. I have a few ideas. That'd be fun.
Okay, let's talk afterward, because maybe it should be higher. But the other thing in this function is how you weight the along flow versus the across flow stresses. And what I showed gives more heavy weighting to the across flow, but a non-zero weighting to the along flow. And that seems to work. But there's a lot of other functions one could try, and if something goes wrong in a particular place, you try to see if another function works better for that place without messing things up where it was working well. Yeah, Dan.
I just want to comment that a spin up with an unstable Thwaites isn't necessarily wrong.
Correct.
I mean,
yeah,
we spent too much time forcing ourselves into steady state initial conditions that are maybe
and the particular spin up technique was one that we've used in previous papers that did specific things for thwaites. And I don't want to go into the details, but it may be those specific things we were doing for thwaites are not a good thing to do in this. So we can do I think what I'd like to do next is use the steady state procedure that Gunter has been working on with Mira for pre-industrial spin up.
There is a question online from Adam. He said, "Hey Bill, nice talk. Could you comment on whether a particular calving algorithm might be more appropriate for calving glaciers that don't have a floating shelf?"
Calving algorithm or calving law?
Calving algorithm. Oh,
Okay.
law, he said.
Okay. Probably yes. And I haven't thought about that yet. And I'd be happy to hear some suggestions. I'll just mention for Greenland, we have a very simple calving law for Greenland and CESM, which is we simply say there are no ice shelves. As soon as the ice starts to float, we remove it. And so one hope would be that with a good calving law tuned appropriately for Greenland, we could actually allow Greenland to have shelves but not get too many shelves. But that's a fjord setting, which is more like terminal calving glaciers as opposed to an open ocean setting like Antarctica. Yep. All done?
So we have a second half of the session later, so more on Antarctica, on Greenland, paleo ice sheets, and glaciers. And maybe a second round of applauses for all of the speakers. See you after the break.
Well, welcome to my presentation. I'm sorry I couldn't be there at Ingvar to give this presentation at the CESM workshop, but I was allowed to give a pre-recorded talk, so bear with me, and I'm happy to share my thoughts and hopefully get some input from you as well at this point. So my name is Tim van den Akker, and I work with YouTube University together with Bill. So I'm using CESM, the community ice sheet model, as a standalone ice sheet model to model the Antarctic ice sheet. I use, so for the experts among you, I use DIVA approximation, I use for stress balance, 4 kilometer resolution, and ISMIP 6 style simulations. I initialize the model with the observed mass change rates. We can talk more about how to do it, or I can give you the paper where we present this later if you like. And I specifically focus on future runs, so 10 to 2,000 to 2,000 years into the future, and I'm very much concerned with the Western Arctic ice sheet stability or potential collapse that might happen. So in the previous study, what we did is we initialized the community ice sheet model with the observed mass change rates on the right. So you can see the observations from Smithsonian 2020, where you can see that there's quite large skimming rates in the Arctic Sea area happening. And the rest of the Antarctic ice sheet is a little bit like spectrum blue and red. On the left, you can see our continuation run for 1,000 years. If you just initialize with the present day mass change rate, so you can see that there is a quite a significant collapse of the Western Arctic ice sheet happening in that case. And of course, we tested this. We did a sensitivity analysis on to see like does this Western Arctic ice sheet collapse happens all the time when you initialize with present day mass change rates? And the answer is yes. So the upper graph here shows every simulation with sea level rise on the axis and ice mountain flotation percentage of waste of Pine Island in this case on the y-axis. And we can see that for all we did a lot of sensitivity testing for all of those tests. The Western Arctic ice sheet collapses. However, the red lines show the runs where we vary their basal friction parameterization. And as you can see, there's little uncertainty associated with the basal friction parameterization. We were quite positive because there are a lot of people that actually say that if you implement the basal friction law, it gives you more friction, you should get a larger sea level rise rate or a larger sea level increase. Now, why is this? Why does basal friction not happen? And I'm going to try to convince you today that this is caused by the buttressing that happens during the collapse. So consider a glacier. In this case, well, you see the pictures already. This is Thwaites, the big one, and the small one on top here is Pine Island. Buttressing and basal friction are basically two main opposing forces for an ice sheet for a glacier to flow into the ocean. So buttressing opposes it and basal friction opposes it. Now, saying that there is less basal friction, that means that the ice will get initially speed up, so more ice will be through the ground line, through the shelf, forming quite a thick shelf. Well, as soon as the shelf is thick enough, it gives you more buttressing. So this is which limits the upstream flow of the glacier again. So these are kind of opposing feedbacks, and using a basal friction parameterization gives you more friction, gives you a larger shelf, and therefore more buttressing, has this compensating effect in it. Only if the shelf actually is able to give you some buttressing. And as you can see in these figures already, we can see on the left regularized block sliding, which gives typically less friction. Parallel sliding, you see that the plane starts to collapse already. It is 500 years into the future. This is the thickness differences with the beginning of the run. You can see this funnel-like structure of the grounding line. So there is kind of a confined bay in which this shelf can form and start to buttress the upstream flow. Is this quantifiable? Yes, it is. So we can either choose to do this through the buttressing number, where you compare the stress balance at the grounding line or at a certain point in your ice shelf to the caudal foot, then you see if there is buttressing or not. Or you can basically just in every situation, like kill all the shelves and see if the grounding ice upstream starts to accelerate. And I tried both, and both methods basically give me the same answer. If you're using more friction, you get a weaker shelf. If you're using less friction, so parameterization allows for faster speed up of your ice, you get a stronger shelf. And the weaker and stronger shelf and the more and less friction, they compensate each other. And this is likely why we don't see much of a difference if you apply these methods. So then we started to you ask yourself if this feedback is always there. So, and the answer is no. So if you see the graph down here, this is again the western ice sheet collapse in sea level rise on the left y-axis, and the volume of flotation percentage on the right. And you can see that for the dashed lines, there is clearly an effect of beta friction. So here we use the green and the black line use the gravitation that allows for less friction, and the blue and the red allow for more friction. And you can see that this is kind of what you expect. Because for friction, your ice sheet starts to slow down. There's slower mass change rate. But this kind of counters what I just told you, that there is the friction buttressing effect. So why is this not happening in this case? Well, this is because in the new spin-up that I just showed you, we initialize also the flow factor. So we do a different initialization to get kind of to the same shape but with different assumptions. And the idea is the advantage of this run is that we tune for surface velocities as well, so this gives us a better velocity fit of the ice sheet. However, the disadvantage is that we have one more free parameter, three parameters instead of two. And we might get the right answer for the wrong reasons. So in this run, the weight is more stable because in this figure on the left, you can see the softness of the ice, and eastern weight is completely black, meaning that the ice is very stiff at this point. And the rest of the western weight is quite soft, and especially Pine Island is super soft in this run. And the friction, which you can see on the right, gets a large blue block, which is an area of super high friction on western plates. So eastern plates gets more stiff, western plates gets more friction. So the whole system of plates glacier is much more stable in this run than in the other run. So what we conclude through that is that basic friction and buttress cancel each other out. There's only in certain geometries that allow significant buttress, like this funnel structure of plates retreating. So if you have another shape of your collapse, it's possibly with the more stable plates, and in the other simulation, Pine Island actually goes first and draws plates with it, then you don't have this potential for buttress increase. But the future geometry depends on the initialized state. Therefore, the sensitivity to basic friction parameterizations is determined by your initial state. With that, I want to close off. I want to thank you for your attention. If you have any thoughts or want to talk, please send me an email.
That's great. Thank you, Tim. So yeah, we won't be able to take any questions for him right now, but if you have questions, I'm sure you can email him. Our next talk is also online. Is CG1 online?
Here.
Oh, never mind. Okay. Well,
Let's see. Okay, well, so let's see. This is how I move. No, I just want to move forward. Yes, okay, yeah. Okay, well, I guess today I'd like to talk a little bit about this new tool that we've been building for modeling glacial isostatic adjustment problems. And so I guess what you see here is, of course, is really the landscape in Hudson Bay where you actually see the raised beaches, right? And so the GIA problem is what we call the glacial isostatic adjustment problem. Is actually quite simple. That is, following ice melt, the land will rebound, right? And then the melt water will flow to the ocean that actually cause additional burden or load to seafloor that causes subsidence for the seafloor, right? And so this whole process is really what we call the glacial isostatic adjustment problem. It turns out that, of course, for this particular session, there's this understanding that the GIA process actually may play a very important role for the ice sheet dynamics. I guess in the sense that the GIA process may actually influence grounding line migration and also affect the sea level. So the sea level is, the sea level overall is important for the ice sheet dynamics. I guess Gunter and Bill, we've been talking about possibly, couple, some of the GIA softwares or models together with with ice sheet dynamics. So that's really sort of the background for my presentation. And so now let's actually first look at a little bit about the GIA in terms of formulation. So basically, we're trying to understand the solid Earth response and to the ice melt on the surface. So this is what we actually call the loading problems. The kind of governing equation is, of course, we have to treat the solid Earth, as some kind of viscoelastic medium. And so you, let's see if I can get, okay. No, a point here. Okay, well, no, it's not what I want. And so anyway, you actually see the governing equation for compressible medium. So basically, the second equation there is equation of motion. Okay, so it's really deformation for the solid Earth. Then, of course, we have to deal with the gravitational potential, which controls the sea level, right? So that's the third equation, essentially Poisson's equation. And then, of course, the Earth medium, when you sort of with deformation, the Earth medium actually will deform and will actually will have this we call the divergency, the volume change. That of course actually change the density, and the density will actually influence the gravity, right? And then this viscoelastic material. So you would treat the Earth mantle, let's say, as a viscoelastic medium. So it's a fluid and also solid, right? So it got a viscosity, got an elasticity. And so that's actually, we treat, essentially Maxwell body. And then we have a load that is essentially ice load, right, on the surface. Now, if you have the mantle viscosity, it turns out to be very important parameter actually control this is the Earth, solid Earth, response. And then, of course, we cannot really, know for sure for the mantle viscosity. Whereas we can actually study by looking at the elastic waves, how the elastic or seismic waves traveling through the Earth's interior to like doing some kind of imaging for the Earth's interior. So you actually can see the Earth's interior, in this case, the Antarctic, right? And there's a tremendous amount of horizontal variations in elastic in elastic properties. And this is essentially the shear wave speed that are traveling through the Earth. You really see this at this particular 300 kilometer depth. There's a very big lateral variations in the shear wave speed, and so this actually probably imply significant variations in temperature and therefore viscosities. And so there's of course there are other kind of viscosity properties that we know, and that is you look at solid Earth. We know we call the lithospherical thickness variations. Going from mid-ocean ridge system to seafloor of old age, and the thickness of the lithosphere can vary significantly in the horizontal directions. And so it's really this kind of 3D mantle viscosity that will demand numerical method to solve the equations I showed to you at the beginning. Okay, right? And so now look at the rheology, and this is I already showed this to you, and this is a compressible Maxwell rheology. And then where we deal with this, really, we kind of really treat this problem as viscous and elastic part. And so the total deformation can be partitioned into these two parts, right? And then you can, in the numerical sense, you take this, you take this rheology, you discretize this in time, and so you end up with this new rheological equation, and then there's a so-called pre-stress term, and this is essentially record the history of deformation. Okay, right? And so, and then because of this, we have to really use, this Lagrangian kind of formulation where we let the grids to deform with time. Okay, and so then of course you put this into, in this case, we put this into this finite element formulation, right? And so then you end up with a big matrix equation you have to solve. Okay, right? And so then here we actually borrow numerical techniques we used in solving mantle convection problem in the past. It's a code that I kind of developed with others. It's called SIGCON-S. And so, and then of course we actually use, this is the global model. So this is how we actually, the kind of grids we, designed. And then of course you can further divide into many even smaller blocks. So you actually, so then you can put this into parallel, computers, right? And so that's essentially what we do here. This is, now, I just want to quickly talk a little bit about how this actually method or this code actually got developed over the years. And first, this is really start with convection code. And so this is SIGCON S. And then we actually, then over the years, we kind of put the viscoelasticity into this. The convection code, of course, viscous fluid, right? And then we put the, viscoelasticity into this. So we kind of add all these functionalities that deal with the GIA problems. And then this actually code can also, global and can also be on the regional scales. And we actually use this to model volcanic loading for places like Hawaiian Island, volcano loading. And then this also can be used for to study the tidal and the rotational loading problems as well, and to study the shape of planet. And so here just kind of quickly show you, in the last few years, we actually really try to improve the parallel efficiency. And this has been running this, this is actually done on Yellowstone, the Inca supercomputer Yellowstone. And so now you can sort of see this is really up to 6,000 cores, and got a very good parallel efficiency, right? And so, now there are, so I want to quickly talk about some of the key features in this. This is actually version 3.0, and so this is a fine element, package for modeling dynamic deformation of 3D spherical shell in response to surface and tidal loading. Okay, and then we use various rheology for the mantle that is stress temperature dependent. Then you can either compressible, median, or incompressible. And we use this this non-Gaussian Lagrangian grids, and that actually tend to give you more or less uniform coverage. You can avoid this kind of pole, the problems near the pole, right? So, and then this is I already showed you the parallel efficiency, and this is open source with user's guide. You actually can access this code or this package, from GitHub. And then we actually this summer it's not over yet, and we're actually still planning to do some Zoom workshops in terms of training. So now I just want to quickly show you some of the accuracy or the benchmarks, and this is the love number is something that for simple models like one-dimensional Earth, we actually can calculate this analytically or semi-analytically, okay? And this is actually represented here as the dashed lines here. And this is actually showing the love number, evolution of love number with time for different spherical harmonics, and 3, 1, 2, 0. This is a different harmonic degree and order. And so in most cases, you can actually see the solution is very, very accurate, okay? So we actually do an error analysis. We plot, the relative error versus grid spacing, right? So so you actually can see, indeed, you look at the slope here is about a 2. So it's really saying that this is second order accurate, okay? And now this is doing the actual I6G. I6G is one of the popular ICE model, right? Developed by Dick Pautier and his colleagues. And so this is really applied I6G onto the, using this code, and you also see the analytic solution here is the red dashed line, and for different harmonics, really is very accurate, okay? And so this is the final slice, I believe. And basically, I just kind of, I show you this slice already. This is the key features of this package. So if you have any questions, I'll feel free to ask. Yeah, thank you.
Are there any questions? So this may be a naive question, but I could see this having some interesting science applications if coupled with CESM. Would you have any thoughts about trying to couple a GIA model to CESM in the future?
Well, that would be nice. we, I guess we certainly, very much open, to this idea. And so I can see, in terms of finite formulations, they're really quite similar. The way we deal with the Earth's mantle, and I guess how Bill and Gunter's, the finite models deal with the ice sheet dynamics. There are a lot of similarities, so we'll have to see. Yeah.
I have some thoughts. All right. Thank you very much.
Sure.
No, it's all good. So next up is CG1 Cat.
Okay, thank you very much for giving me this chance to talk about my recent work with my advisor, my mentor Thorsten Becker and Jeremy Trevega. Now, today I will talk about how follow Shiji's line, continue to talk about how the GI model with the non-Newtonian rheology in the upper mantle can affect the Antarctic ice sheet flux. So, okay, first I want to talk about a little bit how the GI model can give the prediction may be more important for the marine-based ice sheet evolution, and how this can affect the ice sheet evolution and the sea level projection, for example. As Shiji already mentioned, in the intermediate timescales, now we talk about tens of thousand years, these time scales, the Earth, the mantle can be treated as the viscoelastic material. So this basically means, for example, show here, when the ice shrinks, the surface loads forcing to the solid Earth will be decreased. This will trigger the viscous mantle flow towards the region underneath the former ice sheet, like shown here, and this will cause the bedrock uplift underneath the former ice sheet and sea level subsidence beyond the ice sheet. And for the marine-based ice sheet, the grounding line migration will add more complexity for the whole model. And in this part, we can see the GI model can give us a very good prediction for the bedrock topography and the sea level bathymetry variations with time. And on the other side, the huge amount of the ice melted, now the water will flow into the ocean. So how those amount of the water will distributed onto the ocean. As she just said, this is not a very simple geometry problem. There is a physical process here, because the surface, the ocean surface will always follow a geopotential surface. So if there's any gravitational force and changes around those ocean surface, and then the sea surface will adjust according to this physical process. And the GI model can also predict those kind of sea surface adjustment. I will give more details how the GI model handle this gravitational self-consistent ocean. Now we need to solve these sea level equations I showed here. So if we observe this very simple equation, we can see two kind of different variables. One is this little c here. We can see this little c, there's no dependence on location. It only depends on time. So this is basically a global constant value. We can get some idea from the left panel I show. So for example, from A to B, the ice sheet will shrink, and those amount of water will flow into the ocean, and we can see a universal sea level rise will occur. This is eustatic sea level. We call it eustatic sea level, and this is little c can give us a very I think we can call it zero order approximation for the sea level change caused by those ice shakes. And for the second order, for the first order corrections to this uniform sea level rise, we need to consider this physical process caused by this gravitational self-consistent ocean, which I show the frame C. So we can see the real sea level will departure from the eustatic sea level. Nearby this shoreline, we observe a sea level drop, and this is basically caused by the deduction of the gravitational attraction from the former ice sheet. And then if we go further from this nearby side, and we observe less and less sea level drop, and at one point there's no sea level change, and beyond this point we observe the sea level rise in the far field. So from here, I can just we can just argue why the GIA model need the global. I mean this solve the sea level equation globally, because this ocean, because this sea level equation, we need to consider not only the near side, we also need to consider the far side, the ocean loads. So so the GIA model is very expensive because the global computation. And now for the model setup, we still use I6G, includes both the glaciation time period and deglaciation period. And we need to include both the northern hemisphere and the southern hemisphere. So how those ice mass variations from 122,000 years ago to present day. And so the last panel is a video show, but I know how to press, how to, sorry. Oh, I'm so sorry. How to restart? Okay, I go backward. Lower bar. Okay, sorry. So how can I play this video here? Maybe I just pass this. Oh, good. So we can observe in I6G, the grades very coarse. It's 1 by 1 degree, and in Antarctica we can observe multiple ice advance and ice retreats in the glaciation history to LGM, and I observe a very roughly stable period from LGM to around 10,000 years ago. And then after 10,000 years ago, those ice shelf starts to retreat to 4,000 years ago. And in I6G, there's no more change since 4,000 years ago. So typically the I6G only, I think they didn't include any modern ice flux in this ice model. And for the model setup, we also need the initial topography. Theoretically, we have no idea about those initial topography at 122,000 years ago. So we need a good guess. What we're doing here is we just simply took the present day topography models I showed here. One is the global topography and bathymetry model, and then we just replace the Antarctica part with a better topography model with BADMAP2. We use this initial topography, and then we do the GIA model, and we can predict the topography variation at each time steps. And then after we got the relative sea level variations, and then we can use those relative sea level variations to further update those first guess until after several iterations, we can get a good convergency. And you can see the original topography model, the spatial resolution is very good. So about 4 kilometers or just 1 kilometer for BATMAP 2. But in my model, model, because the ISIC-G I used is still very coarse, it's 1 degree by 1 degree. So here I have to sacrifice those kind of high resolution for topography. So what I did here is I just interpolate, just reduce the spatial resolution and interpolate them to 1 by 1 degree, and then continue to my GI model. And I think this is what Shiji already told us. Our different people, different GI people, they use different viscosity profiles. The very simple and the basic profile we use is this 1D viscosity model I showed for on the left panel. And you can see they differ a lot from each other. And also they include different multiple layers. What I showed here is the interesting thing is they show on the right for the different color, they show different sides of the ice sheet and how those different sides of the ice sheet can be sensitive to different depths of the viscosity profiles. For example, for the Antarctica ice sheet, the sides of the post-glacial rebound, the half wavelength is very similar to the Fennoscandia ice sheet. So we can say they're more sensitive to the upper mantle, upper mantle. So we need in theory, we need a better viscosity profile for the upper mantle. But for the lower mantle, maybe they cannot be very sensitive to that kind of parts. And we can also include 3D and Newtonian and non-Newtonian rheology in this part in the model. And as she just said, the sitcom SVE can handle all of those different viscosity models, will give us very good predictions. And here I show the redshift sea level predictions by 3D Newtonian and non-Newtonian GI model. What I want to point out 2 points from this simulation. One is, you can say, when we compare the 3D Newtonian and the 3D non-Newtonian redshift sea level pattern, we can say it's very similar. So the spatial distribution is very similar. So, but if we compare the change of the rate, which I show the difference in the last column, we can say before and after 8,000 years ago, there is a sign flipper we can find. For example, before 8,000 years ago, the non-Newtonian rheology can get will be larger than the Newtonian predictions. But after 8,000 years ago, the Newtonian prediction will be smaller than the non-Newtonian rheology. So this gives us idea that if we use non-Newtonian rheology, the redshift sea level predictions, the process will be much faster than the Newtonian rheology. And also, I want to point out I also give a map of the ice model change on the very left. And you can say the ice model is our source and we're forcing, and all of the 3 panels is our response. The Earth response is our results. So if you compare this spatial pattern, I would say the GIA prediction they're smoother than the source. This is basically because the elastic lithosphere, they just work as a filter. They filter out some kind of the very localized ice variations. So give us a little bit long wavelength of the redshift sea level predictions. And I would skip this one because this is, I think I already talk about in the same conclusion can get from the time series, the time variations comparisons. So I will just skip this one and go to my last slides here. Is what the model resolution I used right now and what's the problem I have, and maybe future collaboration with CESM. So now I use, as I said, I used a very long ice model 1 by 1 degree. We have better high resolution topography, but because of the limitation of the ice model resolution, we have to sacrifice the bedrock topography. For example, here from 1 by 1 I6G model, we predict the grounding and floating ice mask at different time steps, and we can say the resolution. We cannot use this to do any future study for the marine ice sheet instability. So what I'm going to do is to try to run high resolution GI model around 10 kilometers or less, and then the grounding line solution is basically a post-process. So when I run GI model, and we can predict the topography variations, and then use this to through post-process and give the grounding line migration. We can separate this to, we can do experiments to separate the GIA modeling and the grounding line migration resolution. So one is the processing and one is post-processing. And for this, with this high resolution, we want to further explore how predicted grounding line migration can further affect the marine ice sheet instability and the sea level projection. So I will stop here. Sorry, I just started late. Sorry, I'm happy to take any question if you still have time.
Actually, we might have time for questions
Okay.
right now, but people can find you at lunch break.
Okay,
So thank you very
good.
much.
Mhm.
I am next. Okay, I'm going to present a work here on the surface mass balance of the Northern Hemisphere ice sheet during the LGM. And the last glacial maximum is a period that is centered around 21,000 years ago. And at that time, sea level was 120 meters lower than today. We had an ice sheet over North America that was as big as present-day Antarctica. The idea here is that we can apply, or our idea was to apply CESM that had an advanced calculation of surface mass balance to a period different than present day and future. So this LGM is a great opportunity. And we are going to compare ice sheets with each other within the Northern Hemisphere and also with present-day ice sheets to learn a little bit how snowfall and melt play roles for the different ice sheets. Okay. However, so we are using CESM at the standard 1 degree resolution for CMIP simulations. And we are downscaling the SMB to a 4 kilometer grid product. However, CAM6 was replaced by CAM5 due to high climate sensitivity that was giving us too much cooling for the LGM period. Okay, so it is a non-standard CSM2 version, what we are looking at here. So we design the boundary conditions and the forcing following PMIP, so the Paleo MIP. So the same as other studies for the LGM, but we did two things different. So our reconstruction was based on glass 1D for North America, and the reconstruction for the ice sheets, because we are running here fixed topography, we are not running the ice sheet model. So for Eurasian ice sheets, It was from British Chrono. And we did also something for vegetation. So for the high latitudes, high mid latitudes of the Northern Hemisphere, Michele Petrini was, okay. So replacing the present day vegetation map by one that he obtained by running this biome with a forcing from our cold climate of CESM for the LGM. Okay, so you see this blue line. So north of that blue line, we were taking what biome was giving us, so to say cold vegetation, and in the rest of the planet we left it as present day, so as not to mess up too much. Okay, so we get a cooling for, and we performed 2 simulations, one corresponding to 21K and another to 26K, that is a colder period for comparison, so to see some sensitivity to extra cooling for the SMB. Okay, so if we, I'm going to focus for most of it on 21K. So we get a cooling of close to 7 Kelvin with respect to pre-industrial. This is within the reconstructions that we have. And it was 8 Kelvin for the case of 26K. So the largest cooling, we are looking here at winter and summer, is over the ice sheets because of the very high elevation that we have there compared to pre-industrial, and also because of the high albedo, of course. So now if we are looking at incoming radiation during the summer over the Northern Hemisphere ice sheets, we have at the top of the atmosphere less radiation coming, so this is the blue. However, at the surface, we get more than in pre-industrial because the sky is has less clouds. So more is reaching the surface. So this is kind of a paradox. But then when we are looking to the net radiation, including the albedo, if we are looking at the area, now, so if we are looking here at the summer and over the ice sheet area, so then we have blue because we have this high albedo. So the net input of solar is much lower than pre-industrial. Here we are comparing again to pre-industrial. So so we have more radiation and more solar incoming radiation over the ice sheets. So this here, it is largely due to the cloud cover, to the cloud forcing. So there are less cloud forcing, so to say. So we get extra radiation, and also, except in the margin of the ice sheet. So because we have the margin, then we have like more cloudiness than industrial there. However, this is compensated by the high reflectivity of the surface that give us multiple scattering. So then we get some extra incoming radiation. So several things playing here. But for incoming long wave, we get much less because we have a much higher elevation of the ice sheet, so much, and the climate is overall colder. So, so we have this strong reduction in the incoming long wave. Okay, moving to the surface mass balance. So we are gonna use numbers of the surface mass balance, and we are gonna divide them by the area of the ice sheets, so to scale them and compare one ice sheet with each other, no? Regardless of the size. And we are gonna use 2 lines also for the present day values scaled by area for Greenland and Antarctica. So we see where we are moving. So we're going to go component by component of the SMB surface mass balance, focusing on the snowfall and the melt. So if we look at the snowfall, so we are going to have 2 ice sheets that are very dry. So this is the Greenland ice sheet, and the other one is the Barentskara ice sheet. So here and here, very low snowfall. So the accumulation over Greenland is half than present day at the LGM. And we have other ice sheets that have very high snowfall, like the British Irish ice sheet and the Icelandic ice heads. And if we look at North America, so the average snowfall has to take into account areas that have very, very high snowfall with others in the interior, high elevation that are super dry, like the interior of Antarctica today. But altogether give us an average that is in between the snowfall of Greenland today and the snowfall of Antarctica today, or the other way around, between Antarctica and Greenland. Okay, now looking at melt, Greenland doesn't melt, zero, almost zero at the LGM. And in the Barents Kara ice sheet, that is this marine ice sheet there in the Arctic, sorry. So here, no melt. And then we have a lot of melt for the British ice sheet. And I'm looking all the time to the blue bar that corresponds to 21K. Okay, the other one is for 26K. So now we put things together and we are gonna get a lot of refacing around the equilibrium line altitude of the ice sheets. Okay, so now if we go to the SMB, so we get for the Greenland and Barents ice sheet a similar SMB as present day Greenland ice sheet. So for Greenland is funny because we have the compensating effects that we have half the accumulation at the LGM, but we don't have any melt. So altogether, the SMB is the same as present day. Okay, so and this is the map that we are getting. And if we compare with 26K, for 26K, we are going to have in general less snowfall, but also less melt because it is a colder, drier period. Okay, so this results in higher SMB for some of the ice sheets, but in others where the snowfall is very high, like the ice line, which one is that? So for instance, for the Scandi, no, not for this one. So yeah, for those, there are a couple where it is the other way around, so we have lower SMB. So it depends on the interplay between the snowfall reduction and the melt reduction. Okay, so now looking at the energy sources for the melt that we are simulating. So we are going to look at radiation and the sensible and latent heat fluxes. So for the incoming, we saw that already. So the margins of the ice sheet are relatively cloudy. So we have minimum incoming solar there, and it is we have the maximum in the interior of the ice sheet. And this is what we have today for Greenland. So if we go to the interior of Greenland, this is the sunniest place in the summer. So it's covered by clouds, but they are very thin. So it's the solar incoming is maximum. So for the long wave, there is a high dependency with elevation of so how warm it is and how much incoming long wave. Yeah. And now for incoming short wave, we have to look to the albedo very carefully. And so, for instance, in the margins, all the margins of the Laurentide, except the northern margin, we simulate very low albedos that correspond to early exposure of the ice. So this is why we have so much energy for melt there. In some other areas, so for instance, in the Barents Kara ice sheet, that is so-called, the albedo is extremely high. So we have no melt at all there, and very low temperature. So we have maximum sensible and latent heat flux in the margin. Sorry for the color code, it should be the opposite. So we have inputs of energy along the margins of some of the ice sheets, the southern margin. Okay, so in conclusion, this is the map for the SMB that we get when it is downscaled to 4 kilometers. A next step would be to evaluate how this SMB relates to to elevation. No? So we are having very wide ablation areas here with a very high amount of melt. And the next step is to see how this relate to the elevation distribution that we are using here. Yeah, thank you very much. I can take questions.
I think we have time for one quick question, if there's any out here.
If not later.
I have. Yeah, should we go? Okay. So your study seems to be very sensitive to clouds and radiation, and you chose CAM5 for your atmosphere because of the climate sensitivity. What features would you like to see in CAM7 that might make it more useful for paleo applications? Would you like to see a lower climate sensitivity or an option for?
So, so the model is already running for the LGM, and it is doing well, yeah, for the climate. So, yeah, we're happy with the results.
Okay,
yeah,
yes. Okay, so next up we have Taylor.
Hi, everyone. My name's Taylor. I work with Clay Tabor at the University of Connecticut. I'm a PhD student. And today I'm going to be talking about modeling the Antarctic ice sheet and its contribution to Pliocene sea level. So a bit of background for those that might not be familiar with the time period. The Pliocene spans about 5.3 to 2.6 million years ago, and it serves as a potential analog for future climate. So we're going to be focusing particularly on the mid-Pliocene at about 3.2 MA. So uncertainties in sea level are quite high during the Pliocene. And this can be partially attributed to the relationship between the delta 18O of Antarctic ice to benthic, the delta 18O benthic foraminifera. It can also be quite difficult to deconvolve the contributions from deep ocean temperature and global ice volume. So that brings me to the motivation between this project, which is how do uncertain ice sheet parameters affect sea level estimates during this time, and how may our models account for this? So to do this, we are using a fully coupled water isotope tracer-enabled or system model and a climate emulator to force a ice sheet model. And we will also be forcing this ice sheet model with bias-corrected isotope-enabled community Earth system model output fields. So our climate emulator is based on that of Holden et al. This allows us to reduce computational expenses and also construct long-term continuous predictions of climate trends during the Pliocene. So the emulator is calibrated with temperature and precipitation model outputs from ICSM. So for our ensemble input file design, we have both varying orbital and CO2 parameters. And we're also using singular value decomposition to construct our emulator. And this allows us to rotate our data onto a new coordinate system where our components or our new coordinates are principal components. And these PCs allow us to capture nonlinear patterns of climate. And yeah, the type of emulator we're using is a Gaussian process emulator. And this allows us to quantify uncertainties of our emulator. Okay, so we're also using or applying an emulator time series forcing from Holden et al. So orbital forcings are taken from a previous study. And then the carbon dioxide forcing is also from a previous study from Staub et al. And they use oxygen isotopes and inverse modeling to derive CO2 concentrations. So to generate our ICSM experiments, we're using Latin hypercube sampling, and this allows us to generate both orbital and CO2 configurations from a multidimensional distribution. So I have our parameters here. So we have eccentricity times the sign of precession and the eccentricity of cosine, eccentricity times cosine of precession and obliquity. And the ranges from these were also derived from previous studies. And a linear combination of these three orbital terms approximates insolation, so that's why those were used. And then here we also have the natural log of CO2, so we can sample the radiative forcing directly. And this range was primarily derived from boron proxies. So we branched our Pliocene experiments, and we have a total of 40 Pliocene experiments. Previous studies suggest using 10 principal components per input parameter or climate variables. So in our case, 3 orbital parameters and 1 CO2 parameter gives us a total of 40 Pliocene experiments. So we branched our Pliocene experiments off a default PlioMIP configuration, which has 400 parts per meter of CO2. So the climate model we're using is ICSM, and our simulations have a 1.9 by 2.5 degree resolution for the atmosphere and land, and a 1 degree resolution for the sea ice and ocean components. So we have our 40 Pliocene experiments, which were each run for 500 years. And then next up, the ice sheet model we're using is PSU. So PSU is a 3-dimensional thermomechanical ice sheet model, and it contains vertically averaged ice velocities in a column. And this model includes both marine ice sheet instability and marine cliff instability processes. So our topography, monthly total precipitation, monthly surface temperature, and annual ocean outputs from ICSM were used to force PSU. So the ice sheet topography is initialized from a modern bed map, modern observed bed map configuration. And then we interpolate our climate model fields onto the ice sheet model grid using bilinear spatial interpolation. And differences between our interpolated surface elevations in our SESM model and the PSU model are accounted for using temperature and precipitation lapse rate corrections. So our bias corrections are calculated using differences between a modern ICSM 3.1 simulation and also interpolated World Ocean Atlas and modern observed ERA5 data. And then here are just some sample outputs of surface elevation at the mid-Pliocene. So we varied a couple of parameters, Cliffy max, which is the max erosion rate for ice cliffs exceeding 100 meters, and also Cav Lick, which is the scaling depth for the deepening of surface crevasses caused by hydrofracturing. So we're showing outputs from both our bias-corrected ICSM climate used to force the ice sheet model and our raw ICSM 1.2 climate used to force the ice sheet model. And here we can see that a greater maximum erosion rate produces a greater or a lower surface elevation compared to 3 kilometers per year, which is the default maximum ice cliff erosion rate. And we also have a lower surface elevation for our bias corrected climate in comparison to raw climate. And I didn't show the outputs here, but the bias corrected climate and the greater maximum ice cliff erosion rate both do produce greater sea levels as we would expect. So next, moving on to our transient simulations. So forcing our ice sheet model with the emulator. Here I just chose 2 samples of when the ice sheet was at a minimum ice thickness at our minimum ice sheet extent at 4.237 MA, and also an example of when it was at its max ice sheet thickness, one of its max ice sheet thicknesses or extent at 4.016 MA. And so, and then to the left, we have our Holden et al. Forcing parameters. So here we can see that primarily this ice sheet extent is driven by higher eccentricities that modulate the precession and also higher obliquities or tilt. And CO2 here for these 2 times is too small of a signal to really affect it relative to our orbital parameters. And so then to the right here, we have anomalies of surface temperature and precipitation and ocean temperature at 400 meters. And we can see that primarily what's driving this ice sheet extent response is our surface temperature, with a smaller contribution from ocean temperature, particularly partially off the coast of West Antarctica, and we have a lesser contribution from precipitation. And then here is just the change in global mean equivalent sea level between these two times. Okay, so next we have our ice volume of our transient simulations. So this red line here includes those two times of the simulations I previously showed in the last slide. And we also tested the ice sheet model without the ice cliff failure mechanism. So we can see that the frequencies, when you turn off this cliff failure mechanism, the frequencies of these two simulations still align quite well, like the peaks and troughs are pretty aligned, but our amplitude of our simulation using this ice cliff failure mechanism is quite a bit greater. And also I'd like to add the ice volume for the early Pliocene is maybe a little bit higher than you would expect. It matches closer to modern observations, and this may be due to biases in the model. But yeah, these are just preliminary results. That's something we're going to have to look into more. And we also performed a wavelet power spectrum analysis of our transient simulations. And so from this, we can see that the frequency of ice volume is most significant at around 40,000 to 41,000, a period of 40,000, 41,000. This is due to the cycle of obliquity. And then once our obliquity is a bit weaker, that's when we start getting our eccentricity signal. And if you look up towards the top, it is showing some significant frequencies at like 10,000 to 11,000. And we're not entirely sure why that is so far, because you would expect it to be around the cycle of the longitudinal perihelion, around like 20,000 to 23,000. So that's also something we're going to have to look into moving forward. Okay, so in conclusion, our preliminary results of our Antarctic ice sheet response show a collapse of ice shelves across West Antarctica during the Middle-Pliocene, with greater ice loss forcing when greater ice loss when forcings are bias corrected. And both the ice sheet model parameterization and representation of physical processes in our climate models can influence the response of the Antarctic ice sheet and alter the accuracy of sea level rise estimates, as we would expect. So from here, our next steps are to extend our simulations using CESM 1.3. We're actually currently in the process of that now. We want to ensure that our deep ocean reaches equilibrium, so we can get the most accurate sea level rise estimates that we're able to. And of course, we want to extend out our ice sheet model to span the entirety of the Pliocene. And we also want to eventually bias correct these emulated ICSM outputs. And we're also planning on forcing this ice sheet model with ICSM emulated delta 18O precipitation outputs. So there's a subroutine within the ice sheet model that uses Lagrangian tracking with the ice velocities, and that will allow us to estimate the mean oxygen isotope composition of the ice sheet. So far, our Pliocene delta 18O precipitation outputs seem to align quite well with proxy records, at least for the Northern Hemisphere. So that's promising. And then lastly, I plan on exploring a range of melt factors of snow and ice, basal friction and melting, and also GIA using statistical sampling methods. And this will hopefully allow us to address kind of the high parameterization of the ice sheet model. So yeah, thank you. I'd be happy to take any questions if we have time.
Okay, we have time for one quick question.
I know when the original Pollard paper came out, there was a lot of uncertainty about the total amplitude of sea level change in the Pliocene in the range of 5 to 20 meters.
Mhm.
And you can only get to 20 with like an East Antarctic contribution. Are you seeing an East Antarctic contribution, and are there any updates in what the volume is thought to have been, the maximum volume?
Yeah, so far we haven't really run it long enough to look into that. But that's definitely something that we can look more into. I know that recently there was a study coming out using the ice sheet model to force or coupled to a solid earth model to look at that sea level. And so yeah, it might be interesting to compare our results to that, or also run out maybe some Pliocene simulations with CESM and see how the sea level compares. But yeah, that's something I'd have to look into going forward as we run our simulations out further.
Thank you. Summer, you're up.
Good day, everyone. Okay, my name is Summer Minalla, and I'm going to talk about the work that we have recently done on mountain glaciers using the community ice sheet model. And just to be on the same page, I know that most people in this room would know the concepts. I want to introduce mountain glaciers. So these are those glaciers that are found in mountainous regions, and we are focusing on high mountain area regions, for example, Himalayas or the Alps. These are different from the continental glaciers or the peripheral glaciers of the ice sheets in Antarctica and Greenland region. Those are often studied in the context of sea level rise. And a couple of people have asked me this question, whether we are looking at sea level rise for mountain glaciers. And the answer is no, because first, these are very small glaciers, and there are thousands of these mountain glaciers. Just an example, in this figure, I'm showing the Karakoram and Himalaya region. So this is a small domain, almost around 200 by 200 kilometer. And you can see that there are quite a few different types and shapes and sizes of glaciers, even within such a small stretch of domain. So at the top here is Siachen, which is one of the largest glaciers outside the polar region. The length of its main stem is over 76 kilometer. Then you see these smaller glaciers, 10 to 20 kilometers in length. And then in the green box, there are these really teeny tiny glaciers. Most of them are less than a kilometer in length. And again, as I mentioned, that there are thousands of these. In the high mountain Asia region alone, there are over 98,000 glaciers. The significance of these mountain glaciers is as a freshwater resource. So their melt feed river systems that local economies and societies rely on. So they don't really end up contributing to sea level rise. Also, a quick introduction of CISM. I know that this is a CESM workshop. It always surprises me. Even within CGD, there are quite a few people who don't know about CISM for some reason, but this is the ice dynamics component of CESM. And as the name suggests, it is used to study ice sheet evolutions in Greenland and Antarctica. So what it does is solve these conservation equations for mass, momentum, and energy. And what we are going to get is an information of geometry evolution, velocities, and internal temperature. So just to give an idea what sort of output we are getting, this is a figure from Lipscomb et al. And this is for Greenland surface velocities. On the left is observed, and on the right is what is simulated by CISM. And as an ice sheet model, this is run mostly at kilometer scale, so 4 kilometer or coarser. And in this presentation, I'm going to make this distinction of CISM as an ice sheet model and CISM as a glacier model. Okay, so for this work, our focus was to introduce a modeling framework to simulate mountain glaciers within CISM. And then to study their evolution, how they're changing under different climate scenarios. And now CISM can simulate both the mass balance and flow dynamics of mountain glaciers. So it is also a glacier model. And as a glacier model, we require these 4 types of inputs. So we require an outline of the glaciers, their surface topography, their thickness or bed topography, and climate forcing. And thus far, we have done our main runs over the Alps region. And in this figure, I'm just showing a smaller subset of our full Alps domain. So as I mentioned earlier, that as an ice sheet model, it is run at kilometer scale, but for glaciers, we have to go to much finer resolutions, again, because they're so much smaller. So here on the left, I'm showing a 200-meter CISM grid, and this is over Karakoram region. So the big glaciers that you're seeing in the center here is Baltoro. Just as a comparison, on the right side here, I'm showing the same glacier represented by a very traditional glacier model, OGGM, which is a flow line model. So with CISM, we can get this distributed information of thickness and velocities. For the Alps region, we actually ran it at an even finer resolution of 100 meter. And there were a couple of reasons for that. One of them was that even at 200-meter resolutions, there were a few glaciers that were missing. They were at subgrid level. And at 100-meter resolution, you can see that there were only 6 glaciers that were smaller than our grid size. So we wanted to account for the most number of glaciers and also the most mass of glaciers in every region. Okay, so again, as an ice sheet model, CISM requires an input of surface mass balance. It does not compute that. And for if we are doing couple runs, that information is coming from the land component of CSM for Greenland and Antarctica. This coupling is not presently available for mountain glaciers. So we introduced a new, simpler scheme to compute mass balance of these glaciers using this PDD scheme, positive degree day. And here the mass balance depends on only precipitation and temperature. So we have these 2 equation calibration scheme. The first equation at the top is where we are assuming that our baseline climate is at some pre-industrial level when the net mass balance of the glaciers was 0. And for the second equation, we want to use this information, geodetic mass balance from Hugonet et al. So this is an auxiliary climate equation where our mean precipitation and temperature is coming from 2000 and 2019 mean climate from the atmospheric forcing. Now we have 2 equations and we have 2 unknowns, which are our parameters, alpha and mu, that I'm showing here in red. So we tune for these 2 parameters. Mu is the temperature sensitivity parameter, and alpha is the precipitation correction parameter, and we get alpha and mu for each individual glacier. For the velocity solver, we are using DIVA, which is depth integrated viscosity approximation, and this is quite stable even at 100-meter resolutions. So here we have another parameter, which is friction coefficient, CP, and we tune for CP to nudge the model thickness towards this reference or input thickness, which I'm showing here in the left. So this reference thickness is coming from Perinoti 2019 dataset. And on the right here, I'm showing the output after spin up, the thickness output of the model. And we see that usually there are very small differences. There are some special peculiarities here, but overall these results are fairly good. Okay, so we run a model for spin up for 10,000 years, 8,000 with inversion, 2,000 without inversion. Here in this figure, I'm showing the surface velocities. On the right, what is output by CESM after the spin up. On the left is an external data set. I was very happy to see these results because not only we are capturing the overall magnitudes fairly well, but we can also capture some of the spatial patterns. So if you look at some of those purple dark blobs of high velocity zones, we can capture those with CISM as well. All right, so this year we participated in Glacier MIP3. So this is an intercomparison project for glacier models. And this is the 3rd phase, which is focusing on looking at the equilibration of glaciers under different climate scenarios. And the question that they want to look at is, what would be the equilibrium volume and area of these glaciers if the global mean temperatures were to stabilize at the present day levels and at different warming levels? So to look at this first component here, which is present day level, we looked at commitment loss. So what we mean here is that if the temperatures were to stay where they are right now, what would happen to the glaciers? So on the left side is the current thickness. On the right side is what's going to happen. Even if there's no further warming, we are still going to lose a very large number of glaciers and a very large area and volume of glaciers. And that is shown in the figure at the bottom. So this is percentage area change. This is for the full Alps region accumulated over the domain. And you can see that it's going to take around 270 years for the glaciers to stabilize to current climates, and they're going to lose around 60% of their area and around the same percentage for their volume as well. Very quickly talking about the Glacier Map 3 results, these were shared by Lillian Schuster. So on the left side, we have two different atmospheric forcing models, and then at the top, I'm showing three time periods only. So 1901 to 1920, and the last one is a SSP 126 scenario. All the different colors are the various glacier models who submitted to Glacier Map 3, and these are volume changes. So the two things I want to point out here is that CESM is performing fairly well. So it is the model in the brown color, and it is one of those model in the middle. So we are seeing similar results to all the other traditional glacier models. The second thing is that if you look at the middle panel, which is 1995 to 2014, consider the current climate, you are going to see that most of the glaciers are showing pretty much the same loss, which is around 60% of glacier volume losses. Again, this is something which is simulated, but all the models have a consensus here. Okay, so I want to wrap up by acknowledging all the team members. Bill Lipscomb did all the model development, and this is quite an incredible feat because it's not easy to simulate all of these thousands of glaciers. As I mentioned, they're small, they're spread out, so just putting something like that in an ice sheet model is quite incredible. I know that there are other modeling groups who are trying to do something similar, but maybe with not so much success, so we are really happy with this. Gunter provided a lot of support to do these runs on the HPC. And finally, I want to also acknowledge the Glacier Map 3 team members, especially Harry, Lillian, and Fabian. And with that, if there are any questions, I'm happy to take those.
All right, we got time for some questions. Yeah. Oh, I'm sorry. You need this.
Hi, thank you for the talk. I'm curious, so for in the mass balance scheme, you're using a positive degree day. And I was just wondering what the motivation for using a PDD scheme instead of like a surface energy balance.
Well, to put it simply, that's the simplest thing we can incorporate at the shortest time available that we had. Again, as I mentioned, CESM does not compute mass balance. That is something that comes from the land component, and it is not trivial to include a surface energy balance type of scheme. So I didn't talk about the future work, but what we want to do in the next couple of years is to couple CLM, the land component, and CESM to actually feed this mass balance, similar to what is happening in Antarctica and the polar regions. So Kate is going to be the person to bring this coupling into place for mountain glaciers. But again, as I mentioned, I mean, for this stage, we were quite happy to put something in there that works fairly well.
Okay. And Matthias. Thank you. Last but not least.
All right. So yeah, for the last 10 minutes of the session, I'm going to take you to Patagonia, to the southern tip of South America, and more specifically to the southern Patagonian ice field, where we aim to use the community ice sheet model to forecast the evolution of this ice field over the coming century, by the end of the century. The southern Patagonian ice field is the largest temperate ice field in the southern hemisphere. It's about 12,000 square kilometers, and it's a very long and narrow ice field, and it caps the Andes mountain range. And it's not the only ice field in Patagonia. We have three smaller ones. We have the northern Patagonian ice field, the Gran Campo Nevado ice field, and the Cordillera Darwin ice field. And over roughly the last 2 decades, the ice field ice loss equaled to an equivalent eustatic sea level rise of 0.02 to 0.04 millimeters per year. Now, if we zoom in on this southern Patagonian ice field, we actually see that on its western side, most of the outlet glaciers, they terminate in fjords, so they are marine terminating, and those are here indicated in pink. While on the eastern side, the green glaciers, they mostly terminate in lakes. So calving is a very important process here in Patagonia. Now, the ice field also hosts some of the fastest flowing glaciers in the world, with Penguin Glacier here located in the central western side of the ice field, flowing at a rate of about 10 kilometers a year, which is 28 meters on a daily basis. Next to that, the ice field also experiences a very strong west to east precipitation gradient. And this is shown here on the left panel. And actually, the majority of the precipitation reaching Patagonia is actually sourced from the westerly wind belt. So that's those are winds crossing the Pacific Ocean and bringing tremendous amounts of humidity to the continent. Then those winds collide with the Andes and they rain out along the western Pacific side of the mountain range. And actually, the southern Patagonian ice field is located right at the center of this humid westerly wind belt, where we see the most precipitation. More towards the north and more towards the south, the edges of the wind belt, it gets drier. This map shows here annual precipitation and annual snowfall above the southern Patagonian ice field reaches 5 meters of snow per year, and in some extreme cases, 7 to 10 meters of snow per year. And then towards the east of the ice fields, towards the east of the Andes, it quickly dries out. The right panel here shows us mean annual temperature, and here you can see that Patagonia actually has a relatively warm climate where glaciers exist today. In Western Patagonia, at sea level, mean annual temperature is about 8 degrees Celsius. In the Northeast, it's rather 12, and it decreases towards the south, but also at altitude, and eventually we reach sub-0 degrees Celsius above those ice fields. Now, the latitudinal gradient of precipitation I was talking about earlier, this is also something we see in the glacier variations of the past 2 decades. And this is what this figure shows here. So this is again the southern Patagonian ice field, and the circles, they show us the rate of mass change. Whereas the colors, the surface colors, show us the rate of glacier surface elevation change. And what we see is that in the northern half of the ice field, we see retreat of the glaciers, general retreat, except for this one blue one, this Beyonce Glacier, and that's a surging glacier. But the southern half, over the last 2 decades, the glaciers remained relatively stable. And it's actually this part of the ice field which coincides with the center of the westerly wind belt. And what we see here actually since the 1980s is that increases in snowfall have attenuated glacier retreat driven by anthropogenic warming. Now, our question is, what will happen in the future? And that's what we see here. On the right-hand side, we see temperature and precipitation forecasts under RCP 8.5 simulated by the Chilean Climate Research Center. And we see that by the end of the century, the continent is going to experience a relatively homogeneous temperature increase. Whereas the change in precipitation will show a very strong latitudinal gradient. What actually will happen is that the westerly wind belt, it will move southwards. At the same time, it will also contract. So that means that precipitation in its core will even increase, while at its northern and southern edges, it will decrease. So the northern Patagonian ice field will dry out. The 2 smaller southern ice fields, the Gran Campo, Cordillera ice fields, are going to increase precipitation. Whereas the southern Patagonian ice field is right at the transition of this gradient, where its northern half will get less precipitation, and in the south we might see more precipitation. So this brings me actually to our research goals, where we aim to use the community ice sheet model to estimate the net mass change of the ice field by the end of this century, and test our central hypothesis where this latitudinal gradient in precipitation change might drive a heterogeneous response of the ice field's glaciers to future climate change, where we expect accelerated retreat in the north and maybe glacier stabilization in the south. During this presentation, this is actually still a project in its starting blocks, so we don't have results yet, so I will mainly focus on our methodology from now on, and some challenges and assumptions we'll have to make. So we have to feed our model, of course, with some glaciological data, and here we'll look at some published data sets, for instance, the Fürst et al. Data set, where we will have subglacial bed elevation and also glacier thickness, and the Milan et al. Data set, which gives us ice flow velocity. Climate forcing is also a major part of our effort. And first of all, we have to do some model initialization to get our modern climate and our modern glacial states in agreement. And there we'll use the CR2 MET dataset. It's a meteorological dataset produced by the Chilean Center of Climate Research, and this provides us precipitation and near surface temperature on a daily basis since the 1960s. And once this initialization is running, we'll do some future experiments, again, using a data set produced by the Chilean Center of Climate Research, where we'll focus on RCP 2.6 and 8.5, so the two extremes. We won't look to the other RCPs or the other SSSPs for now, because basically the Chilean Research Center has not yet produced those simulations yet, but hopefully they will do in the future. And as a third experiment, we'll have a control experiment where we keep present day climate stable until the end of the century. Some important remaining challenges we still face in the development of this model is that most of these proglacial fjords and proglacial lakes, they're missing actually a large amount of bathymetric data. So we miss subaquatic topography. So we'll have to make some assumptions there. And the basic thing we can do is just assume in those proglacial basins we have like a U-shaped morphology carved out by previous glaciations, and assume a depth equal to the depth at the grounding line presented by the Fürst et al. Dataset. Now, once our contemporary and future simulations are running well, we also aim to zoom in on specific outlet glaciers of the ice field and solve some paleo case studies. For instance, here for the Torre Glacier, this is a special situation because in front of this glacier, we find this very neat set of frontal moraines, which get younger and younger the closer you come to the present day ice front. And they were all deposited between now and the LGM. With the furthest out, the oldest one deposited about 17,000 years ago, and the youngest one about 500 years ago. So we want to use CESM to actually determine what the climate perturbations were, which deposited these frontal moraines. And we also want to know how far the glacier retreated in between those moraine building events. A similar thing is present in the Uppsala Glacier. So we basically want to test the resilience of those major outlet glaciers to past climate variations. So yeah, this was my presentation. This is our methodology or approach, and hopefully we'll be back next year with some results.
Are there questions? Got time for one.
This isn't my field, so it may be a naive question, but I'm wondering with the bathymetry that you're trying to figure out in the lakes, is there any chance that you can use the shape and the method of breakup of those glaciers that are there to figure out what the bathymetry underneath is?
Yeah, so that's actually what's present in the Fuchs et al. Data set. So they made a data set of ice thickness represented for the year 2000. And by now, lots of those glaciers actually retreated a couple of kilometers and revealed their subglacial topography. So maybe we can make some inferences there from this data set.
Okay, thanks everybody. Let's give a big round of applause for all of our speakers this session and for our help with all the meeting logistics that we've had. Thank you, Caitlin, and our AV team, everybody here. Thank you, Gunter, for organizing a great meeting, and Miran. We have lunch until 1 o'clock, and then this afternoon, some of you might be interested in the Paleoclimate and polar meetings happening. And then remember that there's a wrap-up session at 4:30. Not right now. She's very bad. She'll respond. Which is not. Exactly. Oh, you're trying to. Yeah. Yeah. Well, I have to do that. Like, I guess you could just go. Yeah, I would look for the I'll say, I'll be able that's what my card is. Like jumps. Friday, I mean.
Well, I got back at Really? I get like you should go to some. You want to do I recommended it to Jack in your house. That's there. I was so happy when he said that. My stream was the best.
Yeah.
So in Kansas City, it's
So you got, did you get in there?
Okay, it's already 2 minutes past 1. Let's get started. Thank you for coming, both in person and virtually online. Can I have my introduction slides? Okay, thanks. Yeah, on behalf of the co-chairs of Paleoclimate Working Group, myself, Samantha Stevenson, sitting over there, and Ryan Feng, who's online. We welcome everyone to join the meeting. And I want to remind people that please follow the code of conduct during the meeting. Please offer constructive feedback, share the air, show appreciation, acknowledge teamwork, listen to understand, communicate context, value new ideas, encourage innovation. And next. We have a packed agenda with a lot of interesting talks. And for most of the talks, the speaker will get a total of 15 minutes, and including 2 to 3 minutes for questions. And for the first talk, we only have 10 minutes. Thank you, Sophia, for agreeing to sacrifice the time for your talk. And we have a break at 3 p.m. and the entire session will end at 4:30. That's when we will join the CESM plenary wrap up. And if you have questions for the speakers after the talk, you can either walk to the microphone or we can bring the microphone to you. And for online participants, you can type in your questions in the chat. It's monitored. And I want to take this opportunity to make this announcement that isotope-enabled CESM 1.3 high-res version is the recommended isotope code for research, and it has been ported and tested on derecho. We have validated the simulation at multiple resolutions, including the high-resolution atmosphere, high-resolution ocean, and a high-resolution atmosphere, standard resolution ocean, and a standard resolution atmosphere and ocean coupled. We also have tested this causal resolution 2-degree atmosphere and 1-degree ocean. And we have manuscripts in preparation, and we plan to release a lot of simulation data soon, and the code is available on GitHub. And finally, we have an informal happy hour after the meeting at around 5:30. It will be at Rayback Collective. Have the address here. It's on the Vermont Road at 28th Street. And many of us have cars. Hopefully we can drive there. And if you cannot find a ride, it's 20 minutes walk. Hopefully it's not too bad. And also for this pointer, so you press and hold it, and you should be able to see it. You can also directly point towards the screen. That should also work. And I will stop here and let's start the first talk. Sophia.
Hi, I'll just start talking. I'm Sophia Makarowicz. I'm a project scientist in the Paleo group in CGD. And today I'm going to talk about this new exciting set of high resolution CESM simulations. And I really want to acknowledge the co-authors here because this group was a part of the original accelerated scientific discovery team that really developed and produced these simulations. So this kind of new set of simulations samples a wide range of climate states and CO2 levels in the past. So we use this high resolution version of CESM 1.3 with water isotope tracers. So there's a 1/4 degree atmosphere and land and a 10th degree ocean and sea ice grid. We have a pre-industrial control simulation, last glacial maximum, Pliocene, Eocene with 3 times pre-industrial CO2, Eocene with 6 times pre-industrial CO2, and then I'm just comparing alongside with a RCP 8.5 simulation for sort of a future comparison with the same model configuration. So high resolution CESM provides a really exciting opportunity for paleoatmospheric river studies. So the modern simulations that have been run with this configuration have shown that high resolution CESM improves atmospheric river strength in response to large scale climate modes. You can see here, let's see if I can figure out how to use it. Here, you can see the bias is reduced significantly relative to ERA5, atmospheric river integrated vapor transport. And so we're kind of hoping, and excited that these simulations could improve our understanding of the role of atmospheric rivers in past hydroclimate change and potentially even resolve proxy model discrepancies in regional hydroclimate change using this modeling approach. And so atmospheric rivers are these, thin filaments of high moisture transport in the atmosphere. And typically they're identified using some criteria of integrated vapor transport and shape. But this can be done in a ton of different ways. So the atmospheric river tracking method intercomparison project essentially compares all these different tracking methods and shows that even for the same AR, you can get a ton of different footprints of that same event. So it's a really important source of variability and uncertainty in our understanding of atmospheric rivers. And they just all provide different perspectives. And so in this work, we're trying to use more than one tracking method. So we have 2 tempest extremes as well as LoRa version 2 methods to provide those 2 different perspectives. We use the same criteria for each of those tracking methods through all of our time intervals for consistency. And today I only have time to show you a few things from the tempest extremes results. So first, I just want to show you kind of broad scale trends in atmospheric river integrated vapor transport, which is shown on the top in the pre-industrial case, the absolute values, and then atmospheric river frequency in the bottom panel. And then I'm showing you the change in the RCP 8.5 scenario. So overall, you see that increase in atmospheric river activity. You can repeat that with all of our paleo simulations. And so in general, the trend that you see is when you increase atmospheric CO2 in the atmosphere, you see an increase in integrated vapor transport and frequency related to ARs. And the opposite occurs for the cooler LGM case in general. But how does that change in atmospheric river activity actually translate into precipitation, which is kind of what our proxies are actually going to record? Here, I'm looking at sort of fall to wintertime precipitation in both of the hemispheres. This is when our atmospheric rivers are primarily occurring, at least in our regions of interest, which are the Western US, Southwest South America, as well as the Western Europe. And so I'm showing you total precipitation on the top during those months, and then the AR component of that precipitation on the bottom, and then the same sort of change for RCP 8.5. And so in general, what I just want to highlight here is that where you see a total change in precipitation during these months, it's usually ARs are playing an important role in that precipitation change. And so you can repeat that for our paleo simulations, and you actually see a really similar pattern coming through for the Pliocene. And in particular, I just want to highlight the Western US here, where you can see an increase in total precipitation during those months and then the increase in ARs. And that's kind of exciting because proxies have long recorded a wetter than present conditions in these regions, but climate models have had a tough time resolving that shift. And so also I'm interested in looking at changes in landfalling AR intensity. And so there's a category system for ARs. The way you define the intensity of an AR in this system is the maximum integrated vapor transport and duration of an AR event. And so here I'm just showing you how that sort of pans out for the Western North America in terms of landfalling ARs per year. And so in general, you see the highest amount of these weaker atmospheric river events that gradually decreases with increasing intensity. For the RCP 8.5 scenario, you see a scaling up of all those categories with the greatest change in those most damaging Cat 4 and 5 ARs. Let's see where I'm at in time. Okay. You can compare that with an LGM scenario where you see a scaling down of all your categories of ARs. You actually don't detect any Cat 4 or Cat 5, at least with this tracking method in that region. You could then contrast that with a Pliocene scenario, which actually tends to have a very similar distribution to our RCP 8.5 simulation. And then you could add on our hothouse Eocene simulations where that distribution actually changes. You have the most Cat 1, but then you actually, your second highest category is those really damaging Cat 5 events. And then lastly, I'll just try to wrap up and not maybe explain this fully, but we wanted to kind of understand the kind of broad drivers that are causing these changes in AR activity over all of these time intervals. So integrated vapor transport is combining the integral of moisture and winds in the atmospheric column. So you can have a change in moisture or a change in winds that causes a change in integrated vapor transport and your ARs. And so a few different studies have tried to estimate how do you quantify the contribution of winds versus moisture to a change in atmospheric river activity. And so what Gao et al. Did in 2015 is essentially like come up with this scaling metric for integrated vapor transport, where you create a hypothetical scenario where you keep your present day winds exactly the same, and then scale up your moisture to a future scenario like RCP 8.5. And in that hypothetical scenario, you can see how your atmospheric river activity changes relative to a full RCP 8.5 scenario. And what they find in this method is that moisture is by far the driving force of your increase in AR activity. It's not winds. And so we've replicated that result here. And we've also done that. So this is for the Northeastern Pacific in particular. And so I've repeated that for the Pliocene and the LGM, and we find the same thing. Moisture drives the change in atmospheric river activity, not winds. That's a more preliminary result. So I'm still working through the details of that result. So, okay, now I'll just finish off with some simple conclusions. I think a lot of these, oh, great, okay. I think I'll just finish with these very broad conclusions. I think a lot of these are very common sense conclusions that we would expect from studies that have been done on future AR activity change. But I think that's kind of promising when we're thinking about using these paleo simulations to inform future extreme events in atmospheric rivers. And I think it's also promising that we've seen these high resolution simulations have the potential to resolve some proxy model discrepancies in past hydroclimate change. Should I monitor the online?
Yeah.
Oh, yeah.
Thanks, Sophia. We do have time for questions.
Highest resolution time step for each of these simulations?
You mean in terms of the
If
output?
you have daily, yeah. Do you have?
Yeah,
daily
so
for
for the atmospheric river, there's 6 hourly outputs. And we have 3 hourly outputs for tropical cyclone tracking and other extremes.
Hi, Sophia. That was a great talk. So one of the things that I found when I was looking at ARs and Eocene was a shift in the jet streams, which of course drive where the atmospheric rivers fall.
Yeah.
So for say like the Eocene, where you have a profound shift in the storm track.
Yeah.
Have you looked at other regions that don't necessarily have ARs now, but potentially had them then? I'm thinking specifically of Australia, because I did find a huge signal in Australia, and I would love to see if you find that as well in your simulations.
Yeah, we do. We do. And yeah, I initially wanted to include Australia in my analysis, but because there's such that large shift in continental drift, it's hard to make comparisons across all these time intervals, but there's a ton of atmospheric rivers in Australia.
I'd encourage you to take a look at the dynamical shifts in the jet as well. As part of your analysis, because I think that's a big piece of where the atmospheric rivers are going in terms of frequency. It could be that there may not be there just because there's a shift.
Sure.
Yeah.
Oh, thanks. Yeah, thank you.
Our next speaker is Karishma Diane from India. This will be a virtual talk.
Hello.
Yes, we can hear you. Can you
Now
start?
I can share the screen.
Yes, please.
Is it visible?
We don't see your slides.
It might be on a different window, so you might have to share a different screen. So it might be on a different screen if you have two monitors. So you might just have to share the other window with us.
Now is it visible?
Yes, we see it now, but not in full screen mode.
I put the in the full screen. Is it visible?
It's just in the slides. We cannot see the full screen yet. We just see your layout.
Hello everyone, my name is Karishma Daya. I am from India. I'm a PhD student working in the National Institute of Technology, Odisha, India. Today I'm going to present one of my PhD work on understanding the inter-annual variability of Indian summer monsoon during the warm mid-Pliocene period. As we all know, the Indian summer monsoon is a large-scale phenomenon with a reversal of winds from northeasterly in winter to southwesterly in summer. Uh, as in it is Indian summer monsoon occurs every year, but its intensity, its distribution, like spatially, and its timing also varies year to year. Uh, so large variations in Indian summer monsoon can lead to flood and drought events. As we see in the 20th century, there is a decreasing trend in the Indian summer monsoon rainfall, which is associated with random fluctuation. While in the 21st century projection from many climate models, there are large variation with the increasing trend in the Indian summer monsoon rainfall. So to betterly understand this variations, uh, uh, for the better prediction, we have chosen one of the past warm period, that is the mid-Pliocene period in Pliocene epoch, having the solar orbital forcing and the global surface temperature similar to the 21st century. For studying this, we have used six CMIP 6 models, including CSM, EC, GISS, HEDGEM, NORESM, and IPSL. We have selected the data on the monthly time scale for a number of parameters.
Karishma, we are still looking at your first slide.
Slides are not changing.
No.
Oh. How to? So can you share from your side? Actually, I'm changing. I've sent the PPT.
We are still looking at your first slide. Maybe you can click what you have on the left. Yeah.
Actually, now it is not in slideshow mode. So can I continue with this?
Yes, I think this will work. Thank you.
Okay. So I have listed the six CMIP 6 models we have used based on the availability of these models in the mid-Pliocene period. And we have also used the reanalysis and observational data set for a number of parameters like precipitation, GPCC, sea surface temperature, COV-SST data. In this study for finding the interannual variation, we have used a number of statistical tools like coefficient of variation, then the dynamical monsoon indices like Indian monsoon index, vertical meridional shear index, vertical zonal shear index. The standard deviation in these monsoon indices will tell about the interannual variability and the intensity of Indian summer monsoon. For finding out the like flood and drought events, we have used the standardized precipitation anomaly, and for finding the El Nino and the La Nina event, we have used the standardized SST anomaly or the Nino 3.4 region. So coming to the results, initially we have validated these CMIP 6 models on the interannual scale. For this, we can see in the figure 2, We have plotted the JJ's precipitation anomaly over the 100 years of period from 1914 to 2013 from all the models for the historical period, and the respective observation we have shown in the black line. As from the figure, we can't interpret directly like how much betterly the models are capturing the variation. So for that we have calculated the correlation between the two, and we found in the table we can see the correlation values of the respective models, but at the 95% significance the value is 0.195. Based on that we can able to analyze that all the models are having the correlation values more than it. So models are able to capture the interannual variation in precipitation from on the interannual scale. Similarly, actually, we have also analyzed the global SST anomaly also over the 100 years of period, and we can see the correlation values are much higher for the SST. So models are well able to capture the SST in the precipitation features on the interannual scale. So for the further investigation in mid Pliocene period, we have used all these model. Uh, so for finding the interannual variation in mid Pliocene, we are actually relatively finding the this variability in respect to pre-industrial period, and for this we have done the 100 years of variability we have seen in the precipitation during the JJ season. As we can see, like colored lines in the figure 4 representing the models in the mid Pliocene, while the black line representing their corresponding pre-industrial simulation. So for this we can see from the figure also we can somewhat interpret which model having the larger variation, which are showing larger, which are showing less interannual variability. But the statistics of this we have calculated from the coefficient of variation, and in the table 3 we can see the mid Pliocene period the values of coefficient of variation are less during the mid Pliocene than the pre-industrial period, indicating the less interannual variability in precipitation during the mid Pliocene as compared to the pre-industrial. This we have verified through the different monsoon indices also. So in different monsoon indices, as I mentioned earlier, in MHI, IMI and WYI, we have calculated the standard deviation and we have compared in both the periods. From that we found like most of the models are showing the finding the less standard deviation. During the mid Pliocene, interpreting there is a less interannual variability during the mid Pliocene than the pre-industrial. But these results, we have interpreted for the models, but for the interannual scale, there is till now no proxy studies we have found. So its verification is somewhat uncertain. So for finding the variability in ISMR, how much it is reliable, we can be dependent on its forcing drivers. As we know, interannual variability of Indian summer monsoon depends mainly on the tropical forcings like ENSO and IOD. So further, we have tried to find out the variation in those forcings and then how they are correlating with the Indian summer monsoon. So first, the tropical forcing is in ENSO. So for that, we have looked over the SST anomaly over the Nino 3.4 region. In the figure 5, we can see the variability of SST over the Nino 3.4 region, and the coefficient of variation in these shows that during the mid Pliocene, the variability is less. So this we have further verified through the El Nino composite, the spatial pattern of SST anomaly during the El Nino composites, showing that over the Eastern Pacific, in the both the periods mid Pliocene and pre-industrial, we can see most of the models are showing the highest, more magnitude in SST anomaly during the pre-industrial. This signifies that verifies there is more interannual variability in pre-industrial rather than the mid Pliocene. So similar analysis we have done using the La Nina composites also, that also verifies there is less interannual variability in mid Pliocene as compared to the pre-industrial from most of the models. And these results are consistent with the previous recent studies which are showing less interannual variability in ENSO. Even there were studies showing the permanent El Nino situation also, La Nina situation also, but the recent studies are completely denying that permanent El Nino and the La Nina situations, and found there is less interannual variability in mid-Pliocene than the pre-industrial. So now we can find a teleconnection, like less interannual annual variability we found in the mid-Pliocene in the ISMR, and now we are finding the less interannual variability in ENSO also. So there is teleconnection, as we all know, but how this teleconnection is how much stronger in the mid-Pliocene than the pre-industrial, that for this we have seen the JJ's precipitation anomaly during the El Nino composites and also during the La Nina composite. So as we can see, the drought condition during the El Nino years are much stronger over the Indian region during the mid-Pliocene. Similarly, during the La Nina composites also, this wetter conditions during the La Nina composites are much stronger during the mid-Pliocene, indicating the teleconnection between the SMR and the ENSO is much stronger during the warm mid-Pliocene. And this we have further verified the teleconnection through the statistics of simultaneous frequency of drought with the El Nino events and flood with the La Nina events. So here also from this table statistics we found that teleconnection is much stronger in the mid-Pliocene period. Further, we have also verified through the spatial correlation between the ISMR and Nino 3.4 index. As we can see in this figure 10, like the negative correlation is much higher during the mid-Pliocene in the left panel as compared to the right panel in most of the models. So again, verifying there is the teleconnection between the ISMR and ENSO is much stronger in the warm mid-Pliocene than the pre-industrial period. Another tropical forcing we have seen is the Indian Ocean dipole. From this figure 11, we can see their variability. We can't clearly depict the variability, but the statistics of this variation we have depicted from the standard deviation, which shows that most of the models, including the CSM, are showing the less interannual variability in mid-Pliocene in the Indian Ocean dipole. But for finding the the teleconnection between the IOD and the ISMR, we have done the spatial composite analysis over the Indian region from the spatial pattern of JJ's precipitation from the IOD composites, which showing not the clear results. Like during the positive IOD years, we are getting drought condition during both the periods, not even the pre-industrial, in both the periods, mid-Pliocene and pre-industrial. From most of the models, we are getting drought condition. And similarly, in the negative IOD years, we are getting the wetter condition. So this is somewhat opposite correlation we are finding in both the periods. Then we can say the teleconnection between the two, the IOD and the ISMR, is much weaker, that we have verified through the spatial correlation between the two. We can see the negative values in both the periods except the head jump model. So the teleconnection, maybe
Sorry,
the models are not able
sorry
to
to interrupt.
capture.
This is your 2-minute warning.
Yeah, I will finish in just 2 minutes.
Go ahead. Yeah, you have 2 more minutes.
So maybe the models are not able to capture this this teleconnection between the ISMR or and IOD, because the positive correlation between the two is not able to capture in the pre-industrial period also. Further, we have find the like in the recent studies we found there's extratropical forcings also influencing the Indian summer monsoon. For that respect, we found the interannual variability in NAO, and the standard deviation in the NAO found to be less values during the mid-Pliocene than the pre-industrial, indicating the weaker forcing of NAO during the mid-Pliocene. and having the less through the correlation we found there is weaker correlation in both the periods in the pre-industrial and the mid-Pliocene. It may be due to the models are not able to capture, or maybe in both the periods the forcing is very less. One another forcing, extratropical forcing we found is the Eurasian snow cover. We try to see the impact. Generally, the higher than the normal winter and spring temperature led to stronger condition during the ISM. But from these results, we are not able to conclude that during the mid-Pliocene and in the pre-industrial, the impact of snow cover is not significant. So, as I'm concluding, the variability in ISMR and its associated tropical or the extratropical forcings is less only, but the teleconnection between the main driving force we found from the study is ENSO. And there's less interannual variability in different parameters or in the forcing during the warm mid-Pliocene may be due to the equilibrium state reached in the mid-Pliocene, which is not found to be projected in the warm 21st century. These are some of the references. Thank you.
Thanks for showing the interesting results. And I want to point out that Kurishima is joining us at midnight their local time. So we really appreciate your participation. And do we have a quick question? Okay, then in the interest of time, we should move on.
Thank you.
Thank you. Our next talk is from Gary Upchurch. Gary?
Oh, very good. Everybody can hear me? I have to stoop over. All right. Today, I'm going to be giving a data talk, and it will be about using die-cut wood anatomy for reconstructing climates in deep time, and in particular, the Cretaceous. Now, wood anatomy, and in particular, growth ring studies are familiar to most people in the field of paleoclimate, especially those working with the Pleistocene and Holocene. And with growth ring analysis, you use individual species, correlate patterns in the growth rings to climatic parameters using multiple regression, and from that, you come up with climatic reconstructions. What's less widely appreciated is that in deep time, you can use a number of wood anatomical characters for climatic reconstructions, and you tend to work from whole assemblages rather than from individual species because most of the species are extinct. Now, the presence or absence of growth rings is, of course, probably the most widely recognized tool, but there are a number of other characteristics of microscopic anatomy that paleobotanists can use in order to reconstruct climates of the past. Now, in order to give you an example, I will be showing you two different woods. This is elm on the right. This is balsa wood on the, elm on the left, balsa wood on the right. And the elm is a good example of a temperate zone wood. First of all, it has growth rings, which are cessation of growth during a dormant season. We see one here, and then down here we see another. The second thing is that we see variation in the size of the water conducting cells called vessels. Here we have very large vessels produced early in the growing season, and then much smaller diameter, less hydraulically efficient vessels later on. And finally, we see the development of a lot of support, hard tissue, fibers in this particular case. Contrast that with balsa wood. Balsa wood has fewer very large vessel elements. There are no growth rings, and you see a lot of parenchyma or soft tissue. Now, I'm going to address several questions in this talk. First of all, can die-cut wood anatomy be used to infer late Cretaceous terrestrial climate besides the obvious one or presence of absence or seasonality? And second, I'm going to ask whether die-cut wood anatomy can provide quantitative climatic estimates congruent with those of other proxies. And I'll talk about mean annual temperature first, briefly talk about cold month mean temperature, mean annual range of temperature, mean annual precipitation, and then the length of the dry season. So the flora I'll be talking about is one that my research group has worked with off and on for the last 3 decades. It's from the Jose Creek member of the McCrae Formation. We call it the Jose Creek flora. South central New Mexico, located around 40 degrees paleolatitude, give or take. It's dated as late Campanian based on uranium lead dates on zircons from the volcanic ashes. It is a hyper-diverse flora, the most diverse Cretaceous macroflora known in the world, soon to be reported in detail. It also bears plenty of woods, fruits, and seeds. And the wood flora is diverse. It consists of conifers, various dicots, and then finally monocots, both in situ woods, logs, and wood fragments. Now, I'll be using 2 major sources of data for my interpretations. One is the publications led by my former postdoc, Emilio Strada, now in Mexico City, and then the unpublished dissertation of my PhD student, Joan Parrott, not published, but nonetheless available online as a source of data. So this is just to give you an example of what the flora looks like and some of its diversity. We have at least 38 dicot wood types, at least 20 we know are from tree-sized individuals. If you take a look at the pretty pictures, you can see a very large stump here with Emilio and Joan for scale. Just looking at the cross sections of wood here, you can see very nice preservation of tissues. This is due to abundant volcanic ashes and very nice silicification. You can see details of the water conducting cells. Here we have a junction between 2 where you have these ladder-shaped slits or perforations. This one here has a single round perforation. This is a side view of wood showing these radial structures called rays, fibers running up and down, and the little dark cells are secretory structures. Now, this is a one-of-a-kind flora. This is the first Cretaceous flora where we have enough tree-sized individuals in order to be able to try this technique on the Cretaceous. So how do you go about estimating climate? Well, there are various qualitative indicators, and then there are what I refer to as physiognomic transfer functions. The qualitative indicators are based on quantitative measurements of anatomy or tissue structure, and then are used to generate certain indices that can be compared with modern vegetation type. So we have, for instance, the presence or absence of annual rings. Then we have something, the vulnerability to air embolisms, an index called V. Basically, if you're like a wood up here, whoops, wrong one. Okay, here we go. If you're like a wood up here, you have very few vessel elements. They're large. You're very vulnerable to incapacitation of your flow by air embolisms. And meanwhile, if you're down here, you have greater redundancy. You're less vulnerable. Another index is mesomorphy, basically the Goldilocks of wood structure. And then patterns of vessel density and diameter. And here we can see up at the top here, these are patterns that are very characteristic of modern tropical plants. Tropical plants have this type too, but in the temperate zone, this is basically the pattern you see. We also have physiognomic transfer functions, multiple regression equations. We look at percentages of species with given characters, and we can derive parameters of temperature, and we can derive parameters of precipitation. So first, let's take a look at the quantitative overview of the Jose Creek dicot woods, along with a few cross-sections showing preservation. Over 90% of the wood types have 0 growth rings, not even a hint, indicates clearly no freezing and probably no dry season. The vulnerability to air embolisms, the V value is 10, which to a wood anatomist means relatively wet conditions with no freezing. If you're in the temperate zone or you're in dry season zone, the V values will typically be 1 or even less. Mesomorphy, or our Goldilocks value, is 5,800. What that means is this is clearly something in the Goldilocks zone, very different from woods that either are in freezing climates or else in dry zones. And then we have the tropical pattern of vessel diameter in our flora. 45% of the trees have that typical tropical pattern. In tropical South America, 65%, and in temperate North America, north of Mexico, it's under 2. We have various transfer functions that have been proposed. Had a flurry of activity about 25 years ago, spearheaded by Michael Wieman, along with Elizabeth Wheeler and Steve Manchester. They derived a series of equations for mean annual temperature. They ended up with 3 that had the lowest variation when trying to predict the mean annual temperature of modern reference sites. If we use those 3 on our Jose Creek flora, we get values ranging from 28C to 21. If we average them, it comes out to 24. If we look at the overlap of 2 standard deviations for the equations, we end up with a range of 24 to 26 degrees. Now, you might say, well, this isn't so good until you start looking at the other temperature indicators from the Lake Campanian, and then it's in the same range as them. For instance, leaf margin analysis for the Dory's Tough leaf flora from the Jose Creek gives a value of about 21C. If you go with Tex 86 from the Mississippi embayment, the Shuqualak core, you get a mean annual temperature of 28, and there are other published values that fall in this range. So we're in the range of other published values. For knowing cold month mean temperature, there's only one equation proposed. It gave a really high value, 23 to 24 degrees C, which was 4 degrees C, maybe 5C lower than the highest mean annual temperature. If you simply subtract this value from the different mean annual temperatures, we get a cold month mean temperature of at least 16 degrees C, which will give us a mean annual range of temperature somewhere around 10. Do we have other indicators to back it up? Yes. So for instance, we have diverse palms known both from leaves and from woods. We have plenty of woods with no rings, like 90%. And then we have diverse cycads, a palm-like group of conifer relatives. And they all constrain the cold month mean temperature to be at least 5 degrees C, probably much higher. Well, what about mean annual precipitation and the length of the dry season? I have to issue a caveat here. Paleobotanical estimators of precip and deep time typically overestimate, sometimes pretty severely. And with these wood functions, like 9 out of the 10 reference floras had gross overestimates of precip. The equation that's provided gives us nearly 3 meters of precipitation a year. When we look at the length of the dry season, plug our values into the equation, we get a dry season of -6 months. There's clearly no dry season here. Is this backed up by other indicators? Well, the paleosols, no pedogenic carbonate, no evidence of dry season. The comparison is with alpha sols and ultisols, which would seem to give an upper limit of about 1.5 meters or 150 centimeters of precip a year. Leaf size analysis gives comparable results. This is based on unpublished results from the Dory's Tough flora. The exact equation you use to derive precip will give you slightly different results, but all within this range of under 150 centimeters. So to conclude, the dicot wood flora of the Jose Creek is most comparable to that of the modern day tropics or warm subtropics. Mean annual temperature in the realm of 24 to 26 C, probably. My microphone is busy falling down on me. Megathermal climate at about 40 degrees of latitude. It falls within the range of other climatic indicators. A moist to wet climate. And to give a good visual, I like to use the Holdridge scheme of vegetation, where we have three sides: potential evapotranspiration on the left, annual precipitation on the right. We also have different vegetation types. This is the tropics, where you have lowland, pre-montane, lower montane. Cut off on the right, we have lowland, tropical, subtropical, and so on. And even though we have some ranges of values, our Jose Creek flora falls in this realm, in the realm of warm, pre-montane to lowland, tropical, moist vegetation. On that, I'd like to acknowledge support over the years through various sources, and I'm happy to take any questions.
Yes, we have time for questions, maybe a couple.
Thanks for sharing. It was really neat to see the fossil cross sections and stuff. I was wondering, so at the end when you're talking about some of the kind of quantitative reconstructions and maybe casting some doubt on some of these values, is part of this procedure are you able to come up with uncertainty quantifications for some of these measurements, just because this can be really useful in terms of model data comparisons?
The answer is we haven't worked on formal quantitative uncertainties. There are, of course, standard deviations on these various estimators. And so we clearly can do that for especially temperature. And essentially for mean annual temperature, it doesn't matter whether you're using woods or leaves. One standard deviation is about 2.5 degrees C. And so you can use that. With the precip, I think there may be a published value. And I would say with the precip, if I was doing any model data comparison and you told me the precip was only 1.2 meters, I said, yeah, that's fine, because we know the proxy doesn't work well here. So there are some, and there are others where we might not have it exactly, but if you were to contradict me, I'd say, okay. Next.
We have an online question. Oh, can everyone hear me? Is this working? It should be working? Okay. Ramfang asked, this is really cool. It looks like the site is next to the Central American Seaway. Previous simulations, Frick and Seawall 2011 records suggest monsoonal climate to the east of the Central American Seaway. Perhaps the woods are telling a different story.
Well, you said monsoonal to the east of the seaway, or you mean to the
west? To the
west?
west. To the west.
And okay, one thing, this is well inland. It's at least 100 to 200 kilometers inland from the seaway. Would I suspect monsoonal circulation? Yes, I think that's probably part of it, especially given the reconstructed heights for Laramidia, the Sevier Highlands or Laramide Highlands, wherever you want to be in that time zone. So I suspect that's part of it. Betty and I have been discussing tropical cyclonic storms coming up the western margin of the seaway as another potential moisture source. And I might point out that to the south of the McCrae, there was a paper published this year in Cretaceous Research by Emilio Estrada's group with me as last author, where we have evidence for pretty wet conditions. It's in the Olmos Formation. You've got these thick piles of coal, like 2 and 3 meter thick coal beds. And again, whether, probably have some mixture of monsoonal precipitation and cyclonic storms providing a lot of the moisture.
We will move on to our next talk by Josh Coop.
All right. Hello, everyone. My name is Joshua Coop. I'm a postdoc at CU Boulder. Title of my talk is Sunburn Phytoplankton of the Chicxulub Asteroid Impact as a Case Study for Ultraviolet Radiation Inhibition in Marble. And I'm going to be talking about my attempts to simulate the asteroid impact in CSM and incorporate UV radiation. So we think that the Chicxulub asteroid impact around 66 million years ago at the KPG boundary caused this mass extinction event through the injection of soot, dust and other aerosols into the upper atmosphere, which blocked sunlight, caused heating in the upper atmosphere, and likely destroyed stratospheric ozone, such that when all of the aerosols were removed from the stratosphere, there was a possible pulse of ultraviolet radiation impacting terrestrial and marine organisms. And this UV pulse has been hypothesized to maybe contribute to the extinction. So we're using CSM to simulate that very UV pulse and figure out what role it could have played. So straight into the methods, we're using POP version 2. It's coupled to the Marine Biogeochemistry Library, or MARBLE. We're including 4 phytoplankton functional types, including small phytoplankton, diatoms, diazotrophs, and importantly, coccolithophores, which are these calcifying phytoplankton. And there's evidence of their extinction at the boundary, so we want to understand how they evolved. And we also have 1 zooplankton functional type to keep the phytoplankton in check. And this tool is going to help us simulate this impact. For the getting the biogeochemical state right to simulate the impact, we need a spin-up. So we did a physical ocean state spin-up for around 1,000 years using 2-degree CAM4 as the atmospheric component. Then we needed to spin up the biogeochemical ocean state, requiring around a 1,500-year spin-up before ideal age became stable in the deep ocean. This was initialized using globally averaged, uniformly distributed values. And by the end of the spin-up, the primary productivity looked something like this. And these are the biomass for all the different phytoplankton functional types in our late Cretaceous continental configuration. We had to scale oxygen consumption due to this known issue with POP having a sluggish ocean circulation. This issue popped up in the late Cretaceous as well. So to prevent the deep ocean from becoming anoxic, we have this scaling. And then these are the boundary conditions for CO2 is pretty high, 850 ppm. Solar constant is a bit lower than present day, and global average sea surface temperatures are quite warm at 26 degrees Celsius. The atmospheric model to simulate all the aerosols is WACM, a slightly older version 4, which is a little bit more stable with these all of these light absorbing aerosols. And we've coupled this to the tropospheric ultraviolet and visible, or TUV model. And this is going to let us simulate UV radiation and then pass it to the ocean so it could then affect phytoplankton. And this lets us simulate all the consequences of aerosols. We're using CARMA as the aerosol module, which simulates the growth, transport, and removal processes of soot, dust, and all of the halogens. And in TUV, we have this capability of calculating this E star INH. It's essentially a cell damage parameter, and you input these biological weighting functions in order to compute that. So within the model, as I mentioned, we have all these phytoplankton functional types. We scoured the literature from present day phytoplankton. Obviously, this is the Cretaceous, but it's hard to find even these weighting functions for the present day. So that's one caveat. So for diatoms, coccolithophores, small phytoplankton, they all have their own biological weighting functions. Note that diatoms are quite sensitive to UV light at this lower wavelength bound. That'll become important later on. The asteroid emissions, there are 3 types of emissions. There's an emission at around 50 kilometers in the upper atmosphere, which is a ballistic emission. There are these global wildfires that happen at the impact from the initial thermal heat pulse, and then the rocks of the ejecta going throughout the world, causing global wildfires. And there's also these splashed emissions, uniform aerosol emissions centered around 4,000 kilometers from the impact itself and mixed above the tropopause. And so we're injecting over 70,000 teragrams of soot, of which 20,800 is fine, which is the soot that'll actually last. The rest of it is coarse soot that'll fall out rather quickly. We're injecting 2 million teragrams of dust, over 100,000 teragrams of halogens, which will help to destroy the ozone layer, and 66,000 teragrams of NOx emissions, which will also help to destroy the ozone layer, and over 7 million teragrams of water vapor from the impact was in a shallow sea, so a lot of that water became vaporized and entered the upper atmosphere. So getting quickly into the first results, this is a visual of the soot as it is injected into the upper atmosphere. So this is with height and this is through time. And so over the course of 7 years, that's around the time it takes for most of the soot to leave the upper atmosphere. But during this time, there's essentially no sunlight reaching the surface. The presence of these aerosols is causing heating, as well as the presence of the ozone depleting halogens causes a very sudden reduction in global ozone levels. So this blue line is a control run with no perturbation, so around 300 Dobson units of global column ozone, and there's essentially no ozone for 6 to 7 years until some of the soot gets removed and some of that heating is removed from the stratosphere, which allows for some ozone generation. But towards the end of this model run, it's still around 50 Dobson units, which is quite low, allowing a lot of UV radiation in. So unfortunately, these simulations only go out to year 8. This model got to that point on Monday afternoon. So these slides were made Monday night. The impact winter caused, the impact winter is around a negative 15 degrees Celsius drop in global surface temperatures, which is somewhat consistent with previous work using WACM to simulate this level of an asteroid impact. The global downwelling solar flux remains pretty low until, again, year 7, where there's this sudden soot removal event in the stratosphere and sunlight returns. Now getting into the actual UV results. So this is a plot of global averaged E star INH, which is that damage parameter I mentioned before. This blue line is a control run, so normal UV conditions. And this orange line is the asteroid impact case, showing essentially no UV reaching the surface for 4 years. There's simply too much smoke. And then in year 6, 7, you see this big increase as the soot aerosols start to be removed from the atmosphere. There's a lot of UV light between this 280 to 290 nanometer range. So it's actually diatom damage that's driving this big increase. And then somewhat unexpectedly, the removal of soot and gain of some ozone causes a decline in UV light between 280 to 290. And it's actually the other phytoplankton functional types that then start to increase after that point. I've got to go back for a second. As insolation increases, I don't know where my pointer went. There we go. As insolation increases, UV starts to increase towards the end of this run. And unfortunately, that's where it stops. But we do think that it's going to continue at a kind of an elevated state for many years. How does phytoplankton respond to this UV radiation pulse? So I guess you could say the main result is that there is almost no productivity for 3 years. The world's oceans are pretty much dead. But there's a fraction of phytoplankton. Life finds a way. And as light slowly returns, you see that total phytoplankton starts to approach the control run once again. And in fact, it surpasses it. There's this enormous UV pulse because there were years where these phytoplankton weren't uptaking nutrients, and there's abundant nutrients even though the sunlight is a little bit less. Kind of noteworthy is that UV actually doesn't have that much of an impact through these first few years when you look at it on a global level, which is a bit unexpected. So I had to look into that a little bit further. So what we did was look at how the vertical distribution of phytoplankton is being changed by this UV pulse after an impact winter. And so in the first 20 or so meters is about what we expected, a 20% or more decline in phytoplankton MPP, because it turns out, well, UV really isn't going to make it past this black line. But the visible light, as it starts to return, is able to reach deeper levels, and you see this subsurface bloom for a couple of years that almost compensates for the UV radiation. So this UV pulse is simply shifting where phytoplankton is in the column despite all of the impact winter conditions. And then in year 6, 7, as the aerosols are removed, suddenly diatoms are no longer as inhibited because there's a little bit of an increase in ozone as well. So you get this big bloom of diatoms near the surface, which unexpectedly causes a reversal in this surface to subsurface pattern where there's sudden shading of phytoplankton. So there's some interesting dynamics here in the short term. The years 8 to 25, once those simulations come out, will also probably be a little different than what was happening in these years 3 to 7. So this is looking at it from another perspective. The other plots that I've been showing, they're just all phytoplankton together. It turns out the different phytoplankton functional types all have different responses to UV due to the fact that they're sensitive in different ways to different wavelengths of UV light, and they compete with each other. So first, the diatoms, which is the green line here, years 4 through 7, they suffer pretty immensely during those first few years, whereas the small phytoplankton and coccolithophores actually benefit at their expense despite the pulse of UV light. As the aerosols are removed, suddenly diatoms are no longer as inhibited, and they actually benefit during these high UV conditions, whereas small phytoplankton decline. Coccolithophores severely decline as well. And as the UV continues and these simulations are run out longer, we expect the coccolithophores to continue in this diminished state with almost a 20% reduction in MPP. This is for a number of reasons. One reason being the fact that the UV inhibition function for coccolithophores is partially a function of their shell thickness. And in these impact winter conditions, the oceans become more acidic and they're unable to build thick shells. So this UV inhibition is enhancing the coccolithophore response. And this is pretty consistent with some records of coccolithophores and their calcium carbonate shells disappearing at the KPG boundary, which suggests maybe on one aspect it could just be the ocean acidification, but maybe UV radiation combined with this acidification response could have enhanced their demise. And that's essentially what I got. These are sort of first attempts at these impact simulations, but they do show evidence of a post-impact UV spike, a severely diminished stratospheric ozone state. But I should emphasize that it's not the UV levels really are not even a second order driver of MPP changes on a global level for the first 8 years. It's cold temperatures and almost no sunlight for multiple years. But this is an additional stressor, possibly over decades after the impact, that might be driving coccolithophore decline in the global oceans, especially if stratospheric ozone doesn't recover for many decades. But that will remain to be seen as these simulations are only 8 years in.
Nice. Okay, nice talk, first of all. Second, has your group been in touch with Barry Lomax's group at the University of Nottingham? Because they're using UV pigments in spores to try and quantitatively reconstruct the UV flux.
At the beginning of this proposal, we received, initially we were intending to work with Barry on his work with UV and spores, but we have not been in touch with him for the last few years. So not yet, maybe in the future.
Well, the work is just ramping up after COVID, so you might be interested in comparing notes there.
Yeah, he's on our radar for sure.
Okay, fair enough. And the other thing I wanted to mention is that when you look at other extinction boundaries, like the Permo-Triassic, the Triassic, Jurassic, and even the Toarcian, you get these large percentages of malformed spores, which are being attributed to high UV flux based on modern growth chamber work. And you don't seem to see that at the KPG boundary. At least it's not been really noted. And that's just to put things into perspective, and I'd like to get together and chat sometime in the near future.
Sure, yeah. Thanks. Questions?
Okay. Thank you. Let's move on to our next talk by Feng Zhu.
Hello, everyone. Good afternoon. My name is Feng Zhu. I'm currently a paleoclimate software engineer, aka cyber paleoclimatologist in the paleo group here at UNCAR. So I still do lots of science. And today I'd like to present our ongoing study entitled Revisiting Miocene Climatic Optimum with a Unique Equilibrated CESM Simulation. So the simulation is designed under the guidance of John and our collaborators from Brown, Wei-Ming, and the team. They provided us the proxy data compilation and lots of helpful insights from the observational perspective. So the talk is organized in 4 parts: motivation, design, results, and finally the summary. So Miocene climatic optimum is a geological time interval around 15 million years ago. Why do we care about that? It's so long ago, right? Well, so this period is actually of great scientific interest because based on this Westhold et al. Science paper, the CO2 level at that time is about comparable to the RCP 8.5 scenario for the future. So this period provides lots of warm climate insights, and we can do lots of interesting science, like the relationship between carbon cycle and the global climate, and also the ocean circulation and ice sheets. And more importantly, we can do very important validation of our climate models. So if we cannot simulate such warm climate of the past, how can we trust the future warming simulation, right? So in our study, we are really focusing on these very fundamental but important scientific questions, like how warm was MCO, and what's the equator to pole temperature gradient, and how surface and temperature, deep ocean temperature are connected. Before continue, one thing notable was mentioned that in this science paper, they reconstructed the deep time CO2 level based on this benthic forum data routine. So what is benthic forum? It's actually a kind of bug that lives in the deep ocean, and these bugs have shells, and these shells record the in deep ocean environment during their living time. So it could be a kind of proxy for the deep time climate. And in fact, it's one of the most reliable proxies of deep time, and can be a good validation target for our paleoclimate model simulations. However, most of the existing simulations cannot be compared to these basic forum records directly, which will require that the simulation is isotope enabled, and we need to have the equilibrated deep ocean. So based on these reasons, we conducted a state-of-the-art isotope-enabled CESM simulation with a very long spin-up so that we can have the equilibrated deep ocean. And here we used a dynamic core of spectral element with a 2 degree of atmosphere and land and 1 degree of ocean, so that it's relatively cost efficient, but still able to capture the larger scale dynamics. Here we also leveraged the simulation from A. Costa et al. 2022 as our initial condition, which already runs for 2,000 years. We also used the boundary conditions from shared within the MAOMIP1 project, so that our results could be comparable to their simulations. And also, of course, this is the isotope-enabled simulation, so that we are able to compare directly to our proxy records. So we run our simulation for 9,000 years after the initial condition with 2,000 years. And we almost achieved the equilibrium after 5,000 years. So looking at the first 50-year climatology and the last 50 years, we see that for the surface, global mean surface temperature and the high latitude SST, the difference is above 1 degree. And for the deep ocean, the difference is 3 degrees. And this also affects the surface and the bottom connections. So if we calculate this delta at the difference between MCO and the pre-industrial, and we calculate this delta GMST, the ratio of delta GMST and bottom water temperature. We see that in the beginning, the ratio is 1.65, but in the end, it's very close to 1. So which is very good agreement with this latest study that suggests that the relationship should be 1 to 1. So this ratio is actually very useful because it means that we can estimate our surface temperature based on the bottom water temperature. And again, since the bottom temperature could be estimated with this benthic forum, which is more relatively reliable, that means we can get a reliable estimate of the surface temperature. However, if our simulation does not have the equilibrated deep ocean, then our inference could be incorrect because this ratio is wrong. Now let's move on to the comparison with the existing MIP1 simulations. So here on the left, we compare our simulations, the sea surface temperature against the available PROSI records, and we see that we have overall good agreement in the tropics, but not the case for the high latitudes. To see this more clearer, we look at this zonal mean plot. We see that the models are consistently colder than the PROSI records, and the difference could be up to 10 degrees. So which is interesting, but not our focus today. So our focus is this Southern Ocean area. So we see that our simulation, this thick orange curve, is still within the uncertainty band of the PROSIs, but it's much warmer than other existing simulations with the same 3 times CO2 boundary condition, including our initial condition here, A goes down this brown curve. So you may wonder why first 500 years at our baseline, and we compare our climatology during each period of our spin-up process. We see that this Southern Ocean high latitude SST difference could be up to 5 degrees after about 3,000 years or 5,000 years. And then you may wonder why we have this such huge difference in Southern Ocean, but not in the Northern Hemisphere. Well, that's actually related to this deep ocean circulation. So here we don't have AMOC. However, we have the deep water formation in the Southern Pacific sector, like this. So when we have this deep water formation, the mixing timescale becomes much longer. So we have so huge difference during the spin-up process. And if you look at this spatial pattern of this difference, we see that it connects well with that region of the deep ocean formation, deep water formation. And this difference is really stable. There's not much seasonal variability here. So one big conclusion in our study here is that long spin-up alone can introduce such significant high latitude SST difference. Now, the question is, how does our simulation compare to the PROSI records? So to make a direct comparison, we need to first convert our model simulated seawater delta rating to the CalSat delta rating following this formula. So it basically says that the CalSat delta rating is basically our seawater delta rating plus a function of our seawater temperature. And we have a huge PROSI database, but we filter the database to pick only 5 sites with 200 samples for each site, so that we can really estimate the average of this MCO interval relatively reliable. And now if we compare our, if we pick up the nearest grid point in our simulation and compare to the Rossi locales, and we plot out every sample in this plot to get a sense of the uncertainty, we see that our 3 times CO2 simulation seems to be off compared to the observations. And so is it too warm or too cold? So let's think about from the first principle here. So basically, if we have a warm climate, we will have less ice sheet. And we know that in ice sheet, the delta O18 is usually very negative. So when the ice melts, those negative values goes back to the ocean, leads to a more negative seawater delta O18. And in other words, if we have colder climate, then we have more ice sheet and we have less negative seawater delta O18. So that leads us to 3 possible causes. The first one is actually pretty normal that the foreground data is not really the counterpart of our simulation, meaning that it's not an apple-to-apple comparison. So that's always possible. But in addition to that, we have 2 other causes. The second point is that our simulated ocean is just too warm. And the third is that we specify the seawater delta O18 or the effective ice sheet is just too small. So from these 2 points, we conducted another simulation with 1.5 times CO2, and we also specified a larger effective ice sheet. And we get this triangle here, which is in a better agreement with our observations. So it seems that these 2 causes are possible. And there's actually another hypothesis called deep heat but big ice. So it's a kind of a crazy hypothesis that it means that we still have lots of ice sheet even in a warm climate. So to test this hypothesis, we specify our effective ice sheet to be equal to our present day. So that's crazy. But even with this extreme assumption, our 3 times CO2 simulation seems to be biased. So based on this test, I think our 3 times CO2 may be still too much for MCO. So to wrap up, in this study, we revisited the MCO leveraging a unique state-of-the-art CESM 1.3 simulation featuring equilibrated deep ocean. And we found that with this equilibrium of deep ocean, it affects not only the deep ocean, but also the surface. And this high latitude sea surface temperature difference could be up to 5 degrees, which is huge. And secondly, we also find that this equilibrium of deep ocean can also affect the surface to bottom water ratio. And lastly, we find that this 3 times CO2 might be too much for MCO, according to our benthic forum evidence. But this is still a preliminary result, and we need more time to digest that. So this study is powered by a Python package called S4C, X-ray for CESM for the analysis and the visualization. And with that, I'd like to thank you for your attention and be happy to take any questions.
Questions? Ran again says, interesting. Did AMOC never occur in your Miocene run, or it disappeared due to more and more stratified ocean? Would that affect your result of surface versus deep ocean warming?
Good question. So AMOC never appears because our initial condition already we don't see the AMOC already, and we believe that's very likely due to the topography we used, like the open sea gates will affect that significantly. Thank you. Okay, thank you.
Let's move on to our next talk by Sloan Coates. Press and hold it.
I can just do it here.
Yeah.
So I'm Sloan Coates, and I want to take a moment just to thank my collaborators on this project who are listed on this slide. But this work was actually led primarily by a graduate student in my lab, Gordon Walker. And this is Gordon. And so Gordon decided to pursue a doctorate so that he could research a specific question, which is how did climate variability impact the transatlantic slave trade? And so this project is emerging of his interest in climate, as well as his background in African-American studies, and also his own personal history as a part of the communities affected by the transatlantic slave trade. I'm going to refer to this as the TAST for short. And so what Gordon's going to be doing is using state-of-the-art tools from climate science and employing various lenses from other fields like history and geography to address the question of climate impacts on the TAST. One of these viewpoints that he's going to use, and he's going to use quite a few, is the role for climate variability in specific events during and in the immediate aftermath of the TAST. So for instance, in 1850, a series of fires were set on plantations as a form of protest on the island of Antigua. And so this is the location of, oh, it's hard doing it this way, of Antigua here in the northern Lesser Antilles. And so there are documented social, political, as well as economic contributors here to the civil unrest. But historical documents also suggest that there may have been drought conditions during this period that contributed. So to better understand whether there was a drought, as well as the climate conditions that could have led to that drought, Gordon first turned to the nearest available contemporaneous proxy record, which is a coral from Parguera, Puerto Rico, that was developed and then published by Kilburn et al. In 2008. And so I've extended this map here to the west now, and so you can see the southern coast of Puerto Rico where this coral record is located. This is the record of Delta 018 from that coral, which extends from 1751 to 2004. And then this dashed line here is the timing of the civil unrest on Antigua. And so we can see that conditions were relatively enriched in the coral leading up to, during, and in the immediate aftermath of the civil unrest. So to try to understand what was happening in terms of the regional to large scale climate conditions and how this could have produced this enriched signal in the coral, we're going to use the isotope-enabled version of CESM. So I want to take a moment just to motivate why we are employing a climate model in this case. And the short answer is data limitations, as it often is. So we really have very little data here with which to quantify and understand how climate variability impacts water isotopes. And just to be clear here, water isotopes are a really prevalent observation in high-resolution paleoclimate, particularly of the Common Era. And so this is going to be a general problem that we're speaking about here. So to illustrate just how data limited we are, I want to give you two examples. So one approach we could have used here is to leverage any portion of this record that overlaps with instrumental observations. And quite clearly, this extends to 2004. So we could have taken the modern part of this record, correlated it with, for instance, modes of variability from instrumental observations in reanalyses. And that's obviously a worthwhile type of analysis, but it's going to be limited in a number of ways. Principally, we're going to have just a few degrees of freedom when trying to look at things like decadal variability. And perhaps more fundamentally, we have to assume that the results that we see over that modern interval are stationary as we move back through time, which is a notably poor assumption. And this is a general problem. So what I'm showing here are the fraction of records from the ISO2K database that are available from 1960 to present. And so for many of these, you don't even have overlap with the instrumental record. If we go to the really data-rich period around about 1980, when we start to have the satellite record, we're looking at about 25% of records being available. And this drops really precipitously as we move towards the mid-1990s.
So another option here, we could have tried to leverage instrumental observations of water isotopes, which we do have some of, particularly from GNIP. And so on the left, what I'm showing is the number of GNIP stations, again, from 1960 to present. It peaks about at 170 stations in the year 2000. And just to provide a reference point, there are 20,000 precipitation gauge stations in that same year. So this is really a very limited amount of data to work with. So to address these data limitations, we're instead going to use ICESM, and we're going to use that in place of observations. And specifically, we're going to use ICESM output in concert with a proxy system model for corals. From ICESM, we're going to take 7 last millennium simulations. These are all force transient, but I want to be clear, they don't all include the same forcings. And it's not ideal, but for the results here, we're just going to take them as equal. So treat these as equivalent. But in future work, we're going to try to tease out the role for individual transient forcings of things like volcanic eruptions. So for each simulation, we are going to take seawater delta 018 as well as sea surface temperature from the grid point that is closest to the coral record in Parguera, Puerto Rico. And we're going to use that to drive the coral sensor model of Thompson et al., which is shown here. And what that's going to provide is an ICESM-derived pseudo-proxy record of coral delta 018. So for now, we're going to ignore this noise term that we've got on the end, but we're going to bring that back in towards the end of the talk when looking at some other results. And so we're going to focus here on the range of large and regional scale climate conditions, as well as approximately 20 modes of variability. And we're going to look specifically at the 10% most enriched years within our pseudo-proxy records. And just flipping back quickly to motivate that, this is that real coral record. And the year 1850 is amongst the 10% most enriched years between 1751 and 2004. I do want to note that the results that I'm going to show are really not sensitive to the choice of 10%. And we could also use some sort of averaging interval, 3-5 years, we'd still get the same results. So first, we're going to look at the regional climate conditions during the 10% most enriched years in these pseudo-proxies. The colors here are P minus E. We see that conditions were broadly drier across the Caribbean, and so that's suggesting that the enriched coral delta 018 is consistent with suggestions from historical records that there were drought conditions on Antigua during the civil unrest. The vectors and contours here are going to be low-level winds and geopotential height, respectively. And these are suggesting that there was a southward shifted and strengthened subtropical high, leading to a strengthened low-level jet. So you can see the low level. Well, if I can, guess I got to do it on here. Oop. Ooh. So you can see the low-level jet here is strengthened substantially. And so what's going on here is that as you strengthen that low-level jet via the subtropical high, you're exporting more moisture out of the Caribbean. And in fact, if we look at modes of variability, and I'm not going to show you this directly, but we see a really robust strengthening of the ITCZ. So we're actually exporting that moisture out of the Caribbean, but into the ITCZ, where you see this wetting here just south of the Caribbean. At the same time, the strengthening of the subtropical high is going to increase the stability of the atmosphere over the Caribbean, causing further drying. So as we move to large scale, the colors and SSTs here are the colors are SSTs, the vectors and contours here are going to be mid-tropospheric winds and geopotential height, respectively. And this is pretty straightforward. We see a clear decrease in tropical SSTs, and we also see this in the modes of variability. Again, I'm not going to show this directly, but there's a significant La Nina-like decrease in the Nina 3.4 index. So going back to the original coral record, the enriched conditions around 1850, when we combine it with the ICESM pseudo-proxies, suggest that a strengthening of the subtropical high in low-level jets, increased moisture export out of the Caribbean, increased stability, and led to dry conditions. So at this point, I want to take a step back because we could have done this a huge range of different ways. So I'm not trying to argue that this is an ideal approach to understanding what climate looked like in this region at this time. So the reason we chose this particular approach is because we have a broader goal here of trying to build these methods into a community tool. I don't think it's exactly geared towards people in this room, but more towards practitioners of geochemical records, people developing proxy records that are less likely to go on to the supercomputer and leverage all this data to try to understand what's happening in their paleoclimate records. And so that community tool is going to be geared towards understanding ISO 2K records more generally, so specifically high resolution paleoclimate during the Common Era. So with that in mind, we applied the same approach to all 70 coral records in the ISO 2K database. The dots here are locations of these records. And so for each of these, we're going to use ICESM in a similar framework to produce pseudo-proxy records of coral delta O18. There's a ton that we can do with this. One of the things that we focused on are the regional to large scale climate conditions. We're not going to show those today. Instead, we're going to focus here on modes of climate variability. So specifically, we quantified which of the approximately 20 modes of variability have a significant association with each of these proxy or pseudo-proxy records. And then we took the results of that analysis and we put them into a clustering algorithm. And the idea here is we're trying to find some consistency across these records or any generalizable insights as to what they might telling us about the broader climate system. So we used pretty standard elbowing techniques to determine the optimal number of clusters, which was 5 given our data. And the colors here are going to be the assignments of the records to those 5 clusters. I do not know why this turned yellow on me, which is going to make the colors a little bit harder to see. But if you look, for instance, at those 3 red records directly south of the Hawaiian Islands, those are all assigned to the same cluster. Green records, another cluster. Okay. So the first thing to notice here, at least that I noticed, is these colors are kind of all over the place, right? So there's a little bit of geographic consistency, but when you look at them more generally, 2 sites that are pretty close together can be assigned to different clusters. And what that implies is that they're associated with different modes of variability. So we're going to start here with the green cluster. So this is the cluster that contains this Parguera Puerto Rico coral. And we see that these are centered somewhat in the Caribbean and in the Eastern Pacific. But there's also sites here that are much further afield, like in the South Pacific and the Indian Ocean. These sites in particular are associated with a wide range of modes of variability. They have a significant association with ITCZ strength, with location and area, and so in the PDO, the Indian Ocean dipole and basin modes, and even the northern annular mode and PNA. And so when these records are relatively enriched or depleted, we expect a large-scale reorganization of the tropical atmosphere and ocean. That's also going to cause some teleconnected impacts to the extratropical atmosphere, and particularly in the northern hemisphere. So if you're looking for a coral record that can tell you a lot about the large-scale climate system, the ones in this green cluster would be a particularly good choice. So this red cluster is much more Pacific focused, but in terms of the association to modes of variability, it's actually quite similar here. The only sort of notable difference here is that there's a significant association with Modoki or Central Pacific El Nino that we did not see with that previous cluster. And then the remaining clusters have much less in terms of these modal associations. So this group here, which is largely in the Western Pacific and Indian Ocean, is associated with the Indian Ocean dipole. This purple cluster is the ITCZ strength and ENSO. And then this poor orange cluster here, which has no associations to any modes of climate variability. And so I'm not trying to say that these are not useful records, but these records in particular are likely telling you something about local conditions, not about the large scale atmosphere and ocean. So these are results for perfect pseudo proxies, but we can also check the robustness of these results to the presence of noise by using the noise term in that coral sensor model. And so that's exactly what we're going to do. This is a low noise case with a signal to noise ratio of 2:1. We do see some loss in these modal associations, but the green and red clusters, for instance, still are indicating a large scale reorganization of the tropical atmosphere and ocean. As we go to a high noise case, 1:1 signal to noise case, we really lose a lot of the modal associations. But for the green cluster, for instance, it still has a strong association with ENSO. So these records, if you combine them with statistical methods, could give you a great reconstruction of ENSO. So just to wrap things up, I noted the goal here is to build towards a community tool. And we have a very preliminary version. So take this with a big grain of salt if you want to try to use it. We're calling this PIGM. The idea is that you can go to this website, select any of the 606 ISO 2K records, a timescale, and a seasonality, and it will automatically generate what I hope is a roughly publication quality figure that's going to summarize regional and large-scale climate states, as well as the states of various modes of variability when conditions are enriched or depleted at the location of a proxy record. So currently, this is based on amount-weighted precipitation delta 018, but we're going to try to put PSMs in here instead, and so more soon on that front. And I probably went over time, sorry.
Unfortunately, we are running late. I think you can find Sloan during the break. Let's move on to our next talk by Victoria Todd.
Hi. Okay, so thank you guys all for coming. My name is Victoria Todd. I'm a PhD candidate at UT Austin working with Tim Shanahan, where we primarily do biomarker-based proxy reconstructions. So I just wanted to start off by thanking all of the collaborators and co-authors on this study who contributed their lake records and contributed their model data. We are so grateful for all of you. So I'm really excited to get to have the opportunity to talk about some of the work that we've been doing. The Western US is currently under the most severe drought in 900 years with huge impacts for the Colorado River Basin. This region has experienced mega drought since around the year 2000. But of course, persistent drought in the Southwest is not new, right? So one potential analog could be the Mid-Holocene. Previous studies have shown widespread drought in this region, though quantitative estimates of this drought are really rare. And even less is known about changes in precipitation specifically, as it's really difficult to separate changes in precipitation and evaporation. So in this study, we reconstructed 3 new leaf wax stable isotope records from the Rocky Mountains. So you can see them there. We have Kite Lake from Colorado, Hunter's Lake from Colorado, and Stewart Bog from New Mexico. For comparison at the top, I've also plotted the speleothem isotope record from Leviathan Cave, which is located in Nevada. So these records are quite some distance apart, and they show many of the same isotopic features, which could suggest that this would be a large-scale change in precipitation across the southwestern US. So all of these records show more positive isotopic values during the early to mid-Holocene, and that's really the signal that I'm going to be focusing on in this talk. So we wanted to be able to compare the magnitudes of the precipitation changes in our proxy data directly with the precipitation changes in our model simulations. So for this reason, we utilized a Bayesian mixing model approach. So modern precipitation isotopes in this region are primarily controlled by seasonal moisture sources. So winter moisture is significantly more negative isotopically than summer precipitation. So we use these probability distributions for modern precipitation isotopes to simulate the range of possible proportions of warm and cold season precipitation that could explain, that could explain the proxy data. Then we use the constraint that precipitation must have been lower than today during the mid-Holocene and assume similar probability distributions for seasonal rainfall. So then we can produce a probability density plot of the ranges of possible changes in the amount of warm and cool season precipitation that would explain our proxy records. So what we find is that with this Bayesian stable isotope modeling approach, that drought is much more extensive than was indicated by the PMIP3 models, winter drought. And we're actually seeing declines in winter precipitation that's around 15 to 20% greater than in those models. But we wanted to understand why those simulations are underestimating these changes so severely. So one possible reason is that cool early Holocene temperatures, as we're seeing in these PMIP3 version of climate models, sorry about that, are inconsistent with reconstructions based on proxy data. So this disagreement has been called the Holocene temperature conundrum and is typically attributed to seasonal biases within the proxy records. However, during the mid-Holocene, we do know that there were large changes in vegetation cover, particularly over Africa with the emergence of the so-called Green Sahara. And this vegetation change has been shown in previous work to produce warming in agreement with proxy data, as you can see in the middle here. So for this reason, we decided to use a multi-model ensemble of simulations for the mid-Holocene with this paleoecologically realistic vegetation changes prescribed. So when we plot the changes in winter precipitation in these prescribed vegetation models against warming, we see that warmer mid-Holocene temperatures always produce reductions in winter precipitation, though the magnitude of these changes vary widely. However, I'll also note that the magnitudes of the precipitation responses are small, and though they do improve the agreement with our reconstructions, there's still substantial disagreements between the proxy and model estimates. So I'll get back to that in a minute, but first I wanted to talk about why the models get drier, which could give us some insights into why they aren't drying enough. So when we look at these models, one of the first things that pops up is that this increased warming that's associated with these vegetation changes is not uniform, but it actually results in a lobe of warmer sea surface temperatures that extend from the west to the east across the North Pacific with a lobe of, or with a U-shaped area of cooler or unchanged sea surface temperatures along the coast of Western North America. So interestingly enough, we see a similar pattern in the EC Earth model, which is already quite a warm simulation, even without any vegetation change, which suggests to us that this pattern may be more related to hemispheric warming instead of into anything specific with the vegetation changes. So we wanted to see if this PDO-like pattern of sea surface temperatures during the mid-Holocene was consistent with the existing proxy data. So we synthesized a whole bunch of proxy sea surface temperature reconstructions for the mid-Holocene. And although it's pretty sparse, especially in the areas where we'd really like to see more proxy records like the central North Pacific, sea surface temperature does show some key agreement with the vegetation-enabled models in key areas like the warming in the Kuroshio Current region off of Japan and cooling in the locations off the west coast of the US. So we then categorized proxy precipitation data as wetter, drier, or unchanged so that we could quantitatively evaluate proxy versus model responses using the Cohen's kappa and Goetze statistics. So as you can see in nearly all models, the proxy model agreement is much stronger for the simulations with expanded Northern Hemisphere vegetation up here. So we wanted to understand these mechanisms that are driving the emergence of these sea surface temperature patterns. So first we started off by doing a heat budget analysis. And what we find is that the persistence of the sea surface temperature pattern is primarily due to ocean dynamical adjustments and to a much less extent due to low cloud feedbacks, but that still didn't answer to us exactly what was driving this response. So next we did a single forcing run And what we find is that in the 6K simulation with prescribed vegetation and fixed sea surface temperatures and sea ice, we find that solely land surface warming can actually initiate that atmospheric response in the Aleutian low and this changes in surface winds. So in conclusion, we find that models underestimate the winter precipitation changes during the mid-Holocene. Proxy model agreement is higher in simulations with mid-Holocene warming, and across multiple models, this warming is associated with the emergence of a PDO-like state. This emergent PDO-like state appears to be initiated by an atmospheric response, which is then magnified by those ocean-atmosphere interactions. And hemispheric warming by itself may induce a negative PDO-like state, which could contribute to persistent drought in the Southwest. So thank you so much.
A great talk. We have a lot of time for questions. Did you check the isotopes in the model to compare with your proxy data? Do you see that?
Yeah, so especially for our Bayesian isotope mixing model, that was one of our key concerns because one of the fundamental assumptions that we made was that winter and summer precipitation isotopic distributions were not varying, or at least not varying very much between the mid-Holocene and the present. So that is one of the things that we checked in the model and our assumption was valid. We see pretty good agreement with our proxy records, but yeah, still a little bit cautious about using the CESM.
Okay, let's move on to the last talk of this first session from Andrew Flame.
Okay. Well, that's very unintuitive to use. Okay, great. Thanks. I'm Andrew Flime. I'm a PhD candidate at Washington University in St. Louis, where I work with Brown and Conkey. And today I'm going to talk a little bit about our work reconstructing the North Atlantic Oscillation using isotope-based proxy records in the ICE2K database. We did this in collaboration with Sloan, who thankfully introduced ICE2K a little bit just a minute ago. And then we're going to compare our reconstruction with the Last Millennium Ensemble in the isotope-enabled CESM. Okay, so first I'll give you a little bit of a primer on the North Atlantic Oscillation, just in case North Atlantic Oscillation indexes primarily constrains this sea level pressure gradient in the North Atlantic. The difference between the Azores high here and the Icelandic low. Essentially, to produce the instrumental index that's plotted on the bottom, we just take the difference between the normalized sea level pressure at these two stations. And the reason we're interested primarily in the index here is because during, in particular, the positive mode in the winter, the NAO is strongest in the winter. We're going to be focusing on the winter in this case. Typically, we see a deflection of the jet and storm tracks and temperature and precipitation anomalies. We see warm, wet conditions in Scandinavia and Northern Europe, and that's contrasted by cooler and drier conditions in the Iberian Peninsula and the Northern Mediterranean. And so we're interested in constraining this system insofar as it influences temperature and precipitation in Europe. And also in Greenland, you'll notice that there are anomalies associated with the NAO, especially in Western Greenland. But paleo reconstructions of the NAO, there are still a couple of important questions I think that can be answered. In particular, I pulled this figure from one of Ed Cook's more recent reconstructions, where he's using primarily a tree ring network in Europe to reconstruct the NAO over the last millennium. And you'll see when you compare with other published reconstructions of the NAO, there's pretty big disagreement in the presence, even and especially the magnitude of low frequency variability in the NAO, which is much more difficult to constrain in the instrumental record. And so paleo reconstructions of the NAO give us this opportunity to really evaluate how much low frequency, multi-decadal to centennial scale variability do we see in this mode. And another thing you might notice from sort of the list of proxies that are used in a lot of these reconstructions, isotope-based paleoclimate proxies are somewhat underrepresented in published reconstructions.
And like I mentioned, we have a new Pages working group product called ISO2K, which is this global network of isotope-based paleoclimate proxy records that gives us an exciting opportunity to investigate sort of the isotopic fingerprint of the NAO in this proxy network. And in particular, we know that precipitation delta 18O is regionally much more sensitive to these hydroclimate modes than just precipitation amount, for example. So it integrates sort of large-scale processes that allow us to constrain even the teleconnections of these modes through time. So in order to produce this new reconstruction, we're going to filter the database to focus primarily on annually or subannually resolved records in the Northern Hemisphere. The ISO2K, or sorry, the NAO index is primarily an interannual phenomenon, so we want to focus on that annually resolved subset of the data. And we also want to make sure that we have relatively good data coverage in this instrumental interval, where we can calibrate our reconstruction against the instrumental index. So we're only using records that have 2/3 coverage in the instrumental index. Okay, so the map on top shows you the ISO2K records that meet those filtering conditions. So effectively, we end up with a bunch of ice cores in Greenland. These triangles here, these are delta 18O of cellulose, tree ring cellulose records. And then we've got a couple of speleothems out here. But primarily, we're going to focus for the purposes of this talk on the relationships in Europe and Greenland. I will point out that we have a bunch of significantly correlated records out here in sort of Central Southeast Asia. I could give a whole talk on just the teleconnection there. And we do find that we have significant improvement of our reconstruction if we include this teleconnection. But I'm going to focus mainly on this sort of the centers of action of the NAO for this talk. But if you have ideas about the teleconnection, definitely come ask me about it. Anyway, so the proxies here are colored by just the correlation between the proxy time series and the instrumental index of the NAO in that instrumental period. And to produce the reconstruction effectively, what we do is just take a weighted average. It's called a composite plus scale reconstruction method. And so the weighted average of each of these proxies, weighted where the weights are the correlation of the proxy time series with the instrumental index. And this is what we end up with. So in black here at the bottom, you see the reconstruction of the NAO over the last millennium if we use all of the records that meet our filtering conditions. And then in order to produce an ensemble, we reproduce that reconstruction 1,000 times, each time removing half the records from consideration to sort of hedge against the possibility that one record or one small collection of records is really driving the signals that we see. And then I've run a 30-year moving average through that median of the reconstruction in order to sort of give you an idea for the lower frequency variability. And I'll come back to that low frequency variability in a minute. But really what I want to focus on right now are the spatial distributions of the relationships between the proxy records and the NAO that we see. Because as I set up before, there's a pretty distinct spatial character of the impact of the NAO, at least in the modern. And so we want to evaluate, using the isotope-enabled last millennium ensemble, we want to evaluate whether we're meeting sort of the expectations that we would have for the spatial distribution of the impacts in isotope space. Okay, so defining the NAO using fundamentally the same methods that we use in the instrumental, where we take the difference between normalized sea level pressure in the boxes that contain the instrumental stations. And then the next few plots that I'm going to show are all going to be correlation contours, where I'm testing the correlation of this modeled winter NAO index against the winter, in this case, sea level pressure, to show you sort of the character of the NAO when we define it using this 2-box method. Okay, so the real value of using the isotope-enabled last millennium ensemble here is that we can directly test the correlation of the NAO in the model with the modeled winter isotopes of precipitation. And so these contours show we have significant negative correlation with the isotopes of precipitation over Greenland, especially Western Greenland here. And then we have this sort of uniform positive correlation with isotopes of precipitation over Europe. And if we overlay the proxies, Greenland and Europe, these are two regions I want to focus on. If we overlay again, the proxies that we pulled from the ISO2K database, we can see we have broad scale agreement. We have predominantly negative correlations with isotopes in the ice cores in Greenland. And then in Europe, again, we're meeting that sort of broadly positive correlations across most of Europe. To some extent, this is a little bit contrary to what we would expect when I set up at the beginning that we have sort of differential impacts of the NAO in Northern Europe and Southern Europe. So to explore this in a little bit more detail, we're also going to test the correlation of this modeled winter NAO against a couple of other variables in the model, namely temperature. And so you can see here we have a significant negative correlation with temperature over Greenland. This is primarily what's driving the isotopes in the ice cores. And then in Europe, we do have a significant positive correlation with temperature over Scandinavia and Northern Europe. But if you notice, as you move south into the Iberian Peninsula, and especially the Northern Mediterranean here, you lose those significant correlations with temperature. And if we contrast this with the correlations with precipitation, what we see here actually is that the correlation with precipitation becomes significant over the Iberian Peninsula and the Northern Mediterranean region, really sort of filling in the gaps there that we see with the correlation in temperature. So if we go back to our correlations with the isotopes of precipitation, ultimately what we're seeing here is a latitudinal shift in the primary driver of the isotope relationship with the NAO as you move from Northern Europe down towards the Iberian Peninsula, where farther north you have temperature and the temperature relationship with the NAO driving the isotopes of precipitation. But as you move further south, then precipitation amount starts to become more significant. And I don't mean to suggest that we see like a classic precipitation amount effect like you would in the tropics, but just more so that the temperature relationship with the isotopes of precipitation is significantly weaker when you move south into those more southerly records. Okay, so I want to take a step back here and return to the motivation that I set up at the beginning of the talk, which was that we're really interested in the low frequency variability that we see in the NAO. We can learn a lot about the spatial patterns in the isotope-enabled last millennium ensemble, but how do we compare the low frequency variability over the last millennium between the proxy reconstruction and the models? So one method that we can do to make that comparison is to do a multi-taper spectral decomposition of the two reconstructions. So on the top here, this is the proxy-based reconstruction. And what I really want to highlight is the centennial scale and decadal scale variability that we see meeting or exceeding our null hypothesis in terms of the multi-taper method for the proxies that's largely absent in the last millennium ensemble. And this is maybe even a little bit more apparent if we look at a Morlet and wavelet decomposition of the same two time series. On top is the proxy reconstruction, on bottom is the NAO in the last millennium. And what I really want to highlight here is the black contours give us pretty extensive, significant low frequency variability, especially early in the last millennium, although that signal is largely stationary throughout the last millennium. And if we compare this then to the NAO, we have largely absent significant low frequency variability in the Morlet wavelet. And so this is, I think, is one of the primary contributions that this reconstruction can make is to provide fairly good evidence for low frequency multi-decadal to centennial scale variability across the last millennium that maybe we're missing out a little bit in the isotope-enabled last millennium ensemble. Now, this isn't a particularly groundbreaking revelation because it's somewhat well documented that the last millennium simulations don't necessarily capture all the low frequency variability that we have in these modes. But I do think it's important that we emphasize that, especially in isotope space, we have pretty good evidence that there's low frequency variability in the NAO that maybe some other proxy reconstructions aren't fully capturing. Okay, so with that, I'll leave with a couple main points. We've produced this new proxy reconstruction of the NAO based solely on records that rely on the isotopes of precipitation. We have some interesting transition in drivers of the isotopes of precipitation and their relationship with the NAO that we've learned from the isotope-enabled last millennium ensemble. And then finally, we have some pretty good evidence for multi-decadal to centennial variability in the NAO index that maybe we're not fully capturing in the last millennium ensemble simulations. And I'd like to thank Bronwyn Konecki, my advisor, for all of her support on this project, and Sloan for his collaboration, and also NCAR for the travel support to come present this to all of you today. All right, thanks.
Do we have questions?
Much larger looking at it in particular, looking at individual simulations.
Yeah, absolutely. I think that's a great question. So what I should have clarified is that we're using, in this case, we're looking at individual ensemble members of the Last Millennium Ensemble. There's 3 fully forced individual ensemble members, and that's where we're doing this analysis. But you're absolutely right that looking at the larger ensemble space outside of the isotope enabled members might give us a better idea for how much variability we see in the NAO across ensemble members. Thanks.
They're saying no one's saying anything, so I feel like they might not be able to hear.
There's a mute.
I can repeat the question.
There's a mute button on the bottom.
Okay, cool. Okay, the question is if low frequency variability also shows in other types of proxies by themselves, but just not that one. Okay, so if I'm understanding your question correctly, the low frequency variability, I think, is to some extent a feature of the isotope enabled or the isotope based proxies. If we look at some of the other reconstructions that rely solely on true ring chronologies, for example, perhaps my hypothesis is that as a function of the way that the tree ring chronologies are collected, you're sort of filtering out some of the low frequency variability. So you don't get as much of it in the reconstructions that are based on tree ring chronologies, for example. So I'm sort of arguing that that's a strength of the isotope isotope based proxies, that they give us this low frequency variability that maybe we're missing in other proxy types. Hopefully that answers the question. Okay, awesome. Thanks for the question.
Okay, thank you. If we don't have more questions, before we break, let's give another round of applause to all the speakers for the first session. Okay, let's restart at 3:30. And for the people who are online, please come back at 3:30.
fun at home or wherever you are. We have 4 more talks in this second session. I believe they're all virtual. But yeah, why don't we go ahead and get started with that? The first one we have is Yuntao Bao. Are you online?
Yes, I'm here.
Well, we get set up. That's going to be speaking about ice core evolution and its implication for the Holocene temperature conundrum. So take it away.
Okay, can you see my screen?
We can see a presenter view.
Oh, okay. How about now?
Whoa. Yeah, that looks good. Thanks.
The full screen. Okay. Hope you can hear clearly. Yeah, hi, good afternoon, everyone. So I'm Yuntao Bao. I'm glad to join the CSM workshop this year. I'm a postdoc from the Ohio State University, both Polar and Climate Research Center, and we just completed a transient simulation for the Holocene climate using ICSM version 1 model. And thanks to the contributor who did this simulations. Today I'm going to talk about the ice core data weighting evolution and its implications for the Holocene temperature conundrum. So the last presenter, Victoria, I think she just talked about that before, but you may also heard that the Holocene temperature conundrum, which basically it describes the discrepancy or mismatch of the temperature between the proxy reconstructions and climate models. As you can see in this figure, the blue line is the global mean sea surface temperatures from the proxy reconstructions, and you can clearly see a mid-Holocene thermal maximum during the mid-Holocene, followed by the cooling trend till towards the present day. But at the same locations in climate models, you can see what you see is a gradual warming throughout the Holocene. So this mismatch has 2 main sources of uncertainties. One is from the proxy data itself, because some of the proxy data may bias to specific seasons, to their growth seasons. Another one uncertainties is from the climate models. Obviously, we know model is never perfect and may not capture everything for the past climate. But there are still many efforts trying to reconcile the model data discrepancy. One is from the BOVA in 2021. They tried to remove the seasonal effect or seasonal bias in the marine-based proxies. And after that, they get more or less consistent warming trend throughout the Holocene with the climate models. But this problem still exists if we look at the land region. If you look at the multi-proxy data from the latest TEMP12K dataset, we can still see a clear mid-Holocene warming along different latitude bands. But compared to the climate models, most models show a mid-Holocene cooling, except for the Arctic region. So this problem is still far from being resolved, and especially for the land areas. And we're going to revisit this problem using the direct model data comparison approach. So what data we're going to use? It is the ice core data weighting records, mainly from the Greenland, Antarctic, and tropical mountains. And we know that among different timescales, the ice core data weighting records from Greenland and Antarctic is proved to be a signal of temperature. But for tropical mountains, it's more complex, and I will show that later. For the climate models, as I just told, we use we did the transient simulations for the Holocene using the ICSM model. We call it iTrace. The advantage of this approach, obviously, using ice core data weighting while alleviating the biases in the temperature reconstruction associated with seasonality and other biogeochemical factors. And we don't need to reconstruct data weighting to temperature, therefore introduce less errors. So data weighting, ice core data weighting should be a good benchmark to better evaluate model performance. Let's first look at the results of this direct comparison. We selected 6 Greenland proxies and 3 tropical mountain proxies and 2 from Antarctica. Overall, for Greenland and Antarctica, the proxy, which is shown in black line, proxy data weighting ice core, and the model data weighting in precipitation, which is in blue line, they are more or less consistent overall. But the model data weighting, mostly they underestimate the response, mainly because the model has a weaker sensitivity to insulation forcing. But the most striking results is from the tropical mountains. As you can see, the black line, again, from the proxy data weighting, both Kilimanjaro and Ascron, they show a depletion trend in data weighting throughout the Holocene. But our ITRIS model showing a contrasting enrichment throughout the Holocene. So this contrasting trend is kind of surprising, because given that in our previous work, which just published, we just see the model has a good agreement with the ice core data weighting, especially from the Ascron, and we proved that it's a good indicator of the in situ temperature, and moreover a global temperature. But that is only for deglaciation. As for the Holocene, that is more complex. Let me take the Ascron ice core as an example. So Ascron is an tropical Andes ice core located in 9 degrees south. And the wet season in Ascron is from February to March. And if we're going to find the forcing of this of the Ascron ice core, we can look at the DJF insulation, right? And as you can see in this purple line, the insulation steadily increased throughout the Holocene. So if data weighting is indeed is indeed an indicator of temperature, then we would expect temperature will also increase following the insulation. And then the data weighting ice core should also increase their values or enrich, right? But in fact, the proxy data weighting showing the depletion trend throughout the Holocene. Therefore, this is out of our expectation. We raise a challenging question. What's the forcing mechanisms on tropical mountain ice core data weighting? In other words, what's the interpretations of ice core data weighting during the Holocene? You may think that maybe the precipitation seasonality may change from DJF to other seasons in mid-Holocene, right? For example, we can see that in dry season, such as JJA and SON, the insolation at 9 degrees Celsius all show decreasing trend. So we would expect, if that's the case, the temperature will decrease, therefore may explain this depletion trend in data weighting. But we can test this hypothesis in multi-model simulations from PMIP4. This plot shows the precipitation annual cycle in both the mid-Holocene simulation and the PI control run. And you can see, compared with the black line and red line, they do not show too much difference. Okay, therefore, no obvious seasonality change in precipitation based on these multi-model simulations. So we think that this wet season temperature only may not enough to explain the ice core data weighting change in tropical mountains. So if that's not the mechanisms, what else? Actually, we noticed a recent study. They highlight the exchange between the vapor and snow. Therefore, the signal of the dry season may also be incorporated into the ice core. To test this hypothesis, we can do that like in this way, like the dashed line again that is shown in previous one. This is the model data weighting in precipitation. So that is only for wet seasons or for precipitation events. And this is the conventional way to do model data comparison. But in order to incorporate the dry season signal, we can just simply do the arithmetic annual mean for data weighting, which is shown in the solid line. So compare with the solid line with the proxy in this blue line, which we can see a little bit decreasing trend in the arithmetic mean model data weighting, right? So this may tell us if tropical mountain ice core data weighting represents the in situ temperature, the climate signals from the dry seasons and from precipitation intermissions may also be important in determining the final data weighting ice core values. So this is our first hypothesis. If data weighting still represents the temperature, that should be incorporate both the wet season and dry season signals. And dry season, again, that is produced by the vapor and snow exchange. So if that's the case, we would expect the ice core in Oscaron will tell us the mid-Holocene should be warming, which is close to the Greenland case, right? But can we see that in climate models? Again, we plot the temperature at the mid-troposphere in different PIMIP4 models, which is shown in the contour lines. You can see all of these models show mid-Holocene cooling instead of warming, suggesting ice core proxies. So that's again produces the problem, the model data discrepancy. But we cannot rule out the another interpretations, that is the amount effect. Data weighting may also represent the in situ precipitation or the upstream moisture conditions. Can we see that in climate models? All the climate models, yes, they show the decreasing precipitation in mid-Holocene in both the upstream and Andes regions. But all the PIMIP models, they do not incorporate isotopes in their simulations. So we cannot fully validate the forcing mechanisms here. So there are still, I will raise these two main open questions for the future research. Firstly, can we quantitatively estimate the Holocene temperature change in tropical mountain regions? So far, we cannot validate, we cannot estimate that because we cannot validate whether the tropical mountain ice core data weighting represents for the temperature or they represent for precipitation, right, throughout the Holocene. And there are two main reasons. One is that we do not have other individual proxies or individual records, such as the borehole temperature, to estimate that. Another problem is that climate models, as we show that they do not incorporate data weighting in most climate models. And the model data discrepancy makes it harder for us to study the mechanisms with the help of the models. And the second question is, what's the possible climate model deficiencies and how can we prove that in the future? We resist three possible model deficiencies. First, obviously, the model resolutions, because the mountain region, the higher the model resolution, the better they can capture the physics. And also the double ITCD bias is also a problem in most climate models. The second one is the so-called poleward energy transport bias. So how to understand that? We did more analysis, but basically we showed that the temperature bias in mid-high latitude may also causes the temperature bias in tropical regions because tropics and mid-high latitudes are connected with the poleward transport, right? And you can imagine if the polar region is colder, that will requires more energy transport from the tropical regions to the polar regions. Therefore, the tropical regions could be colder. So that's another bias. Another one is a missing physical process in climate models, because here we did comparison between the model and data weighting from ice cores, but models do not explicitly simulate the post-condensation process in ice cores, such as vapor and snow exchange I just mentioned before. So there are still a lot of open questions for the mid-Holocene temperature change in the future. So I hope this will inspire the future research. Thanks. Any questions and comments are welcome.
Okay, great. Yeah, I think we have time for a brief question or two. Yes.
Thanks for the great talk. Do you have any chance to look into the trim axis in the ice cores?
You mean the axis?
Yes.
Oh, yeah. And yeah, that's a good question. We haven't looked at that because I think the axis is the second order, which tell us like the moisture source or more complex process. But the problem is that I think the first order is not right compared to the model and data. But yeah, I can look at that later.
Okay, great. Thanks. I guess, in the interest of time, let's move on to the next speaker. And I do apologize if I get the pronunciation wrong here. It's Christo Wizard, the Greenland spatial fingerprint of Dansgaard Oscar events in observations and models.
Yeah, thank you very much for the introduction. And it is a very difficult name to pronounce. I apologize. It's a Dutch name. Even my own wife cannot pronounce it correctly. So I do not see any shared content. Are you sharing should I share my own screen? Because I did send the slides in online.
Yeah, you can go ahead and share the screen.
I'll just share my own screen? Okay. Because I wasn't, let me see. I gotta find it. Can you see my screen? Is it full screen?
It is full screen. It's falling off the screen a little bit, but
off the screen a little bit.
I think it's okay.
I can do that. Is it should I swap presenter?
Oh, okay, yeah, we got it now. Don't worry. Go ahead.
Is this better?
Oh, no. Put
It's
it back
worse.
the way it was. It was great. Yeah.
Okay, we'll go back to this one then. Okay, well, thank you so much. It's a real pleasure to be here and be able to give you this lecture today. So the title here is The Greenland Fingerprint of DO Events in Observations and Models. So I think for this crowd, I don't really have to introduce or define what Dansgaard-Oeschger events are. These are, the most prime example of abrupt climate change that we have in the paleoclimate record. Here are two records for the last 60,000 years. The top curve there is the stable isotopic composition of Greenland's summit ice cores, showing these really abrupt variations that are numbered here at the bottom, these DO events. And each of these represents about 10 degrees of mean annual warming in central Greenland. The bottom curve there is the waste divide methane concentration, and there's a very clear one-to-one relationship between the temperature in Greenland and these global methane concentrations, speaking to the global coupled nature of these oscillations. So the goal here today is to compile all the Greenland DO event data, and I'll compare it to isotope-enabled model simulations, including the CESM model that's the topic of your meeting. And I'll use this framework to improve the understanding of the dynamics of these events. So for this study, what I did, I compiled all the records we have from all these different ice cores. This is an overview of the ice cores. Here in the top is Camp Century, very old one. Then Neem, North Grip, GIS2, Renland, and Die 3. And for all these sites, where available, I cataloged the following data sets. The site temperature, as reconstructed from this proxy, the 15N isotopes. I don't have time to go into the details of how it works, but this is a seasonally unbiased mean annual temperature reconstruction. Then there's the water isotopic composition of the ice, the delta 18O. This is, of course, a proxy for temperature, but not a very good quantitative one. It's a qualitative climate proxy that is kind of complex to interpret. Then there's the deuterium excess of the ice. That's a proxy for this vapor source conditions. And last, there's the snow accumulation rates. So these data are available for some of these sites, not for all sites, for some events, not all events. So the database overall is a little spotty, but I tried to compile all the data that are available. And then the next step would be to compare this to the models. I want to emphasize that there are two sites here, the Renland site in East Greenland and the Die3 site in South Greenland, where we have new data. So this study involves new data from those two sites. And as you can see, that really greatly improves our spatial fingerprint. Instead of having just cores in the northwest of Greenland, we now have an East Greenland core and a South Greenland core. The Die3 core was drilled in the 80s, but we reanalyzed it with modern methods. So these are the data that I'll be looking at. The models that I look at are these two models that are published. There are many more models of simulations of DO events. However, when it comes to isotope-enabled model simulations, the pickings are a little bit more slim. These are the two published estimates. The first one here is this British HATCM3 study led by Louis Syme. That was the impact of abrupt sea ice on Greenland water isotopes, where they simulate a series of DO events. The second study here was from Cheng-Fei He. This is part of the iTrace simulation. As part of the deglaciation, there are two such abrupt climate events. There's the abrupt bowling onset, and the abrupt onset of the Holocene, which are interpreted here as traditional DO events, which they probably were in a sense. They have the same climate dynamics that underlie them. So this is the isotope-enabled version of CESM, ICESM. So let's just jump right into it. What I have here is sort of this, looking at this spatial fingerprint. So this is a bit of a complex figure, so let me talk you through it. Here on the right are the data. The black ones with the arrow bars are the data. I'm starting here as a transect. So D3, that's Die3 here, Summit, North Grip, and Neem. So going from the left to the right in this figure is a transect going from South Greenland to North Greenland. By the way, I hope you can all see my cursor as I'm moving along. Here on the right is the Renland side, which is sort of off by itself, off the main divide of the ice sheet. So I plotted it here by itself. The blue and the red curves are these two isotope-enabled models. There's the CESM model in blue and the HATCM3 model in red. The green curve you can ignore for now. It's not really that important. And I actually removed it from the manuscript as well. So the green line really shouldn't be there. So this is the fit to the data. As you can see, the models broadly agree with the magnitude of these changes, right? So the temperature changes here, the abrupt temperature changes are in the ballpark of, say, 12 degrees in southern Greenland to about 8 degrees of abrupt warming in northern Greenland. The CESM model particularly gets this south to north gradient really quite well. What is shown here on the left, the shading in the background is the CESM model because it performed the best of the two that we looked at compared to the data. And so the pattern really is one of south to north, where South Greenland, simply due to its proximity to the North Atlantic, gets a much bigger signal amplitude. When we look here at East Greenland, the Renland side, the magnitude of abrupt warming is really, really small in this side, maybe about 5 degrees Celsius only, really the smallest of all the sides we looked at. And all the models that we looked at overestimate the magnitude of the warming at this site. It could be just a microclimate issue. This is a local ice cap that is within this big mountain range. And so the models probably do not have the resolution to really resolve the microclimate of this site. The next figure here is the change in the water isotopic composition. What the data suggest here is that broadly, all these sites have about 4 per mil of increase in delta 18O across the DO event, with the smallest value being here at Greenland Summit, the largest value being here at Neem in the northwest, but they're very comparable. Again, the CESM model really captures the magnitude of these 18O shifts quite well. The HATCM3 model has a bit more of doesn't fit the data as well, particularly here in South Greenland. It really overestimates the magnitude of the shift in the isotopic composition. Again, here, the Renland side, both models don't do a very good job. So now moving on, this panel here, this bottom panel here, panel C, is a top panel here, so I already talked about it. This next panel here is the ratio. That's the isotope sensitivity. That's the change in per mil per Kelvin. In other words, this is the magnitude of the water isotope change divided by the magnitude of the temperature change. And this is an extremely important variable for us because this tells us how sensitive the water thermometer is to local climate change. So this is the parameter that we need to know when we're working on climate reconstructions using isotope. Again, the CESM model here does a remarkably good job, particularly here in central and southern Greenland. Here in northwestern Greenland, it misses the mark a little bit, but overall, really, really remarkably good agreement. Here at Renland, the model performs well. That's simply because it overestimates both the magnitude of the water isotope change and the magnitude of the temperature change. So the ratio does happen to fit well. Not because the model performs so well in either of the two individual categories. Moving on here, deuterium excess. The change in deuterium excess is anti-phase. So when we get a positive change in 18O, we get a negative change in this deuterium excess parameter. And again, it's fairly homogeneous across Greenland. So all these I-scores indicate somewhere between 3 and 4 per mil of change in deuterium excess. The HETCM3 model is not at all calibrated for deuterium excess, and I didn't plot it here. The CESM model, again, performs remarkably well. To my knowledge, this is the first time that these abrupt changes in deuterium excess have been simulated in a climate model. And so, the model gets the magnitude quite well. It doesn't quite get the spatial pattern, but it does a really good job with the magnitude, which is remarkable in itself. Then the bottom graph here is the change in the snow accumulation rate. So here expressed as a ratio. So that's the snow accumulation rate in the Greenland interstadial divided by the Greenland stadial that precedes it. What we find is that in most of these cores, there's about a doubling of the snow accumulation rate. Across the abrupt DO event, central Greenland, about a doubling. Here in the south of Greenland, the data are quite uncertain, but it looks like it may even triple. So we get a tripling of the accumulation rates here. And in this case, both models capture the data quite well within the uncertainty of the observation. So roughly about a doubling of snowfall across the DO event in central Greenland, and that's captured by the models quite well. So this was the model data comparison. And again, the conclusion here is that the CESM model particularly has actually remarkably good skill in simulating all the observable variables during a abrupt DO transition. Moving on to the link to sea ice, and this has been well established in the literature that these DO events have a very strong link to the sea ice concentrations. So these models have skill in simulating these events, and both these models simulate large migrations of the winter sea ice edge across this DO event. So the color is the scheme is the same as before. The red one here is the HETCM3, the blue is CESM3. And what we find is that during the stadial phase, during the cold phase, the wintertime sea ice edge is all the way out here, covering the entire subpolar gyre region, the SPG. The entire subpolar gyre region is filled here with winter sea ice. Whereas during the warm stages, the winter sea ice edge retreats and it still covers the Nordic seas. So much of the Nordic seas are still covered in sea ice here during the winters, but no longer the subpolar gyre. So there seems to be really in these models a focus on the subpolar gyre. I don't have time to go into the details here, but what we did is a series of idealized atmosphere-only experiments. So we took the IChem5, so just the atmospheric component of CESM, and we took that to do some idealized experiments. As you can see in this map here, I divided up the North Atlantic into different marginal seas, the Greenland Sea, Icelandic Sea, Norwegian Sea, Erminger, Labrador, and Baffin Bay, and here the subpolar gyre. And we performed idealized experiments where we applied sea ice and temperature anomalies to these different regions, as well as sea surface temperature anomalies. And so I don't have time again to go into details, but what we find in this this extensive series of atmosphere-only DO experiments, that really sea ice anomalies to the subpolar gyre are key, right? And so what we find from these idealized experiments, if we want to explain the DO fingerprint in Greenland, we have to do the following. One, winter sea ice cover during the stadial, during the cold phases, if one were to cover the subpolar gyre with winter sea ice during the stadials, that is a sufficient condition. If you do nothing else, just do this one thing, you can explain all the observations that I presented to you earlier. The second observation there is that sea ice in the Nordic seas alone is insufficient. There's quite some, I can point you to at least 5 to 10 papers in the literature that will argue that sea ice changes in the Nordic seas are critical to DO variability. I don't want to dispute that there are sea ice changes in the Nordic seas, but what these simulations show us, these idealized simulations, is that the Nordic seas alone are completely insufficient. You really need to have that much wider footprint of the subpolar gyre region to explain particularly the magnitude of the observations in Greenland. The Nordic seas by themselves, even if you hit them really hard with sea ice, they don't have enough oomph to really drive the signals that we see in Greenland. The third observation, sea surface temperature alone, also insufficient. You can do an 8-degree warming in mean annual SST across the entire North Atlantic, and still you fail to simulate DO events, right? DO events really require that sea ice extend, change into the subpolar gyre. There was no other way, at least in this ICAM5 simulation, there was no other way we could really simulate this database. And the last observation here is that I argued earlier that in this model, applying wintertime sea ice to the subpolar gyre is a sufficient condition, right? If you do this, you can explain all the observations in Greenland. I would also argue in these simulations, at least, it was a necessary condition. Unless we applied wintertime sea ice to the subpolar gyre, we could not explain it otherwise. This was the only way you could fit the observations if you did at least this very thin. So it's definitely a sufficient condition, and it may be a necessary condition to have wintertime sea ice in the subpolar gyre during the cold stadial phases of the DO cycle. The last thing I want to focus on, in the interest of time, is some moisture tagging. This is, excuse me?
2 minutes left.
2 minutes left. I think I can wrap it up in 2 minutes. So we did some moisture tagging experiments as well. So this is where the moisture comes from. We divided the world into these different boxes. There's the northern North Atlantic, the southern North Atlantic, North Pacific, and Northern Hemisphere land masses, and then the rest of the world. This is where the vapor in Greenland comes from. During the interstadial warm phases, the northern North Atlantic is by far the largest source of vapor to Greenland precipitation. However, during the stadial, we really removed this vapor source, mostly because of sea ice cover. So the extensive sea ice cover during the cold stages suppresses moisture delivery from these regions. And so we're really suppressing moisture delivery from both the northern North Atlantic and a little bit from the southern North Atlantic. And this is why we see this big reduction in snowfall. What we then did, we decomposed these, using the moisture tagging, we came up with this technique, Kyle Niesgoda did, came up with this technique of decomposing the change in water isotopes into distillation that happens en route, so between evaporation and deposition, just simply the changes to the water vapor source distribution and other changes. And we find that all the isotopic changes you see in Greenland, both the delta 18O and the deuterium excess, can just be explained by the change in vapor source distribution. The traditional interpretation of these ice core record is this orange one, right? It's radial distillation. People have always argued that these changes reflect distillation or radial distillation between the source and the site. What we find in these tagging experiments, you can explain all isotopic observations in Greenland simply by changing the vapor source. So what we're doing during a DO event, during the cold stage, we're suppressing these very proximal water sources. These water sources have very positive 18O and very negative deuterium excess. So when you remove this local source, you make the water isotopes that make Greenland more negative in terms of delta 18O and more positive in deuterium excess. So just the change in water vapor sources can explain the entire observations in the isotopes in the Greenland ice core record. This brings me to my conclusions, right? So we have new records. I performed this multi-proxy fingerprint of the DO signal from the data. We compared it to the models, and the models actually have surprising skill at simulating the DO events, particularly the CESM model, which is a nice note for your meeting here. We did some idealized model simulations, and we find that the subpolar gyre stadial winter sea ice cover is a sufficient explanation for DO events and may actually be a necessary explanation. And last, the water isotope signals in Greenland can be explained in these simulations entirely by changes in the source region distribution, and you do not need to invoke radial distillation or changes in local temperature to explain them. So thank you very much for your attention, and I look forward to any questions you may have if we have time to do so.
Okay, great. We are a little behind, but if someone has a brief question. No, nothing online.
No?
Okay. All right. Well, yeah, great. Yeah, I think we're gonna have to move on to the next speaker then, who is Andreas Schmittner, who will be telling us all about carbon and carbon-13 in the pre-industrial and glacial ocean, a precise and complete decomposition.
Hello, everybody. Can you hear me?
Yeah, we can hear you.
Awesome. And can you see my slides?
Yeah, they're not full screen at the moment, but we can see them.
Okay, let's see if I can. Still not full screen, huh?
No, I think you can hit the play button on the top bar of your keynote there.
Yeah.
Yeah, there you go. Perfect.
Okay, thank you. Thank you so much for having me. We move to the oceans and to carbon cycle, but stick to isotopes. So I'll present you some work that is about to be published in PLOS Climate that has been mainly performed by my previous grad student, Nathaniel Fillman, who has implemented diagnostic tracers in the ocean carbon and C13 model to make more sense out of the simulations of the glacial ocean. So a little bit of motivation. C13 has been long used as a tracer for ocean processes, ocean circulation, carbon cycle processes, but its interpretation is not easy because it's influenced by various processes. And here we can look at two different hypotheses for the whole ocean decrease in C13 during the last glacial maximum. For example, an early paper by Nick Shackleton suggested that this decrease in C13 was mainly due to the transfer of terrestrial carbon, which is isotopically light from land to the ocean, whereas Brovkin suggested that the biological pump increasing would also reduce that C13 and would be an alternative explanation for it. So what do? We use a data constraint, an isotope-enabled model, not CESM, but an intermediate complexity model, OSU version of the UVic model. We run LGM simulations with it, and we have in previous publications shown and compared it with with various a range of paleo observations such as temperature, C13, radiocarbon, nitrogen isotopes. And we are pretty happy with this LGM state that we have produced. It is consistent more or less with these observations, and it is featuring a shallower and weaker AMOC. And we also need to add iron fluxes in the Southern Ocean to match the data. So those are kind of the main features of this LGM states. And then we do a decomposition of the carbon and C13 tracers, similar to what we did for carbon in the Kadiwala et al. 2019 paper in Science Advances. But now we do it for the C13 as well. So we add 8 diagnostic tracers, preformed, saturation. So the preformed is just the concentration at the surface of carbon or C13, and that is then propagated into the interior. The saturation concentration is the surface concentration that it would be at saturation with the atmosphere. And then C-soft, that is the accumulated respired organic carbon in the interior, and CaCO3 is the accumulated dissolved calcium carbonate in the ocean interior. And so we have these 4 diagnostic tracers included prognostically in the model, both for carbon and for C13, so which makes 8 additional diagnostic tracers. And then what we also do, we run the model with and without biology to distinguish the physical effects from biological effects. So we start from a pre-industrial PI state that is equilibrated, and then we instantaneously apply LGM boundary conditions and run to equilibrium, and then we analyze the the last state, the end of the equilibrium run. We do have prognostic CO2 in this simulation. That is different from Kadiwala et al. But and the CO2 in the model is consistent also with ice core data. I'm showing you here the two model simulations. The full model, as you can see, goes from 280 or so in the earlier parts, representing the pre-industrial, to about 190 after we implement the LGM boundary conditions. Whereas the model without biology only has about a third or so of the CO2 reduction, implying that 60 ppm or so of the reduction in atmospheric CO2 during the LGM was due to biological effects. So biology is really important for this CO2 drawdown. Now the decomposition, as I mentioned earlier, the DIC we decompose into preformed components, which are the first four terms here. So the saturation components, the disequilibrium components, and then the regenerated components are added. So C-soft, the organic matter, and the CaCO3, the calcium carbonate. The preformed components, we additionally separate them into saturation, so equilibrium components and disequilibrium components, and each of which can be separated into physical and biological components. So that makes up these six fundamental components that make up DIC, and so the same for C13. And because the disequilibrium turns out to be an important component, I'd like to just briefly discuss what determines them and how they're different between carbon and C13. So if we look at a physics-only world on the left schematic there, and this schematic depicts like Southern Ocean processes of upwelling, North Atlantic deep water, then the water moves south at the surface, it loses heat to the atmosphere, indicated by the red wiggly line arrow there. That leads to cooling of waters and ingassing of CO2, which is more soluble at colder waters. But because that ingassing is incomplete, the waters, when they sink down in the interior, they don't have as much carbon as they would at equilibrium. So the disequilibrium, the physical disequilibrium, is negative. And for C13, because there's fractionation, colder water at equilibrium has higher C13. There's a tendency also to increase C13 as those waters move south at the surface. So we also have a negative physical disequilibrium for C13. Now, if we move on to the biological effects on the right-hand side, the upwelling of respired carbon from the deep ocean leads to outgassing at the surface. So the biological disequilibrium becomes positive because that outgassing is incomplete, and the water that subducts as Antarctic bottom water into the interior has an additional amount of carbon compared to saturation. Whereas for C13, since the organic matter is light in C13, as it's upwelling and coming to the surface, that leads to a tendency to decrease C13 as well. So the biological disequilibrium for C13 is negative. So we have different signs here for the biological disequilibrium for carbon and C13, whereas for the physical, we had the same signs. And if we compare physical and biological disequilibrium for carbon, we can see they have opposite signs. So the physical disequilibrium is negative, the biological is positive, so they compensate each other. Whereas for C13, both physical and biological disequilibria are negative, so they amplify each other, making a relatively larger disequilibrium, total disequilibrium for C13 compared to carbon. Now here is the quantitative results, and this figure is a little bit complicated, so I'll try to walk you through some main aspects of it. Those are the whole ocean integrated carbon on the left, and the whole ocean average C13 numbers on the right. For the pre-industrial in red, the red bars, the light blue bars are for the LGM, and then the purple bars on the bottom panels are the differences, LGM minus pre-industrial. And perhaps we can just look at the at the bottom panels here, in the interest of time, that the differences, the increase in DIC on the left-hand side is dominated by the biological disequilibrium increase. So the whole ocean increase in carbon is dominated by an increase in the biological disequilibrium. For C13 on the right-hand side, we can see C13 has decreased. The whole ocean C13 has decreased by about 0.4 per mil, which is consistent with observations indicated by the blue symbol there and the error bars. And that is also dominated by the biological disequilibrium, which is lower by about 0.6, 0.7 per mil in the LGM. So both carbon and C13 in the biological disequilibrium dominates those changes between the LGM and the pre-industrial. And just a note here on the accuracy of this decomposition, on the left-hand bars, the DIC, there's a little X symbol that indicates that would be the sum of all the individual components. Also for C13, the same. So all the different components add up very precisely to the total, indicating that this decomposition is accurate. Okay, since the biological disequilibrium is so important, I'm just showing you here next spatial distributions of this. On the left, we have the pre-industrial, in the middle, the LGM, and on the right, the difference, LGM minus pre-industrial. And on the top, we have surface maps. So if we start discussing the pre-industrial first, you can see positive values at low latitudes, except for the Eastern Equatorial Pacific, where there's upwelling, and in the high latitudes near the Antarctica, particularly, there's negative values. And if you look at the sections, the meridional sections in the Atlantic, in the center, and in the Indian and Pacific Oceans on the bottom, you can see that these negative biological disequilibria near Antarctica, they propagate into the interior, into the deepest layers, and fill the deepest parts of the ocean. So they dominate this global ocean, whole ocean changes. In the LGM, you can see that the disequilibrium near Antarctica is much more intense, and it also fills more of the deep ocean because the AMOC was shallower, which leads to a much larger increase in the biological disequilibrium, and the differences are shown in the right hand side panels. Here are some vertical profiles, horizontally averaged. On the left is the Atlantic, the pre-industrial in red and LGM in blue. And the solid lines are the models, and the dashed and dotted lines are observational estimates. So you can see that in the LGM, the model has lower C13 by about 1 per mil in the deep Atlantic, consistent with the observations, although the models slightly overestimates the absolute values in the LGM. But in the center panels, we have the differences LGM minus pre-industrial, and those are very similar in the deep Atlantic, about 1 per mil reduction in C13, consistent between observations and the model. And the right-hand side shows the decomposition, and it shows, so the pink, the purple or pink line is the absolute C13, and the light blue is the biological disequilibrium, indicating that this component dominates the total C13 reduction in the deep Atlantic.
2 minutes.
And if we move to the Southern Ocean in the center and the Indian and Pacific Oceans in the bottom panels, you can see that also the light blue line dominates the deep ocean, decreases in C13 in the models, illustrating again that the biological disequilibrium here is the dominant term for these deep ocean changes which dominate the whole ocean changes. Which brings me already to the conclusions. So the biological disequilibrium is the dominating component in increasing the LGM ocean's carbon and also decreasing its C13. which indicates a reduced sink of biological carbon in the LGM and not an increased source. Many people have argued an increased biological pump, but the active biological pump would be represented here in our decomposition by the C-soft components, which, if I may go back here, if we go look at the C-soft components, they're actually reduced in the LGM. So the accumulation directly of respired carbon is lower, consistent with a reduced export production in the model. So the source of biological carbon is reduced, but the sink of biological carbon, so the outgassing, essentially, is much more reduced, which leads to an increase in whole ocean carbon, as indicated by this biological disequilibrium component. Also, our results are inconsistent with the Shackleton hypothesis, because that hypothesis would imply an increase in the physical saturation component and not in the biological disequilibrium. And with that, I thank you all for your attention and look forward to questions.
Okay, great. Yeah, thanks for the presentation. Unfortunately, we're over time right now, so I encourage people to, if you have questions, you can go on the Zoom, talk about it in the chat, but I would like to get our last speaker a chance to give her presentation. So we have Ron Fung next, who's speaking about intermodal spread and mid-Pliocene radiative forcing from boundary condition and CO2 changes. Oh, Ron, I think you might be muted.
Yeah, good point. Yeah, I was just thinking, thanks for the introduction, Sam, and thanks everyone for sticking around. I'll try to talk through this fast. So this is really the research that's just started with my PhD student, Noah Cravat. So this project's really to look at what drives the mid-Pliocene as well as other Sandioc warm interval warms, and also what drives the model spread. So this is a Paleoclimate working group session. So I don't have to say too much about mid-Pliocene, just to highlight that this is the last prolonged warm interval with low glacial interglacial variability, and the CO2 is around 400 ppm. And on the land surface, we do see limited Greenland, only to the eastern side, and limited Antarctic ice sheet with the complete loss of Western Antarctic ice sheet. We have expansive boreal forest in the northern high latitude on land, and in the mid latitude and subtropics, we have greatly reduced desert extent. Instead, we have forests filling a lot of the desert regions. It is very well studied paleoclimate analog for understanding future climate change. I want to highlight the results from the most recent Pliocene model in the comparison project. So this table here is from the Haywood 2020 paper. This project involved 17 different models. They all run with the same mid-Pliocene, 400 ppm CO2, and boundary condition reconstructions. You can see they also feature a range of equilibrium climate sensitivity estimated by the warming due to a doubling of CO2. And when you look at the simulated mid-Pliocene warming, which is in this column here, you can see quite a bit of spread. Some models simulate as little as 1.7 degrees Celsius, but some simulate as much as more than 5 degrees Celsius. And you can see that this is obviously greater than what you would expected from a 400 ppm CO2 forcing alone. So as the first step to understand what really drives mid-Pliocene warms and also the model spread, we are trying to constrain the climate forcing strengths. We're using the effective radiative forcing and adjustments framework, which is used to study present-day climate a lot. So in this framework, effective radiative forcing is defined as the top of the atmosphere radiation imbalance after introduction of a forcing agent without any change in the surface temperature. So it's typically estimated with fixed SST and sea ice experiments with SSTs and sea ice from pre-industrial simulations. Correspondingly, the adjustments are changes that occur directly due to the forcing without mediation by the global mean temperature. Those adjustments includes heating horizontally different heating and cooling in the troposphere and resulted regional circulation, changes in clouds, vertical adjustments in the troposphere temperature profile, humidity and clouds, and different heating in the troposphere between land and ocean resulted circulation, clouds, other changes, as well as immediate biophysical changes, like changes in the evapotranspiration or changes in albedo and things like that. So in order to diagnose effective radiative forcing, I split the mid-Pleistocene forcing, climate forcing agents into 3 groups. So we carried out fixed SST and CS experiments with just changes in the CO2 alone to 400 ppm, and with vegetation ice sheet changes alone, and with combined geography topography changes alone. And then we also carried out an experiment with combined forcing. And we looked into 3 versions of CCSM, CESM, CCSM4, CESM1, CESM2. All the runs are around for 30 years, and I would take the last 20 years for average. So ERF, effective radiative forcing, is estimated by the difference in the top of the atmosphere radiation imbalance between the perturbed case and the pre-industrial control case. To calculate the adjustments, we use the kernel coefficients published by Angie Pendergrass, multiply a state change between the perturbed and control case, and the state change include troposphere temperature, surface temperature, humidity, and albedo. To estimate the cloud adjustments, we compare the clear sky and the total sky adjustments and the direct radiative forcing. To note, we do have to correct for land surface changes, despite we fixed 70% of the surface with the SST and CS conditions of the pre-industrial. Those simulations do allow land surface changes. So to discount that, we subtract the land surface adjustment calculated with the kernel coefficients. So this is going to be very quick. Here are some of the estimates. This chart is organized in such a way that y-axis shows a combined forcing, topography, geography forcing, ice vegetation forcing, or CO2 forcing, and different bars actually shows different model results. And for both the raw ERF, we calculate directly from simulations, and the corrected ERF, we corrected for land surface temperature change. The CO2 forcing is the predominant control. With the corrected ERF, we have CO2 forcing accounting for about 60% of the total combined forcing. However, you do notice that the changes in vegetation ice sheet also plays an important role in providing the forcing for the mid-Pleistocene, and they're about 2/3 of the forcing of the CO2. And luckily, they're actually partially compensated by the negative forcing due to vegetation and geography changes. You also notice there's forcing increase from CCSM4 to CESM1. And however, they're from different reasons. They do correspond to the increase in model climate sensitivity from CCSM4 to CESM2. However, the forcing increase from CCSM4 to CESM1 is actually primarily from the non-CO2 forcing. We see an increase in the forcing from ice sheet and vegetation changes, but decrease in the compensating forcing from topography and geography changes. In contrast to the forcing increase from CESM1 to CESM2, sorry about that, from CESM1 to CESM2 is actually primarily from the increase in the CO2 forcing. So what are the adjustments that potentially contributed to these differences in forcing between models? So in the case of the CO2, we can see that the net adjustments is negligible if we sum all of them, but it's actually 20% in CESM2. And we can also see that the albedo adjustment, humidity adjustment, and cloud adjustments all turns to amplify the initial radiative perturbation due to the CO2. And it's interesting that in CESM2, you do see a much greater cloud adjustments compared to the two previous versions of the models, which contribute significantly to the overall greater CO2 forcing in CESM2. Interestingly, if we look at the adjustments to the combined forcing, actually the cloud changes or cloud adjustments switch signs. In this case, the cloud adjustments actually tend to compensate the forcing. For the combined forcing, it's primarily driven by albedo changes with a little bit additional adjustment from the tropospheric humidity. We can further look at where the source of the ERF is on the spatial map. So for the CO2 forcing, is the strongest in the tropics and in the Arctic region. In contrast, forcing from vegetation ice sheet changes or from topography, geography changes are very regional, and they primarily reflect where we have land cover changes, for example, in the Sahel region and in the subtropic and Milachu region. When we have afforestation, we also show very strong positive forcing. And similarly, in the northern highlight shield, we see very strong positive forcing as well. Topography, geography, we see a strong negative forcing actually around the shelf region in the tropical Pacific, Western Pacific, due to changes in the land mass as a result of isostatic rebound, as well as mantle convection predicted by the model. All right. So here are some preliminary results. We don't have a lot of results yet. So CO2 perturbation provides about 60% of the forcing for the mid-Pliocene climate. We do have another 40%, which is actually from non-CO2 changes. The combined forcing increases with increasing climate sensitivity, which partially explains why when we use those models to run the mid-Pliocene experiments, we do see a enhanced warming from CESM4 to CESM2. However, our decomposition suggests that they're actually from different sources. So the forcing increase from CESM4 to CESM1 is actually due to non-CO2 changes, but from CESM1 to 2, a large part or the majority of it is from CO2 change. And we also notice there's a switch signs or adjustments to the combined forcing differs from the CO2 forcing. The most noticeable thing is cloud actually switched sign. And we're still investigating on why that would be the case and what are the other feedbacks that are brought by the non-CO2 forcing. Yeah, that's all I have. Hopefully I didn't take too much of the time.
Great, thanks, Ron. I guess we have a minute or two for questions if anyone has one for Ron or any of the other speakers.
Maybe I can ask one. Thank you, Ron. Very nice work. I'm wondering for Pliocene, now you have forcing, you have temperature response. Have you calculated the feedback parameter? Do you see similar results as, say, the abrupt 4 times CO2 or ECS simulations in terms of the climate feedback parameter?
I haven't done that. The short answer is that's something we're going to do, and we're missing a simulation at the moment. So we have the topography geography change in the coupled simulation, but I don't have the one just with ice sheet and vegetation changes yet. Yeah, but I haven't looked at it. However, I do notice it's potentially the vegetation ice sheet changes or non-CO2 changes potentially have a higher efficacy compared to the CO2 changes because despite they only have 40% of the contribution to the forcing, when we actually look at the total warming in the Pleistocene compared to the pre-industrial and compared to what you would expect it from CO2 changes, it's actually comparable or even slightly greater than what you would expect from CO2 change. So the forcing is less than CO2, but the warming is comparable, even a little bit more. So yeah.
Do we have more questions?
No. So we're standing between people in a plenary session. So yeah, I guess let's wrap up here. So yeah, let's thank all of our speakers again. Yes, so that concludes our session. And just a quick reminder for everybody who's here in town, there is going to be a happy hour at 5:30 at Rayback. So hopefully see you there. Thanks.